No, thank you, everyone.
Yes, and YouTube is live.
Jason, I like the eagle on the top of your hat.
Yeah, it's a duck.
Oh, it's a duck.
It's supposed to be. I'm at the beach house right now, so I think it's supposed to be like a pelican or something. I can't tell what it is.
Looks like an eagle to me.
Looks like an eagle, though.
Okay, I'm seeing a live stream that could be live for me now that it's on. So I'm gonna close my I'm gonna close my browser. And Jason, are you recording?
I am recording. Yeah, I clicked on record. I'm logged in from two places. The beach house here doesn't have the greatest internet, so I'm remoted into my system at home and recording from there. Should have no problems with that at all. I do not see on the TAPR Digital YouTube channel anything live streaming.
Yeah, I see it here.
Do you? Okay, yeah. Maybe I'm on the wrong channel.
You have to go back to home and go back into the...
And you might have to refresh and stuff.
I've done all that.
Yes, but anybody who's subscribed to the TAPR Digital stream should have got an email or other notification. And with that...
Good, that works.
Right. And YouTube is delayed, so...
Yeah, there is a 30-second delay.
15.
Mm-hmm.
It was.
I tell people 30 to be safe. It's supposed to be 15, but
yes, it depends on all kinds of latencies everywhere.
Right.
So, everybody but Stephen, please disable your video and Stephen.
Okay. Well, thank you, and good morning to everyone. Here in Arizona, the sun is just starting to come up and we're starting to see some daylight outside, but we're really happy to have everyone joining us for this very first virtual digital communications conference. It is also our 39th annual digital communications conference. We were originally going to be in person in Charlotte, North Carolina. However, with the COVID-19, George, can you mute your mic, please?
Oh, sorry.
So we were going to originally be in Charlotte, North Carolina, as an in-person conference. And of course, the COVID-19 virus has really upended everybody's lives around the world. And so the conference was basically postponed, and we went through all the planning and work to be able to bring it online. So we're really pleased with how well it's turned out. We have been doing a great deal of planning. We did some practice this week, and we've watched other conferences as well, and to kind of learn best practices and what techniques we would like to use. And one of those techniques that you're going to observe is that we requested the presenters to pre-record their presentation. And this had a number of benefits, and we kind of learned this from the QSO Today Expo, which was a couple of months ago. They did that. And so we got to give them credit for that idea. Gave the presenters, I hope, a great deal of flexibility. One, that, we gave them plenty of heads up, gave them plenty of time to be able to put their presentation together, put their recordings together, perhaps even practice, and taken a couple of opportunities. They can sit there and select the one that they feel is the best and submit that one. And it helps especially those presenters that we have around the world. It's really exciting. We have 20 plus talks available today and tomorrow. And we're really fortunate and glad to have a number of presenters from around the world. We're going to have a presentation from Japan, France, Germany, Canada, Italy, just to name a few. I may have missed one or two there. And it allowed those folks, of course, to be able to put together their presentation in their time zone. Because there's one thing about a virtual conference that we're not able to overcome, and that's time zones. We went ahead, since this was going to be in Charlotte, North Carolina, which is in the Eastern time zone of the United States, we decided we would anchor this virtual conference on that time zone. Who knows, maybe if we do this more in the future, and if this is very successful, we can find a time zone perhaps that's a little more centralized. But again, it's kind of a challenge with a worldwide audience, but what we can do is for those presenters, we can schedule them at times that are more convenient for them in their time zone. We encourage you to interact. That's one thing about a virtual conference versus an in-person conference is, you know, there's a lot to be said about being able to shake hands and talk and have lunch with others. It's a great part of the in-person experience that is the Digital Communications Conference. Of course, number one is the technical talks, which is what we can bring to you with the virtual conference here. So the interaction will be limited to the chat window. So that'll be your window into the conference. And of course, you'll notice that at the very bottom, you can either send your chats to the panelist. The panelists are those that you see on the screen. Attendees are the ones that are observing, logged in and observing. So you can kind of control who they go to, but feel free to use that. When it comes time for questions and answers, this will be your way of asking the question. The moderator will gather the questions off of the chat window and then present those in their voice to the presenter. And that'll allow the presenter to answer back in their voice as well. We're going to have a couple of situations here where the presenter themselves is unable to join us. So we will play their presentation and we'll allow some interaction and some chat. We're going to stay on schedule. We're not going to get ahead of schedule. This will allow people who are perhaps busy during the day, but would like to observe the 1 or 2 or 3 talks that they find interesting. So we're going to keep that on the schedule. So the schedule as we're going to run it is on the DCC website. Let me bring some URLs up so you can see. And F5. Okay. Come on. Let's dock on it. Oh, here we go. Okay, so here's our welcome. But I wanted to be able to show you these URLs here. And the schedule itself is up on the DCC website. The papers, I'm very happy to say that the presentations or the call for papers that we put out earlier in the year yielded 14 papers. So the printed proceedings is over 230 pages long, which is really exciting. There's some really exciting papers in there. If you'd like to see the titles of each of those papers, we put those up on the TAPR website as well. There will also be a link up there where you can click on and order a printed version of it. Right now, the price of that is set at $9 plus shipping. And of course, the shipping depends upon whatever shipping method that you choose and wherever you're located. And also, we do have a survey set up on the website too. So during the conference, if there's something you'd like to comment on, jump over there to the survey and fill it in. You can fill it in anonymously, or you can enter your name and information and we can get back to you. And of course, I encourage you to go back there as often as you want to or need to throughout the conference. Let us know how we're doing and what you like, what you dislike about it. And is this something you'd like for us to see going into the future? And this is pretty exciting to us. being able to put this on for you. And we will for next year, and that's the year of 2021. And of course, it all depends upon how this COVID virus plays out and whether or not we are able to get back to, you know, what we considered normal in the past. And if, in other words, if we're able to get back together again in large crowds, if that's allowed, then we will be back in Charlotte, North Carolina for an in-person DCC, and that's scheduled in the third weekend of September. And of course, as time grows nearer that time, we will provide more and more details. So of course, everything's still up in the air. It's about a year away, but I wanted to kind of give you a heads up that we basically worked with the conference hotel that we're working with. It's the Hilton Airport Conference Hotel that's near the Charlotte Airport. And we moved this year's conference to next year's. And of course, we shall see how that plays out. Well, I think that's about everything that I wanted to be able to present and say welcome and thank you. And thank you to all of our presenters. And we hope that we have a very exciting time for you all. And we got about 3 more minutes before we start the first talk. So if you have any questions or comments, please put them in the chat box. With that, I'll give big 73s out to everyone. Sit back, relax, and enjoy the show.
Steve, would you please sign in on Slack?
I'll do that.
Thank you. A few brief notes on how we're doing this. We're using the Zoom webinar platform. We've got a 500 attendee license because clearly we've gone over 100. We're using Slack as a back channel communications mechanism, totally independent of Zoom for all the moderators, showrunners, and TAPR board members. And with that, do we have questions? I don't see any coming here. Yeah,
I don't see anything on the chat right now. So go ahead and queue up the first talk, Nathaniel's talk.
That's what it is.
Good morning, Nathaniel.
We do have a question, George, where the slides will be available.
So, okay. So in the process of gathering all the data for this, we had the presenters upload their MP4 video and their slide deck as a PDF. Immediately following the conference, the PDF slide decks will be available by link from the TAPR website. And when I say immediately, give us a couple days. You know, we'll be worn out. And also, we can provide immediately the pre-recorded videos, but it'll take us a little while to slice and dice by talk to include the QA session. And that's what Jason Johnson of Ham Radio 2.0 is doing for us. And of course, the YouTube stream pre-recorded will be available for people to be able to peruse those, but that will not be slice and dice by talks. So Nathaniel, I'm about to turn on, share my computer sound, and ladies and gentlemen, here we go.
Hi, my name is Nathaniel Frizzell, W2NAF. I'm an assistant professor at the University of Scranton, lead principal investigator of the Personal Space Weather Station project, and leader and founder of the HamSCI community. Today, I'm going to talk about the HamSCI Personal Space Weather Station, architecture and current status. I'm very pleased to be here talking about this project at the 2020 virtual ARRL TAPR Digital Communications Conference. Without the collaboration from TAPR, none of this would be possible. As you can see, I have many co-authors on this project. In this presentation, I will give a high-level overview of the Personal Space Weather Station project. Throughout this year's DCC, you will hear from many of my co-authors who will be giving detailed updates on their respective parts of the project. The amateur radio hobby is truly amazing as it has so many facets. with just a few different ones shown on this slide. I personally have always had a tremendous fascination with the high frequency side of the hobby, as I'm sure many others listening to this presentation have as well. For me, one of the major driving factors of this fascination is not only HF radio's unique ability to propagate over the horizon and around the world, but also the variability associated with that propagation. We know that this variability is caused by changes in the ionosphere driven by a complex mix of forcing from space, forcing from the neutral atmosphere, and internal physical processes. In spite of more than a century of study, there is still a great deal that we do not know about radio propagation or the ionosphere. Although we have some understanding of the big picture, we do not understand the short-term, small spatial scale dynamics that affect our daily radio operations. All of this has helped to bring on the idea of the personal space weather station. It is actually Ward Silver, N0AX, who said after the 2017 Eclipse project that this should be HamSCI's next project. It is very exciting to be here today with TAPR and all of our collaborators who are working together to make this a reality. By working together with both the amateur radio and professional geospace science communities, it is my hope that this project will simultaneously help to advance our knowledge of the ionosphere and be useful to amateur radio operators around the world. As you can see in today's presentations, the PSWS is not something you can go out and buy today. Instead, this is a collaborative project that is being designed and developed right now. So what is a personal space weather station? The HamSCI Personal Space Weather Station, or PSWS, is a multi-instrument ground-based device designed to observe space weather effects both as a single point measurement and as part of a larger distributed network. It is personal because it is being designed such that an individual should be able to purchase one and operate it in their own backyard. For amateur radio operators, the Personal Space Weather Station should provide information about current radio propagation conditions both locally and as part of a global network. In addition, the Personal Space Weather Station design takes into account the needs of professional researchers who want to study specific aspects of the ionosphere and space weather. The Personal Space Weather Station is being developed as a collaborative project under the Ham Radio Science Citizen Investigation HamSCI Collective, which is led by the University of Scranton with collaborators at Case Western Reserve University, the New Jersey Institute of Technology, University of Alabama, the MIT Haystack Observatory, TAPR, and volunteers from additional universities and the amateur radio community. Before we get into the design and status of the Personal Space Weather Station, let's review some ways we can remote sense the ionosphere using amateur radio frequencies and show a few examples. So how are we able to remote sense the ionosphere using amateur radio frequencies? If the conditions are right, radio signals of a particular frequency will be refracted back to Earth by the ionosphere, the electrically charged layer of the atmosphere from about 60 to 1,000 kilometers altitude. This is most common in the medium and high frequency bands, which range from 0.3 to 30 megahertz. The red path in the ray trace diagram displayed here models the transionospheric link on 14.03 megahertz between AA2MF transmitting in Florida and Whiskey Echo 9 Victor receiving 1,700 kilometers away in Wisconsin. The ray trace is computed using the FarLap ray tracing toolkit through a solar eclipsed version of the SAMI-3 first principles ionospheric model. The ionosphere will modulate the radio signal as it passes through, and these modulations can be used to remote sense the ionospheric state. It is useful to examine radio signals across a wide range of frequencies because the ionospheric effects on radio waves, including refraction and absorption, are frequency dependent. Because of this, it is advantageous that we as amateur radio operators have a license to transmit on a large number of slice bands distributed throughout the radio spectrum, including those shown in the table on the right. Thanks to systems such as the Reverse Beacon Network, the Weak Signal Propagation Reporting Network, or WhisperNet, and the PSK Reporter, we already have real-time and archival radio propagation observations available to study. These networks are quasi-global, and the data archives now cover an entire solar cycle. Already, we have been able to use data from these systems in peer-reviewed scientific publications. The next few slides will include examples of this. As an example, the figure on the left shows observations and model results from the 2017 total solar eclipse, published in Geophysical Research Letters. The top figure shows 14 megahertz amateur radio reverse speaking network observations before, during, and after the eclipse. The bottom panel shows model results using far-lap ray tracing through the SAMI-3 solar eclipsed ionosphere. Both the observations and the model show the drop-off in 14 megahertz radio communications as a result of the eclipse-induced electron density depletion. The figure on the right also shows observations from the 2017 total solar eclipse. These are unpublished carrier frequency measurements of the 10 megahertz signal transmitted by WWV in Fort Collins, Colorado, and received by an amateur near Milwaukee, Wisconsin, using a receiver with a GNSS disciplined oscillator reference. From 14 to 16 universal time, positive excursions from the 10 megahertz are likely due to a shortening of the propagation path as atmospheric densities increase throughout the morning. Conversely, the negative excursions in the measured frequency are observed in the evening from 20 to 22 UT. Eclipse effects are observed between 16 and 20 UT, with negative excursions during eclipse onset and positive excursions as the eclipse ends. The sudden jump in observed frequency just before 18 UT is associated with a C-class X-ray solar flare observed by the GOES spacecraft. While we have been able to make great use of the RBN, WhisperNet, and PSK reporter data, we note that these systems were not necessarily designed with the goals of generating scientific-grade observations. Therefore, reports from these systems may have limited timestamp accuracy, frequency stability, and flexibility for designing special observation modes. Therefore, and furthermore, frequency measurements like the ones shown here are often difficult to make and are not automated. This is where the Personal Space Weather Station project is working to address these issues. The Personal Space Weather Station will also incorporate instruments such as a ground magnetometer and GPS GNSS receiver that will enable a more complete set of ground-based geospace environment measurements. So what makes up a Personal Space Weather Station? At the heart of the Personal Space Weather Station is a software-defined radio receiver with frequency coverage from about 100 kilohertz to 60 megahertz. The frequency range was chosen because signals in the medium and high frequency bands from 300 kilohertz to 30 megahertz are particularly sensitive to variations of the ionospheric state. This receiver will be able to listen for signals of opportunity and transmissions made specifically for coordinated experiments. The primary output of the software-defined radio will be raw in-phase quadrature IQ samples, which can then be derived into a variety of data products. This includes snapshots of the entire high-frequency radio spectrum, Doppler shift measurements of signals received from standard stations such as WWV and CHU, oblique ionograms from ionosonts of opportunity, decodes of digital amateur radio signals including FT8, the weak signal propagation reporter whisper mode, and Morse code, which can be sent to the reverse beacon network. These SDR observations can also be used to measure high-frequency band noise and detect lightning signatures. A dual-frequency global navigation satellite system, or GNSS receiver chip, will be used to serve as a highly stable frequency reference, provide precision timestamping with 10 to 100 nanosecond accuracy, and provide total electron content TEC measurements. A magneto-inductive ground magnetometer will provide 3-axis magnetic field measurements at a 1-second cadence with approximately 10 nanosecond resolution. A local computer will coordinate operation of all attached instruments, handle local data reduction, provide a local user interface or display, and send data back to a central database and receive commands and updates from the central control system. This system is modular, so instruments can be added or removed as needed. For instance, high-latitude users may want to add an auroral camera. To help maximize adoption, 2 versions of the Personal Space Weather Station are being developed, a highly flexible software-defined radio-based version and a more focused low-cost version. The software-defined radio-based version has the features that were already described, a synchronized dual-channel 0.1 to 60 MHz FPGA-based direct sampling software-defined radio, cross-polarized wideband receive antennas, and a dual-channel GNSS module for precision timestamping, frequency reference, and total electron content measurements. A more powerful single-board computer such as the Odroid N2 will be selected as the computer. The SDR in this version is known as the Tangerine SDR and is being developed by TAPR. The target cost of this system is about US $500. The low-cost version of the Personal Space Weather Station is being developed by the Case Western Reserve University and the Case Amateur Radio Club, W8EDU. The radio in this system is known as the Grape and has a target cost of about US $100. The Grape radio has a single channel and antenna and can measure high frequency variations of received signals such as those from high frequency standard stations, including WWV in Fort Collins, Colorado, and CHU in Ottawa, Canada. A single frequency GNSS discipline oscillator is used as a frequency standard and for precision timestamping. An inexpensive Raspberry Pi will serve as the computer. Both versions of the personal space weather station will use the same hardware for the ground magnetometer. Additionally, the software-defined radio-based version will have a mode to emulate the low-cost version to allow uniform data collection across the maximum number of nodes for specified campaigns. The Personal Space Weather Station project is highly collaborative with multiple institutions, organizations, and volunteers participating. This project falls under the HamSCI Collective and receives funding from the National Science Foundation. The University of Scranton is the lead institution for both the HamSCI and the Personal Space Weather Station and is responsible for overall project integration in radio science. TAPR and Zephyr Engineering Incorporated are responsible for the Tangerine SDR engine, RF module, clock module, and magnetometer engineering. Case Western Reserve University and the Case Amateur Radio Club, WWVD, lead the development of the low-cost personal space weather station. The New Jersey Institute of Technology is providing scientific oversight of the ground magnetometer. The University of Alabama is responsible for this system software and database design, and MIT Haystack Observatory is serving as a science collaborator. In addition, the open nature of the development process has allowed many other institutions and people to collaborate and contribute. So here's the current engineering status of each of the different teams. As you can see, we are moving along in the design phase and we are approaching prototype creation. And this is true for the Tangerine data engine, RF module, and clock module. Same thing with the Magneto Pi Hat. And for we do have some prototype versions of the magnetometer out already in collecting data. There's also the low-cost version. There are some Generation 1 prototypes currently deployed, and the case group is engineering Generation 2 right now. The control software and database currently runs on an Odroid N2 single-board computer, and it uses data from a Tangerine SDR simulator, which consists of a flex radio with GPSDO and IQ output and can monitor up to 16 band segments at a time. So we are definitely moving along with the engineering of this project and hope to have even more prototypes and hope to really have prototypes soon. So in summary, HamSCI is a collective that aims to bring together the amateur radio and professional space science research communities for mutual benefit. In an effort to improve the scientific usability of amateur radio observations and aid in amateur radio communications, HamSCI is developing this personal space weather station designed with science requirements in mind from the very beginning. And these modular systems will include HF radio receivers for studying the ionosphere using signals of opportunity, ground magnetometer with approximately 10 nanotesla resolution, GNSS receivers for precision timestamping and frequency stability, at a target price between about $100 to $1,000 depending on capabilities. So finally, I would like to acknowledge the support from the National Science Foundation, the amateur radio community, my science and engineering collaborators, and the many other people who have helped to make this project possible. Thank you very much and enjoy the DCC. Hello?
Yes, you're on.
All right. Well, thank you very much. I don't see any questions in the Zoom chat right now, but I guess one comment I want to make, because there's not a lot of time for questions. That presentation is supposed to be an overview talk basically for many of the presentations you're going to see today and tomorrow. So all of the presentations up until about 2:30 today are in support of this HamSCI Personal Space Weather Station project. And some of the ones tomorrow too are related as well. So I just hope that presentation kind of puts everything else into perspective And throughout today, we'll learn more about both the engineering and the science projects that people have been working on connected to this larger personal space weather station project.
Yeah, Nathaniel, we have a question from the YouTube user. They want to know if the Odroid's running Linux, and is there some preliminary support for streaming IQ to or from a Flex radio?
Yes, I believe the answer to both of those questions is yes. And that will be in Bill Engelke's talk. The Odroid is running Linux. He has a mock-up of the data engine, and that mock-up is actually being fed by his Flex radio. So he actually has it implemented right now.
And we have another question of when can I get one, which is coming later.
That's right, that's coming later. And that was one of the points I tried to make in my presentation right now too, is, this is something we're actively developing. So we're hoping to see some prototypes of the Tangerine later this year. But I think you'll be talking about that more in your presentation, right, Scotty?
Yes, I will. And another question is there a way for me to contribute to the project, and how can I get one?
So I think Christina will be talking about some ways that you can, well, I guess it also depends what you would like to do to contribute to the project. Right now, the best way to contribute to the project is to join into the Tangerine SDR telecons on Monday nights, and that information is available at tangerinesdr.com, or to go to hamsci.org and click the Get Involved tab. You can find out about our telecons there, and you can find out about the join our listservs as well. And that way you can become part of the development process, and then you'll know exactly when things are going to be available and what the status is.
Nathaniel, there was a question from the chat on more details from Kenya, more details on the magnetometer.
Great. So that's going to be in Dave Witten's and Scotty's, Dave Witten and Hyomin's talk later today. That will be at, I think that one's at 2 p.m. Eastern, I think. To double check the schedule here. But we do have, for that one, we do have some prototypes or, early beta test units that are collecting data right now. They'll be able to show what some of that data looks like. And Scotty has been working to do the CAD layouts for that unit as well. So I think we're getting closer to going to do a prototype production run, making somewhere between 25 to 50 units just for testing.
I think it's 3 p.m. Nathaniel for that presentation, Eastern Daylight Time.
Great, 3 p.m. Eastern Daylight Time is the magnetometer presentation. Thank you very much, George.
And another question, Nathaniel, are the low-cost prototypes deployed going to send data to a central database?
Yes, they will. So the low-cost, the low-cost personal space weather stations will send it to a central database. It will go to the same central database that the regular Tangerine SDR1 will as well. Will the prototypes do that? That's still in development, but that is where things are going to go. Everything will be sending data to a central database.
Okay, and question Christina answered in the text, but the question was, will the control software be available standalone for folks who want to use a radio like a IC7300?
I don't know that we will be able to provide that directly from our team, but this is something where, as a collaborative open source project, it's something that, we could get a volunteer, or if someone wants to volunteer to help implement that. I think we would welcome that. The system that we are developing right now, I think there's going to be basically the control software for the local system is going to be divided into two parts. One part's going to, talk to the radio, and the other part's going to talk to the central database. And so if you take the radio portion, that should be able to be modified, and we'll make the API available so that if someone wants to modify it and make the existing radio system work with that, they would be welcome to do so.
And one more question.
Last question. We need to start Steve's.
Okay. Is there an estimate on how many stations worldwide are needed to get good and overall data? And as an aside to that, you talk about signals of opportunity. Will there be use of signals specifically transmitted to do a study rather than just signals of opportunity?
Those are both great questions. The answer to the first question, how many stations do you need? It really depends on what you're looking at. So there are some things where you could probably get away with 1 or 2 stations, and if you have good quality data, you can do something interesting. And we'll see examples of that in Steve Serwin's talk next, where he's just using a single station. At the same time, if you're looking at things that are more on a global scale, we're going to want as many stations as possible. So no matter if there's 1 station out there or if there's 5 million stations, we should be able to do interesting science. And what was the second question?
Whether there's going to be you're going to be using only signals of opportunity, or whether there's going to be specific signals that you will be able to use to analyze the data.
I hope that we'll be able to use specific signals in the future as well. But right now we're starting out with the signals of opportunity. But this is also a great way for, say, like the frequency measurement test community to collaborate. They could put up a beacon, or we can even, get an experimental license possibly, or coordinate with specific ionosons or super darn radars. So I think there's a lot of opportunity for doing coordinated campaigns as well.
Thank you, Nathaniel. And now on to Steve Serwin, WA5FRF.
Thank you, George.
Good morning. My name is Steve Serwin. I'm here to talk to you about HF community to assist in ionospheric propagation studies. Ionospherically induced frequency variations. These spectrograms show observed frequency characteristics of 5 megahertz WWV during the day, night, and the transition periods. Typically, these on-air spectrograms showed smooth daytime and turbulent nighttime characteristics, and a prominent negative swing at dusk and a positive swing at dawn. And the dawn swing additionally showed multiple higher order swings that sometimes manifested abruptly mid-transition, as you see here. Understanding more about this wild behavior was really the motivation for development of many of the analytical tools that we report in this paper. Here's some additional spectrograms of the dawn and dusk frequency behavior. The positive dawn swings show more mode splitting and include frequency tracks that often manifest or extinguish abruptly mid-transition. The negative frequency swings at dusk on the lower part of the figure are generally more docile, probably because of the moderating effect of recombination. This is a snapshot of predicted propagation paths from WWV to WA5FRF, roughly Fort Collins, Colorado to San Antonio, Texas, on the morning in January of 2020. You can see 1, 2, and 3 hop modes are possible and from multiple ionization layers. During the morning transition, the ionization lowers with time in response to descending and intensifying sunlight. The lowering effect of height shortens all the path lengths. The rate of path length change provides the velocity that gives rise to Doppler shifts. Several mechanisms for the observed mode splitting have been hypothesized. One is for the refraction from the same layer, the 1, 2, and 3 hop modes have path lengths that increase with the number of hops because of the extra up and down zigzagging. As the common refraction layer descends, the modes with more hops have more change in absolute distance. Since the foreshortenings occur over the same time span, the longer paths have a higher velocity of path closure. And because Doppler shift scales directly with velocity, the higher order modes therefore show more frequency shift, and this could result in the mode splitting. The multiple hop modes that manifest abruptly partway through do so when the ionization reaches a level sufficient to support the required high angle of propagation. Now, other mechanisms are possible and have been postulated. Bill Engelke, AB4EJ, suggested different Doppler tracks could occur from simultaneous refractions from different layers. Bill Lyles, WQ6Z, suggested changing wave speed could be responsible for producing frequency shifts. Indeed, an accelerating wave speed produces the same wavefront bunching as a decreasing propagation path, and the results are indistinguishable. So analyzing propagation with targeted experiments to look for things like propagation angles, skip zones, time to flight can help unravel what's going on. These are some of the methods and techniques developed or used in this study. They include the method to extract precision frequency data from a receiver by downconversion of the RF carrier to an audio tone, simultaneous spectrogram recordings to look for correlations across multiple WWV frequencies, the use of oscillographic displays to study short-term amplitude and frequency effects, time flight measurements to produce or deduce propagation modes, and separation of simultaneous WWV and WWVH spectrograms by deinterlacing the 500 and 600 hertz side tones they use. So here's two 24-hour recordings of 5 megahertz WWV taken during the HamSCI Festival of Frequency Measurements. Top trace is a spectrogram using Spectrum Lab. Lower trace is a frequency record obtained with FL-Digi. The difference is Spectrum Lab presents FFT spectrum analysis at each sample interval, whereas FL-Digi outputs only the single frequency of the strongest signal present in each time slot. When the actual frequency track is mostly single valued, like during the middle parts of the day and at night when the wanderings don't get too extreme, the two show pretty good agreement. But during the dawn and dusk transition periods, a spectrogram is the clear choice. It faithfully represents each frequency component present when mode splitting occurs, whereas a single frequency measurement outputs a noisy band of frequencies that result when the different amplitudes capture the FM demodulator. So while the single frequency format works well for frequency measurement, an in-depth analysis of propagation phenomena really require the spectrogram format. Simultaneous recording WWV on multiple frequencies can provide insights into frequency-dependent propagation effects. These three spectrograms are for WWV at 2.55 and 10 megs. The lower two frequencies were steady during the day and turbulent at night. The 10 megahertz frequency was turbulent both day and night. Only weak correlations over frequency were observed during the turbulent times, and the turbulence amplitude did not scale with center frequency, which is interesting when you consider where it might have come from. The 2.5 and 5 megahertz frequency tracks manifest multiple higher order modes during sunrise, but 10 megahertz does not. This probably speaks to supported angle of propagation versus frequency. Some modes manifest or extinguish abruptly midway, and all frequencies contain a mode that shows very, very little shift at all. Things happen with propagation on both long and short timescales, and here's some interesting results in a short-term observation done with an oscilloscope. These dual trace oscilloscope videos show short-term variations in frequency and amplitude in real time. Two 1 kilohertz sine waves are displayed in each video. The stable trace, the one that doesn't move, is from a GPS stabilized lab function generator. The variable trace is the 5 megahertz WWV carrier downconverted 1 kilohertz and passed through a 10 hertz wide bandpass filter to strip off the native modulation. So here are two tones, both generated with atomic clock precision. The difference is that WWV arrived over a 850-mile skywave path and was modulated in amplitude and frequency by the ionosphere. This upper left video that's playing now shows fairly steady amplitude and a frequency that's drifting slowly upwards in frequency. The one on the upper right shows a lot of short-term amplitude flutter and a much quicker upwards frequency drift. And finally, the one on the lower left shows amplitude fluctuations that even include phase reversals, where the envelope amplitude went through 0. Considering the ionosphere as a modulator infers a production of modulation sidebands, which exist as symmetrical frequency excursions about a carrier frequency. This spectrogram in the lower right shows an example of symmetrical frequency excursions. It's very fuzzy, and that fuzz may well be modulation sidebands. Well, pursuant to the idea that the fuzzy appearance might be from sidebands, we ran a specific experiment designed to test that theory. The downconverted carrier was passed through a hard limiter to strip amplitude information off while leaving frequency information intact, just like you would do in a regular FM receiver. This oscilloscope inset on the lower left shows the appearance of the linear before limiting, and then the limited version, where it's essentially constant amplitude. The left spectrogram was made with the linear data, and the one on the right was the limited version. The process of limiting removed a bunch of that fuzz and really sharpened up the frequency track. So it sort of supports the idea that a lot of that fuzz was in fact from AM sidebands. Now, if you measure the time of flight of a radio wave, like from WWV to my receiving station, you might be able to use that to help infer the path length through the ionosphere. And with that knowledge and a geometric analysis, you can infer the number of hops. You can make such a measurement using the per second timing ticks that WWV transmits and the reference that tells you the exact time of launch available from the 1 PPS output of a GPS DO. The timing ticks are 5 milliseconds long. They consist of 5 cycles of a 1 kilohertz tone for WWV and 6 cycles of a 1.2 kilohertz tone for WWVH. I'm going to play an audio recording that gives an example of the per second ticks during the audio time announcement prior to the top of each minute. You'll hear both the female WWVH voice and the WWV male voice that were coming in at the same time. The band was open for both.
At the tone, 12 hours, 2 minutes, coordinated universal time.
The oscilloscope record here shows the appearance of the ticks as displayed on an oscilloscope obtained by getting the audio out of a receiver that was set up to listen in AM mode. This top yellow trace shows the 5 cycle tick from WWV on 5 megahertz here, followed 17 milliseconds later by the 6th cycle tick from the much more distant WWVH in Hawaii. This bottom green trace shows a good copy of WWVH on 10 megahertz, but no copy at all for WWV. So that's what they look like on the air. Now, I had to get a feel for what the times of flight might be like from Colorado to Texas, so I used this really simplified geometric model. It's shown on the left. It predicts the path lengths for 1, 2, and 3 hop modes as a function of virtual height. This height there is simple triangles. It uses a flat earth geometry, perfect wave reflections at the virtual height, and a constant wave speed of c. So the path lengths were computed on a spreadsheet and converted to time of flight and plotted as a function of virtual height from a span of about 100 to 400 kilometers, and are displayed here in this graph on the right. For a ground distance of 1,350 kilometers, reflection heights in the range of 150 to 300 kilometers. The difference in arrival times in the 1 and the 2 and 3 hop modes run from 0.3 to 4 milliseconds. 0.4 milliseconds, 4 milliseconds. The timing tick is 5 milliseconds long, which means that the 2 and the 3 hop pulses are going to come down on top of the 1 hop primary pulse, and they're going to superimpose. This graph also shows that the slopes for 2 and 3 hop modes increase. The different slopes mean that for a given descent rate than virtual height, the multiple hop modes will experience a faster closure rate and incur more Doppler. So this supports the previous supposition. So because the time delays between multiple modes are less than the pulse width, they're going to overlap and they're going to lengthen the pulse by superposition. This top row illustrations show SPI simulations for superposition delays of 1, 2, and 3 milliseconds. The net effect of the overlapping rivals is to lengthen the overall pulse. underneath each of these simulations, an oscilloscope recording showing actual WWV on the air captures showing exactly these situations. So I went looking for them and I found them. Note the first cycle of the primary mode, the very first cycle, and the last cycle of the delayed mode have no overlap. So they're free from superposition distortion. So those are the places you want to measure. You want to measure the time of flight for the primary pulse by referencing the leading edge. And you want to work on the delayed arrivals by referencing the trailing edge because they're clean. You use the rising edge of the GPS DO sync pulse. The 1 PPS sync pulse has the sync for the scope. You have to take into account the time delay through a receiver, which can be significant on a modern DSP radio. It was 4 milliseconds for my 7610, and you also have to use a consistent on-time marker. I used the middle of the first positive half cycle and corrected for the time delay between that and the first part of the pulse. So I acquired data records manually by sitting in front of the radio with the scope and enabling it to trigger on the next available 1 PPS pulse, and recorded about 250 records over a 4-hour period. I plotted them in Excel as a scatter plot. As you can see, they clustered in layers that are consistent with single and multiple hop modes. The negative slope is consistent with descending ionization. Up here, where these higher order modes, they didn't appear until partway through the transition, and this is also consistent with the premise that the high order modes must wait for the propagation to support the required takeoff angle. So these clustered around delays corresponding to 1 hop, and then these are the extra delay time for the multiple hops. These plots on the right is that same data, but with a linear interpolation between the missing points. I only took 250 values over the 4 hours so that I could superimpose a trend line with Excel. On the left is that same time of flight data computed from that geometric model, but it's been turned around, reversed in order so that layer height decreases from left to right to match the lowering height during the dawn transition. And then I took those curves, selected the parts that matched up in both amplitude and slope to where it looked like the data. It's a crude comparison, but it did show a pretty good matchup. These things do compare favorably in slope and in position. And this all happened at a reflection layer height of about 255 kilometers, which turned out to be pretty close to what ray trace simulations predicted. Speaking of ray trace, we ran quite a few of these. Nathaniel Frizzell, W2NAF, provided me with 1 and 2 hop simulations to compare with. So this is a side-by-side, or rather this is an example of the 1 hop data record over here and what Farlap predicted at a time of 1200 UT. And I happen to have a record at 1201 UT. I measured a propagation delay of 4.93 milliseconds. And over here on the Farlap, it was predicting about 5 milliseconds. So they were pretty close. Here's the 2 hop Farlap prediction that Nathaniel provided. The measured 1 and 2 hop modes are both plotted here, and they also agree pretty well with the predictions from Farlap. The ray trace program predicted a 2 hop time of flight of about 6 milliseconds at 1324 Zulu. And I had a data record available at 1329 Zulu, just 5 minutes later, and it produced a 2 hop measurement of 5.67 milliseconds. So those two were not too far off in frequency. This is a 3 hop ray trace simulation made with PropLab Pro that was provided by Carl Lutzelswab, K9LA. The measured 3 hop time of flight compared pretty well for the prediction from this date and time. It predicted 6.46 milliseconds at 1430 Zulu. I had a record at 1444 Zulu that had a measured 3-hop TOF of 6.38. So 6.38 versus 6.46. Okay, there's many times, like in the recording I just played, where the band is open to both WWV in Colorado and WWVH in Hawaii. Because they're on the same frequency, their spectral contributions overlap in the spectrogram. WWV and WWVH alternately transmit standard side tones of 500 and 600 hertz on most minutes of each hour. And these signals are as precise as the carrier. They can be used to separately measure Doppler data if you recover as an upper sideband. WWV uses 500 hertz on even minutes and 600 hertz on odd minutes, and then they trade in the next minutes. So to just track one, you simply have to come up with some sort of a deinterlacing scheme. A lot of ways are possible to do this. I'm going to report an option here that gives you a fully deinterlaced stand that gives you 100% continuous data record for each station on separate outputs and separate spectrograms. To do this, you need 2 receivers, and you have to be able to change frequency every minute so that one receiver continuously listens to WWV while the other one continuously listens to WWVH. So here's an example of the data and the setup. My 7610 has 2 receivers, so it was an ideal platform for this separation experiment. I had to stabilize it with an external GPS DO. So the audio output from main and sub receivers were fed to 2 separate laptops running Spectrum Lab. The main receiver was initially set up over here to translate 500 hertz to the 1000 hertz tone for the analysis program. And the sub receiver was set up to do the same thing for 600 hertz. Both of these moved those tones to 1 kilohertz. And then I accomplished deinterlacing by manually pressing the change button to swap the main and sub. So now this receiver, instead of looking at 500 hertz, is now looking at 600. So it tracked WWV from one to the other. Likewise, this tracked WWVH from one to the other. So their outputs always showed up on the same place on their analysis programs. This was a labor-intensive, manually controlled experiment to just demonstrate the feasibility of the method and make completely separate spectrograms. You could certainly automate it. You could come up with a radio control clock, use that to control a CI5 interface, and have this done for you automatically. So here's what the actual data looks like. These 2 spectrograms show completely separated data streams with WWV on the left and WWV on the right. They show all of the available transmitted data. The missing minutes that are here are those that were intentionally not transmitted by WWV. These short gaps in between the adjacent records, those are the 20-second gaps where the voice announcements happen prior to the top of each minute. I kept the amplitude scale factors the same so that you can tell something about relative amplitude, and that's reflected in trace brightness. Over here, WWVH has got a weaker track than the WWV does. You can clearly see mode splitting over here in WWV, but in WWVH, you had a single mode that was more diffuse. Without this deinterlacing, these 2 spectra would have been superimposed. You'd still see the mode splitting on WWV, but it would be blurred by the presence of these components from Hawaii. And the WWVH data mixed in with here would simply be unrecognizable and lost. So the conclusions are using experimental tools that target specific ionospheric behavior can help you decipher multiple physical processes. The purpose of this paper was just to give example of some of these tools developed for the HamSCI community. These results support at least some of the mode splitting and suggest they may indeed happen from Doppler shifts for multiple hop modes. But the data is a lot more complex than can be accounted for by this one mechanism. Alternate explanations have been proposed and are the subject of future research. So this is very much a work in progress. An automated time of flight collection system and an automated separation system would sure be nice. I'd like to thank Nathaniel Frizzell, W2NAF, Carl Lutzeswab, K9LA, David Kasdan, AD8Y, Bill Laz, NQ6C, and Bill Engelkeef WWVH for their contributions, insights, and great technical discussions. And finally, we'd like to acknowledge support of the project from the NSF grants shown on the bottom of the page. And we'll stand by for questions.
So Steve Serwin is not online to be able to answer questions, and Christina has the next talk, and we'll try to do questions at the end of her talk that also cover Stephen. So moving right along here as soon as I can find. And there's Christina. Good morning. Yes, we're about to start your talk here.
Good morning.
Hello, and thank you for tuning in. My name is Christina Collins from Case Western Reserve University. Last year I gave a talk at DCC entitled The Lion in the Path about the principles and early development of the low-cost personal space weather station and about Doppler measurement. And this year I've decided to stick with the theme and talk about the elephant in the sky, which is not as impressive sounding a title as The Lion in the Path, but I think would be scarier if you came across one in real life. I got the idea for this title from the parable of the blind men and the elephant, which is an Indian folk tale, shows up in a few different places. My favorite version of it is a poem by John Godfrey Saxe that was written in 1872, of which there's an excerpt here. The story is pretty much what it says on the tin. There's a group of blind men, they've never encountered an elephant before, and they try to figure out what it is by feeling the part that's nearest them. So the one who happens to walk up to the leg says, "Ah, this feels like a tree." That's what an elephant is. An elephant is a tree-like object. And the one who feels the ear says, "Nah, an elephant is like a fan," and so forth, and they can't agree. The story is usually used as a metaphor for theological debates, but it can also be used for scientific ones. It came to mind a couple of weeks ago when I was on a telecon with Nathaniel Fursell and Steve Serwin, whose talks preceded mine here in the conference schedule today. And Steve said, WWV has a very steady signal during the day, but it's noisy at night. And I said, what are you talking about? WWV is much more consistent during the night, and it's during the day that it's noisy. But of course, Steve's station is in Texas, and I'm in Cleveland, Ohio. So his ionosphere is different from my ionosphere. We're each looking at a different part of the elephant. I have a couple of sets here of frequency traces that were taken during the Festival of Frequency Measurement on October 1st of last year, of 2019. Each plot shows the frequency variation over a 24-hour UTC day. The y-axis is auto-scaled on these plots, but you'll notice that the magnitude is fairly similar for each set. The top ones are all stations that are on the East Coast, and the bottom ones are all stations on the West Coast. The blue line is the unfiltered frequency estimation data, and the orange line running through it is filtered, and all the stations with green boxes around them, which is to say the one on the top and the three on the bottom, have GPSDOs connected to their receivers. So you start to see some really interesting things once you have these clusters of stations like this that are more or less in agreement. There's at least one group that's agreeing on the tusk and one group that's agreeing on the tail. For those who are watching this after the fact, I want to emphasize that this talk fits in with a series of talks this morning at TAPR DCC concerning the personal space weather station and Doppler measurement. TAPR DCC is one of two meetings where our team every year checks in for the personal space weather station project, the other one being the annual HamSCI workshop in March. I hope you'll join us for that virtually or in person in Scranton, Pennsylvania next year. Last year at TAPR DCC, I talked about the Standard Station Receiver project, showed off this Gen 1 prototype, which is what we're currently working on. Gen 2 is coming up soon, and John and 8OBJ will be giving a talk on that later in the day. I also asked that all of you check in for our special event celebrating the centennial of WWV on the 1st of October. And I have some interesting results from an experiment that we held during that event. One note of terminology, we have elected to call the low-cost personal space weather station the GRAPE. This is for a few reasons. The primary one is that it's easier to say GRAPE than it is to say low-cost personal space weather station or LCPSWS or any such permutation of that. Also because it is a tiny fruit, and people like to name electronics after tiny fruit. We have the Raspberry Pi, we have, of course, the Tangerine, we have Lime SDR, we have the Red Pitaya. The list goes on. I will also note that the magnetometer boards are beginning, because they come in groups of 2, to be referred to as the pair. Also, specific to this device, it does its best work in bunches, and we hope that the data will ferment, as John likes to say, into something quite nice. In the photo here, you see the Gen 1 grape that is collecting data here at my house, and below it is the Gen 0 grape. So a year later, we have some data to play with. We've got a few grape stations that are up and running. We've been doing some long-term data collection, and then we've also got these pilot experiments that I'll be telling you a bit about today. To give you some idea of what the long-term data collection looks like, on the right we have a couple of plots from David 88Y's station. The top one is 5 megahertz traces going from March to June. The one on the bottom is 10 megahertz traces for June into July of this year. Red is frequency, black is frequency, red is amplitude. And then we've also got, again, this experiment with spatial distribution, the Festival of Frequency Measurement for WWV in October, and then the June 2020 Eclipse Festival. And I'll be talking about those and some upcoming experiments. There's an eclipse in December. There's a couple in 2021, and then of course the American eclipses coming up in 2023 and 2024. If you've never made a Doppler measurement before, the tool that we recommend is FLDigi's frequency analysis mode, which is optimized for the frequency measuring test that's run by the ARRL. And this will give you a nice CSV file with an estimation of frequency error and amplitude of your signal throughout the day. So the data that you see that's presented here has been generated using just that in FLDigi, which is a fairly straightforward process. So last year I showed you this slide, inviting everyone to check in for the special event celebrating the centennial of WWV, and also to participate in the Festival of Frequency Measurement, which was to take these Doppler shift measurements for 1 UTC day. We put the protocol out there and said, we'll see what we get. Here's how to make these measurements. And we had a fantastic time celebrating the centennial on site, and knowing that during that time some number of ham radio operators out there in the world were collecting data. And it let us showcase WWV's utility as a scientific resource. So at the end of that, we had 45 participants who collected 5 megahertz data sets that we could use. All of these are available online. And here's the map of stations in the United States. There is one that's not shown here that's in Australia. But we got some good distribution, and what we found is that the amateur community is interested in making these sorts of measurements and in being able to be of assistance in experimentation and in providing scientific data. Here's what that data looks like in a stacked plot sorted by longitude of each station. Each of these plots is 1 UTC day on the x-axis, and the y-axis is estimated frequency error. Once we remove the datasets that have instrumentation errors, which are the ones marked in orange here, and we look at clusters of stations that are near to one another and are seeing similar traces, we start to develop the synthesis of regional perspectives on what WWV's signal looked like in different parts of the country on this particular day. We've been finishing up the analysis on this data set, and we're hoping to have a paper on it out soon. We've faced some fundamental questions in the course of setting up a remote sensing network, like the Personal Space Weather Station network that we're contemplating here. One is, how many stations can we get? Where do the stations have to be? Do we want clusters? Do we want an even distribution? Do we want to go for a grid? Who's going to host them? How many stations can we afford? What kinds of data do we need to be collecting? Should we be collecting frequency data? Should we be collecting audio data? What information do we need about stations that are in a given location, etc.? And once we have that data, how do we analyze it? There's a continuum of analyzing data from a single station, analyzing data from clusters of stations, analyzing data from all of the stations at once, and figuring out how to do an effective data fusion approach works a lot better if you have data that you can actually test it out on. One of the wonderful things about pilot experiments is that they remove a lot of these considerations from the equation. First of all, how many volunteer stations can we get? As many as we can. Where are they going to be? Wherever the volunteers are. We don't need to provide the hardware for these because people are using their own radios. And you're seeing this heterogeneous collection of instrumentation that still is providing pretty good quality data at the end of the day, at least for some of the stations that are out there. But we don't need to worry about that hardware because the amateur community has stepped up and lent it to us. So this lets us do a couple of things. It lets us first focus on certain parts of the process. And also it lets us connect up a toy version of our data pipeline, run things through it, and see what we think. So we really get to focus on the data collection and on the data analysis. I like to think of each station in the Doppler network as filling in a pixel in a display of the ionosphere, and that pixel is at the midpoint between that station and the beacon station. But I want to head off the potential misconception that that pixel is static by showing you a couple of visualizations. I should note the next few slides here are all simulation, not experimental data. I made them with the FARLAP toolkit using the International Reference Ionosphere. Here we have 2D ray traces along the bearing from WWV to Cleveland. So Fort Collins is at the left side of the plot. David 88Y's station is marked around 2,500 kilometers with a red line, and the geographic midpoint between Fort Collins and Cleveland is marked with another red line around 1,250 kilometers. The ionosphere in each of these plots is the same. The color maps are different because I happen to be playing around with color maps that day. The top ray trace is for 2.5 megahertz, then 5 megahertz in the middle, then 10. When you see a pink ray, it's reflecting off the F2 layer and actually hitting the receiver. You'll notice the apogee, the highest point of those rays, doesn't generally occur at the geographic midpoint. It actually moves around quite a lot, which adds another dimension to our problem. Now, if I do the same thing for Steve's station in Texas, we get something quite different. His station is much closer to Fort Collins. His bearing is more north-south, more parallel to the terminator rather than perpendicular to the terminator. And again, ignore the color map. This ray trace is for 5 megahertz, so you want to compare it to the second plot down for the Cleveland station. And you'll see that Steve's not just getting reflections off the F2 layer, he's also getting reflections off the F1 layer in purple and the E layer in blue, which explains why it is that he gets that nice clean signal from WWV during the day. Here's what happens when I ran the 2D simulations like those for all of the stations in the Festival of Frequency Measurement and put them in this map. You can see again, same color scheme. We have blue for E, purple for F1, pink for F2. Not all the stations have a propagation path all the time. Midpoints move around quite a bit. Here's what happens when we break it out by layer and add in the terminator. Stations closer to WWV are getting that E layer propagation during the day. Stations further away are mostly getting F2 propagation at night. Once again, this is a simulation. It's fairly cartoonish compared to the real thing. There's lots of things that are unaccounted for. But depending on where your station is in the United States, it may give you some insight into which part of the elephant you're seeing when you tune in to WWV. Now, many of you will be familiar with the utility of solar eclipses in researching the ionosphere. The wonderful thing about a solar eclipse is that it gives you a period of time where you have some knowledge of solar inputs to the ionosphere beforehand. It's the closest thing you're going to get to a controlled experiment in space. Earlier this year, there was one such event, an annular solar eclipse that covered this nice swath of the Eastern Hemisphere with a very well-positioned time standard station, the Chinese station BPM, marked by that little blue dot. And initially I discussed this idea with Nathaniel last year at DCC, and I dismissed this idea of trying to do anything with this eclipse because I thought, no, it's too soon. But then the quarantine happened, and the global population of bored amateur radio operators spiked, and I became sort of more willing to try things. So around the beginning of June, this experiment ultimately took less than a month of preparation. I decided to give it a shot, and I put out a set of instructions which were based on the ones from the original Festival of Frequency Measurement. Now, there were a couple of adjustments that were very, very helpful. One was that the version of FLDigi that was current last year when we did the original experiment included only timestamps in its CSV files, not date timestamps. So if you had a table, you couldn't just sort it by date time easily. And John N8OBJ wrote a patch to fix this, which W1HKJ, the FLDigi maintainer, was kind enough to integrate into all the more recent versions. So that was a great help. The other big difference was that I collected the data through a Google form rather than having people generate their own data sets and post them into a repository. And I asked for more metadata information at the outset, and I set stricter requirements for the file name conventions. So where the October data took me a month or more to assemble in one place, for this experiment, I had everything pretty nicely collected early on. And, you know, these were improvements that I was able to make because we had already run a pilot experiment. We learned some of these lessons. So we're seeing an evolution here in these data collection processes. I posted the instructions for the experiment first in English, and then I posted a version in Chinese, and I put the word out via ARRL, IARU, various Facebook groups. I was contacted at one point by the member of the Dutch Amateur Radio Press, who was kind enough to translate the instructions into Dutch, so we got this lovely little cloud of stations in the Netherlands. I initially started out just looking for stations in the Eastern Hemisphere, and then just widened the net to whoever wanted to participate. And in the end, we got 50 stations. I got participation on every continent except Antarctica, and met some really lovely people in the process. It's the international cooperation and collaboration side of amateur radio and shortwave listening at its best. I want to share with you one of the really lovely communications that I got from people as I was putting this experiment together. This one in particular is from a ham radio operator in the Netherlands. This was a few days before the experiment. And I like this email because the way that he ends it, he says, "I do not know what we are seeing, the temp of our receiver or changing of ionosphere. Maybe you will laugh at us, but we have fun." I am by no means laughing. I am really impressed with this group because essentially they spontaneously put together their own little Doppler network out of sheer curiosity. There were people who bought time standards for this experiment. There were people who rebuilt their stations for this experiment or went out and bought textbooks on ionospheric physics. People got into it. It was really, really fun to see. But this one in particular I find interesting because what you see here are traces from this operator station. His is in the yellow. And then there was another operator who had two different radios at one place, the red and the green. And they wrote me at one point, and they were like, hey, we have these receivers. They're 5 kilometers away from each other. But they're showing similar traces, very similar traces, but they're not exactly the same. Should we be worried? And of course, the answer is no. No, that's exactly what we're looking for, because even 5 kilometers away, your ionosphere is not the same as your friend's ionosphere. Similar, but not the same. because there are many scales at which you want to be able to examine these things. And if you look at just one of these traces, this is where I think we might have some insight from this as to how we may want to deploy personal space weather stations in the future. Just one of these traces, it's hard to tell. As he says, are you seeing the temperature of your receiver or changes in the ionosphere? Are these things geophysical in nature, or are they a function of your instrumentation? And with one trace, it is hard to tell. But when you have four together like this, it's easy to see that the blue one, which happens to be the receiver that is not frequency stabilized, is the one that is out of whack compared to the others. The others are all pretty well in line, which very much suggests that you're seeing something geophysical in nature. And I think there may be advantage to intentionally deploying receivers in clusters like this one. First, because, again, it makes it a lot easier to look at these and gauge how useful your data probably is, but also because I think that volunteers, ham radio operators, shortwave listeners will get more out of it if they have a little community of people that are all working on this together. And I think that it'll make it easier for them to maintain, because if your station goes down and needs work, you have friends that you can check in with, rely on. If you can't maintain it anymore, you may have somebody that you can hand it off to. So for a scientific approach, and also in the sense that hams thrive on community, I think this cluster approach has some interesting potential. Running a data collection exercise during an eclipse feels a lot like a heist film. You're trying to get this thing of value during a specific time window, and you only get one shot. You're managing this global team of people who have specific skills and distinctive personalities, and you know that at some point your plan is going to run into trouble and you're going to have to improvise. So you try to get as many of the unknowns out of the way as early on as possible. I held a practice run about a week beforehand, had people send me their data from the practice run, and Steve and I reviewed it over the next couple of days, and I let them know if they had any issues with their stations, ground loops, for example, or temperature stability or noise that were indicated in the data before the main experiment. And we found this phenomenon that you see in these plots here, where a lot of the stations in Europe, when you took the frequency plot over a 24-hour UTC day, had this sort of fringe on their frequency analysis data. If you look at the line without the parts where it's getting dragged down, it looks like a pretty reasonable frequency trace for their location. But you have this, all of these little points where the output is jumping down quite significantly. And it turns out that there's a time station, not a time and frequency standard station, but a time station in Italy, whose carrier frequency is just slightly off 10 megahertz. And the frequency estimation algorithm built into FLDigi is just looking for the loudest DFT bin. So when it hears two carrier signals that are about as strong as each other and are slightly off frequency from each other, it jumps between them like a dog with two bones. And obviously, this is a problem for us because WWV and WWVH sing about the same tune at about the same time, and you can often pick up both of them at your station, so you don't know which one you're listening to if you're just looking at the frequency estimation of the carrier. So in the future, we're going to have to do something more clever than just looking at carriers, estimating the frequency, and then looking purely at that frequency estimation data. Because we saw this in the practice run, I had a chance to ask the stations to submit wave files, which were large and difficult to submit, but we managed it through a few different means. And I've also collected IQ data from Kiwi SDRs, thanks to Bill Lyle's NQ6Z and Aidan Monterre KB3UMD for their help with that. And the experiment was still fairly recent, still working on processing, still working on analysis, but we now have this data set of a few different ways of collecting this information, and hopefully some lessons we can implement in future experiments. And I'll let you know what we find. Now, everything we're doing here is in some sense preparation for the 2024 eclipse, for which Cleveland will be in totality, or as David likes to put it, we paid handsomely to ensure that Case would be in totality and MIT would not. Hopefully we'll be able to celebrate this eclipse much as we did the Great American Eclipse of 2017, and hopefully we'll be able to get some good scientific data out of it. But there's no reason that we have to wait to do eclipse science. There are 5 eclipses between now and then, the next one being this December in South America. I'm working on organizing another festival of frequency measurement for that, and updates will be posted to the HamSCI website. In particular, if there's anybody able to help translate the instructions into Spanish or Portuguese, that would be a great help. So if you're a ham radio operator or a shortwave listener, please consider collecting data with us for this event. Even if your station's far away and it doesn't look like it would be well situated, we still might learn something valuable by working through the process. If you'd like to get a look at the data from these and other HamSCI experiments, check out the HamSCI group on the data repository zenodo.org. Also, we have weekly telecons for the Doppler measurements, which are open to all. And the information for those and for the regular HamSCI telecons is on the hamsci.org page under Get Involved. And finally, please consider signing up to help collect data for the December eclipse, the next in this progression of pilot experiments. That's our show. Thanks once again for tuning in, and I look forward to answering any questions anyone may have. And my email is in the lower right-hand corner of this slide for folks who are viewing the presentation after the fact, kd8oxt@case.edu. 7-3 all.
And that brings us to the end of Christina's presentation here. And Christina, are you ready for questions?
Sure thing. I think it might be easiest to answer those in the chat. Oh, thank you, Peter.
Sure, and we think we also have Steve Serwin on the phone as the panelist who shows as the phone number. So we'll ask Steve to unmute, and he can, you and he can try to clean up from the questions left over from his presentation and your own, and then we're going into a 30-minute break, which will be shorter than 30 minutes. So thank you, Christina.
Thank you.
So this question is for Steve. If he's, can you unmute Steve? Are you there?
Can the host possibly unmute Steve? I've been trying to unmute him from my end.
No, he has to unmute himself.
Okay.
I think since he's on a phone, he might have to type *6 to unmute himself.
Oh, I'm afraid he dropped off.
Okay. Maybe we can go with Christina's questions then for now.
Yes, let's deal with Christina's questions, and then at the conclusion, you and Christina can try to handle the questions from Steve's presentation that you can.
Let's see.
Well, so far, Christina, you're getting some kudos, and I don't see any questions just yet.
Yeah, I thought it was an excellent presentation, Christina. It was very good.
Thanks very much, everybody.
Yeah, several kudos to you, Christina. Good job.
David is wondering if there's anyone who can help us set up a station in Des Moines. Those are 2 things we could use help with. We need a station in Des Moines, and I need a Portuguese translator. So we'd like to crowdsource those to the group.
Portuguese station in Des Moines, then you're all set.
Yeah.
So do you need a Portuguese or Brazilian Portuguese?
Thank you. I need Brazilian Portuguese. I do have a Spanish translator, but I need a Brazilian Portuguese translator.
I might know someone who can do that.
That'd be cool.
Yeah.
A couple of
Steve Serwin's calling my phone. I'm gonna take that. So you go.
That's a good idea. He's probably trying to join us.
Maybe Nathaniel can relate the question and get the answer and repeat it, because I don't think he's going to be able to get on with his spotty connection.
So to the attendees, if Nathaniel can make a connection with Steve Serwin on the phone there, he can relay questions. So if you have any questions for Steve Serwin, go ahead and type them into the chat box.
I have a question from YouTube. And let me type that into the chat box for Nathaniel to see.
Who's it for?
It's from Phil Karn over on YouTube.
To whom? Who is the question?
To whom it is to Steve Serwin. And he's asking about AM to PM distortion on WWV at 5, 10, and 15 megahertz. He's noticed this on the transmitters. Does this upset the measurements? And Christina, you may be able to address that also.
Hi, Phil. Yeah, this is something that we've talked about with the station engineers there, but I'm afraid I don't have a good answer on that one offhand.
Looks like Nathaniel has him on the phone.
Yes, I've made contact with Steve. I'm your liaison. I'm your patch between Zoom and here.
So AM to PM distortion on WWV on 5, 10, and 15 megahertz, does it affect the measurements between morning and night propagation? This is like a phone patch before we had phone patches, right?
All right, I do have Steve here, but so just let me know when you're ready for questions. You can keep going with Christina now, or we can put Steve on, whatever works for you guys.
Nathaniel, did you get my question to Steve?
Can you relay it one more time, please?
Yes, it's the AM to PM distortion on WWV transmitters. Does that affect the measurements that you make between morning and night propagation distortion?
Did you get that question, Steve?
No, it was completely muffled.
Okay, the question is, I've noticed significant AM to PM distortion on WWV's 5, 10, and 15 megahertz transmitters. Does this upset the measurements?
I've noticed a lot of pulses with distortion too. Some of them frequency double, some of them null. And on the measurements I took, I simply ignored those. I didn't have any way to handle them any other way, so I simply didn't record them.
Okay, the clarification was amplitude distortion, amplitude modulation to phase modulation, not AM to PM as in time of day.
Would you repeat that, Nathaniel?
Right, was that clarification for me, Scotty?
Yes, that was, well, for Steve also. Phil just typed it to me and said it's, he says, I've noticed significant amplitude modulation to phase modulation distortion on WWV's 5, 10, and 15 megahertz transmitters. Does this upset the measurements?
Yes, that was the question. I read that exact text.
Right, but it's not AM morning, PM night. It's amplitude modulation and phase modulation. I got that wrong.
Yes. So what Steve was saying is that he has also noticed distortion, and he has just been ignoring those measurements for the moment. So the answer is yes. But I think one of the other things Steve has, been working on is that as we've been looking at this data more, he has been figuring out, how to either look at the AM or the FM. So he's trying to untangle how to look at these different effects. And I think he's been doing a pretty good job of that. Steve, what did you mean by closure in your talk?
By what?
Closure?
Oh, closure. When a path between a transmitter and receiver decreases in length.
Okay.
In other words, the distance is closing, getting shorter.
Okay, so by closure, Steve means when the path between a transmitter and receiver is getting shorter in length. And N9NL, who asked the question, said thank you. Are there any other questions for Steve?
Yeah, a comment from Phil Karn on his answer was, he says, so you just average the phase, which takes care of the problem? Is that?
Phil Karn is asking, do you just average the phase to take care of the problem?
The distortion problem?
The distortion problem.
Well, you can't average because the pulse only happens once, and they change from one pulse to the next. So there's nothing to average. You get one pulse, and it's either
distorted or it's not distorted. And the next one may be completely different. So you don't get two pulses in a row that you can average.
Were you able to copy? Were you able to copy that?
Yeah, that came through.
Okay.
May I weigh in here a little? No? May I help answer?
Was there another question?
Are there any more questions?
I think David's trying to say something, but he's a bit muffled.
May I help answering this question? Is that any better? I got audio. I don't have audio.
Okay. You have audio. That's better.
All right. The phase distortion issue is cycle by cycle on the carrier. On the time scale of the modulated audio, this should not be an issue. The phase distortion is minimal to begin with, but it's the basic pathology of a near 100% modulated AM signal.
I'm sorry, I did not understand a word of that. All muffled.
Can you say that one more time, David?
Amplitude modulation. Amplitude modulation near 100% modulation depth has phase distortion on the carrier, but not on the modulated information. So the carrier at 10 megahertz has a bit of phase noise on it. That doesn't change the recovered audio phase relationships.
Right. So, yeah, what David made a comment, David Kasdan made the comment that the phase shifts only affect the carrier measurement, but not the audio measurement.
Okay. What does he mean by phase shifts? This is based on timing, and it's on an AM decoder. So we get this 5-cycle burst, and we're making timing measurements to a specific part on that cycle, which I suppose you could call that phase. And we use the same part every time. And if that part is recognizable, then I simply...
Steve, are you there?
Yes, did you hear that?
We lost the last part.
Oh, well, the measurements were made on taking measurements to specific parts on that 5-cycle.
We lost you again. You were saying this specific part. Yeah, go ahead.
Yes, perhaps we should move on and make sure we have the questions from Christina and move into our break so we can all get just a little respite before charging into Dave Kasdan's talk.
Yeah, there's one question for Christina that she answered in the chat, but maybe you want to answer in voice, Christina?
Thanks, guys. Someone asked, how do you set up a station for the eclipse? And Nathaniel kindly put in the link for the June experiment. I expect that the December experiment, things will be a little bit different, and some of the stuff in David's talk should elucidate that. But there's a sign-up link provided, and I hope that you guys will be able to join us for that eclipse as well.
Oh, David and Christina, we have a volunteer on YouTube that says they can support you with Brazilian Portuguese. How's the best way to contact you?
Brilliant. Email. I put my email address in the YouTube chat because I like to live dangerously.
You put it in the YouTube chat? I don't see that.
Well, it's kd8oxt@case.edu. So.
XT at. Okay, got it. Thank you.
So with that, I guess we're on break until 11 o'clock Eastern time. So that's 21 more minutes. Feel free to use the text chat to chat amongst yourselves. And if any of you attendees want to kind of chat in audio or engage with the panelists, would ask that you raise your hand. I've had one request from N9NL, and I've enabled them and asked them to unmute. So feel free to have a chat on the text window or join the panelists. And we'll turn off that before we restart the presentation in just under 20 minutes at 11 o'clock Eastern time.
So Christina, you said you typed your call sign into the YouTube chat window?
Yes, I got a thanks from the person who had offered, so hopefully I'll hear from them.
Yeah, I didn't see that. Is there more than one chat window open?
I don't think so. The one you were reading out of seems correct.
Okay, so on YouTube, unless you have moderation status on the channel, you will not be able to post hyperlinks and email address links. You can see it yourself, but nobody else can see it.
Oh, weird. Okay.
But he said thanks. So does
yeah, I don't know what that's about, but I can't. I'm looking at it on my screen and I can't see any email addresses.
So did you see my answer that had the email address and there's nothing there?
No, I did not.
Well, maybe he said thanks because you said the email address over the video.
Right.
You heard that.
Yeah, he might have heard that. It's her email address is also hyperlinked from the URL she shared in the Zoom chat for the 2020 Eclipse of Festival frequency.
Right. So we had a question from Roy Gerdig that was, how do you get a copy of the chat? Well, after each day's presentation is concluded and we stop the video for the day, then my computer sits and churns for hours, and it spits out an MP4 file and a saved text chat. And afterwards, we will have the text chats, and they'll eventually also be posted on the TAPR website.
Okay, we had someone on the chat, Kevin on the YouTube chat says there's top chat and live chat. If you select live chat, you'll see the email addresses. So I just posted it again. Yeah, and Christina, that worked with the @ and the dot.
Yeah, sometimes the old ways are the best ways.
Yeah. And I posted it again. You probably didn't see it because, like Jason says, it's blocked.
I'm seeing it now, so you guys must have that setting changed, which is cool. It's not it's not clickable, but it is there.
Okay, and I changed it to live chat, so maybe that's why it works.
Yeah, good deal. Glad it's working glad people are seeing it.
Well, it's that, and Scotty is likely logged in to TAPR Digital, so that would give him moderation ownership powers, and probably that affects it too.
So Phil has some more comments here. I can read them. I think this is directed to Dave New. WWVD does phase modulate its signal with digital data, but that's different from what he was talking about. WWV's 10 and 15 megahertz transmitters use plate modulation, and the RF phase delay through the transmitter varies with the final anode voltage. So on a coherent IQ plot, instead of seeing a line on the plus I axis, you see a banana. The carrier phase varies with the amplitude instead of staying constant. I think he's talked to you about that, Christina, and maybe you too, Dave Kasdan. So did N9NL want to make a comment? You can unmute and talk to us.
Yes, he raised his hand after I asked any attendees who wanted to be able to engage with the panelists during the break to raise their hand, and we'd enable their talk ability for the break and then reset it afterwards. And I invited him to talk and asked him to unmute, but that's where we are.
He said he asked this question during the chat and it was answered.
Okay.
And thank you, Kevin, for that top chat to live chat information.
It's like this is a community thing, and so far the only other person I know who's been a showrunner for a Zoom webinar is Nathaniel, and Zoom has changed somewhat since he did it back in March, and we're just trying to develop methods and techniques so that this stuff can be successful and share the results and what works and what doesn't work with other interested people, so we can just keep iteratively improving these events.
Yeah, that's right, George. We've really seen these virtual workshops and conferences kind of evolve since the pandemic started. And you have a survey that people can fill out, giving their input about this, right?
Yes, we have a survey at the tapr.org website. And there's, of course, the URL is up on the screen that I believe our Steve and 7HPR are showing and is streaming out right now. It's the TAPR-DCC-review survey. And I think you can come and leave multiple comments there. I don't think it's just a one-time thing. Stephen, do you want to comment on that?
Well,
I guess he's taking break time seriously.
Yeah, I guess so. But
Yeah.
I think it'd be really good if people can give their feedback, because one of the questions we've been asking during these presentations is, do people like the pre-recorded formats better or the live formats better? I know at HamSCI we did the presentations live, and that we had to change from an in-person format to a virtual format very quickly. But now we're doing the recorded presentations with the chat. I think there's pros and cons for both formats, so it's be very interesting to see what people have to say about that.
Yeah, and from putting on a show, we also learned a lot from the QSO Today endeavor a month ago, and certainly I think the DX University webinar also used pre-recorded chats, but it was definitely QSO Today that gave us the idea of using Zoom so that somebody, even with a free Zoom account, can just record their own presentation and then create the MP4 file by saving it locally and uploading it. It gives us like 3 separate options. It could be a live stream talk, but still the questions won't happen until the end. It's just too hard to arrange in a format like this. But so it's the recorded presentation lets us stream it consistently because it's already been successfully recorded, and then we can do the live Q&A, and that allows us maybe best bandwidth utilization and more other fallback options. We get the slide decks as PDFs from the presenters as well, so we could play them here and the presenter could talk with them. There are all kinds of options and redundancies available if you collect the right data up front.
That is very true. One nice thing that is, one nice thing with the pre-recorded format like this is that the presenter can actually pay attention to the webinar chat while the presentation is going on. And so I think that's worked out well. I know when I've given live presentations, it's very hard to pay attention to the chat while you're actually talking.
So, this is John. Oh, go ahead, George.
Yeah, so I was going to say, we have a question here from George Schindler. Would it be good to have a separate Zoom for the back-end communications? Well, we're using Slack for the back-end communications, and it's a text medium, and it's totally separate from Zoom. And it's not really possible to have two separate Zoom sessions running on the same device or on two separate devices under the same login. So we've already checked out things like that, and so the determination was we need only one Zoom thing, that's the webinar. We need to use something absolutely not Zoom for redundancy reasons for our back-end communication, and that we're doing. John?
Yeah, just a thought about the recorded versus live from somebody who put together a recording for this. We're using shorter time slots for this virtual conference than we did in person. I think, they're 30-minute versus 45, and we ended up with a lot more speakers. I think, George, we've got 28.
Yeah, something like that.
If you're trying to do short time slots with live presentations, staying on schedule becomes really difficult because it just takes, one or two people to run a little bit long, and you've got problems. By doing the recording, the presenters know what they need to do and can get to the target time, and we know how long their presentations are ahead of time, so we can make sure that there's time for some Q&A and not have things run long. So I think there's actually a relationship between the shorter the time slot, the more useful having it pre-recorded might be.
George, over in the chat, Michael, DK5HH, mentioned that they use BBB in the SDR Academy. And I participated in the SDR Academy and was quite impressed in how well their system worked.
So that's their video system that they used?
I assume so. Michael, are you still on the chat? Can you clarify what BBB stands for? No, Michael's a speaker tomorrow.
Oh, it's a big blue button.
Big blue button?
Okay. Hopefully you can hear me. Well, Big Blue Button is an open source video system which is very famous to universities here in Germany and all over Europe, I think. I don't know where it's coming from. I think it's an American group heading the development of BBB. And well, if it's running in the browser, you can have several tabs, and these tabs could have different sessions. So we used it in the during the SDRIA. It was very nice to have several tabs, and you just change the tab and go to another session.
So this is a way then to have multiple threads in the conference.
Yeah, that is very important. Of course, we used pre-recorded records as well. Well, these videos are played then, but from the starting to the end, we had several sessions by side, and there could be a discussion as you did it as well in YouTube or in the Big Blue Button system. But the discussion in Big Blue Button is just only between the moderator and the presenter. when the presenter is waiting to the end of the video.
So how many threads did you have going at one time?
I think about 3 or 4 threads in the different. You have the presenter before, then the presenter, the next presenter, and well, this was it.
Okay, and then users can switch back
just to finish, every presenter get his own URL. He went it in, and well, he can went in. The others don't have the information about the URL. Only the moderators.
And then to the users, they just appear as tabs on the browser that the users can switch back and forth between at will.
Pardon? Again, please.
So then the users have multiple tabs in their browser, and they can click on them and switch back and forth between the streams at will, and however they want. Is that correct?
No, the users or the audience is viewing on YouTube. The BBB system was only used for the presenters and the moderators.
It was their back channel communication system.
I understand.
We will certainly investigate that for the future. This is all about digital communications, right? Oh, okay. Thank you very much. Now, we're getting close to the end of the break. We have less than 3 minutes. So, Michael, I'm going to put you back to a regular. And David Kasdan will be the next up. We got any? Okay. All kinds of infos coming up in the chat here. So, David, are you pretty prepared for you to be streaming next?
Stream away.
Well, we still have about 2 minutes before we're out. And so you have a 20-minute presentation, and we'll have about a 10, well, just under 21. So we'll have about a 9-minute QA period following David's presentation.
Look, if anybody's still awake after 21 minutes of that talk, then they can ask questions. It's good.
I'll have to be awake. Let's see. Is this your library, David?
Yeah, it's the ham station.
Yeah.
Let's see. I don't think I have too much to show off, really, but this is where I am monitoring CHU on 1.85 megahertz. That's what this transceiver does 24 hours a day. And if you like such things, there's my small plaque arrangement with the mock-up of a ship's radio room clock, including the W and single sideband watch hours.
Yes, we apologize. We know that David's audio is muffled. He's using the microphone in his web camera, hasn't secured his Plantronics headset yet. That's probably coming from Amazon shortly.
Yeah, that's a problem. Sorry.
And with that, we are at the top of the hour, and now introducing. Just
Greetings all. I appreciate you being here for what might not sound like of this conference, frequency estimation. It's true, this is a math topic. This is the underlying math of
I apologize. We seem to have had a hiccup on Zoom, and I'm seeking to recover. Okay. It claims we're live on YouTube. David, do you hear my audio? Shake your head if you do.
Yes, audio is fine.
Okay, I'm going to restart your presentation because it's like when I started it, all of a sudden I got a Zoom crash message. So we'll try this again.
Greetings all. I appreciate you being here for what might not sound like the most scintillatingly fascinating talk of this conference, frequency estimation. It's true, this is a math topic. This is the underlying math of HamSCI's WWV investigations. I will try to make this an entertaining talk with a bit of history, a bit of fun behind it, but yeah, ultimately it's a math talk. Let's see how it goes. I want to thank TAPR. I've been using TAPR stuff, their publications and their products, since the mid-'80s when I ran a packet bulletin board in Michigan. And I want to thank the American Radio Relay League for all of their decades of coaching and publications and running W1AW and all the rest of amateur radio. Got me started in the 60s with this little book, and it's been a fun ride ever since. I want to thank all of my friends and colleagues from the Case Amateur Radio Club and from HamSCI for making it interesting now. And I want to thank the National Institute of Standards and Technology and the staff of WWV and of WW0WWV and of all the world's other national physics laboratories. We have had good friendship and correspondence with them, and they are making it all possible. All right, what's the frequency estimation problem? We do this every day all the time. You listen to speech, you listen to music, you listen to CW signals, you look at a picture and you want to know what the colors are. Frequency estimation is part of the everyday experience of the world. Here's a waterfall. It's turned 90 degrees, but it's still a waterfall of piano music. You can see the attacks and the decays. You can see the frequency slotting of the individual strings on the piano as they're being struck. It's not that much different from what we were doing with WWV monitoring. If you started in CW back in the day, you know what it's like to use a not very selective receiver and try to figure out your signal's sound as it's contaminated with noise, with static, with lightning crashes, and with all the other CW signals out there. It's yet another version of a neurologic frequency estimation problem. I will make an assertion that the statistical problem of frequency estimation might be a part of engineering college statistics. And I think these classes would be more interesting if we all participated in the frequency measuring test. Twice a year, the ARRL runs this. About 120 amateurs enter. This is the nerdiest of the nerdy of amateur radio competition. And I got to tell you, WADU, the Case Amateur Radio Club, we love it. It's amazing how hard your heart can pound during 2 minutes of key down. The FMT itself goes back. Amateurs are supposed to stay within band edges, so you need your equipment calibrated. WNAW used to send standard signals. Then they started asking volunteer amateurs to monitor the bands so that perhaps they could anticipate FCC regulatory actions. It's mostly for fun and scientific interest now because transmitters are so well calibrated. W5CN essentially reproduces WWV in his basement, sends out unknown signals. The contest is maybe akin to penny pitching. Whoever gets the penny closest to the wall gets to scoop up all the other frequencies, does that make sense? And win. Does it on 3 different bands, and the winning scores these days are within 10 millihertz. It's really pretty amazing. The only apparent rule is that you don't bribe the referee. Kind of keeps the referee anonymous, so it's harder than it might be. Otherwise, you bring your equipment and your skills and your experience to this, and may the best frequency measurement win. It's fun. But for HamSCI, the frequency estimation has real significance. The beacons, WWVH, mics in Finland, they launch their signals with very high accuracy and very good stability. But as they bounce off the ionosphere, they get contaminated. The frequency shifts by Doppler shifting, noise gets added, there's multipath interference. HamSCI wants to use these signals of opportunity to read off the electrocardiogram of the ionosphere. What's going on electrically in the ionosphere that can be measured indirectly? Well, we need good measurements for this. They've got to be high resolution and they've got to be fast. They have to have good statistical power. Now, at first blush, estimating frequency doesn't sound that hard. All right, you have a sine wave coming at you. Sine wave is about squiggles. All the information, if it's just a sine wave, is contained in the zero crossings. Every time the signal goes from negative to positive, count. Start a stopwatch, count. At the end of a second, stop counting, report the number. Well, it doesn't sound that hard, but it certainly can be. You're given the signal of single frequency and constant amplitude, but you're also given it contaminated with noise. And in fact, there might be fade. That amplitude might not be that constant. So now, what's the best statistical estimator of the signal's frequency? Well, the earliest version of this was lecture lines, parallel conductor transmission lines that were set up deliberately to have high SWR. You use a light bulb, you measure the distance, the physical distance with a meter stick between SWR peaks, between voltage peaks, and read off the wavelength. All right, if you need to convert that to frequency, you do, but otherwise, you measure the wavelength of the signal. You can do it to about 1% with a system like this, and that's how the original radio regulations were written. Next up was tuned LC circuits. It's just an inductor and a capacitor resonating against each other, and the voltage is measured. You dial it, you have a calibration curve, you can get within about 0.1% this way. All right, part 1,000. The next step was heterodyning receivers. You have an accurate crystal running a local oscillator, and you get to mix it down. Comes out of a speaker, maybe then you can use a tuning fork, which actually is surprisingly accurate. And by ear, with the help of a meter, maybe, you can get about 10 hertz accuracy. So at a megahertz, 10 hertz accuracy on an unknown, that's a part in 10 to the 5th. It's starting to get pretty good. This World War II device was used for a lot of FMTs back in the day, and the official observers all had them. But we've got computers now, and we have NIST. They're running atomic clocks. They disseminate the atomic clocks with GPS-disciplined oscillators. By the way, there's a very cool book on history of crystals. So we should be able to do a whole lot better. How do we do it? All right, here's a signal. This is what comes out of the speaker of your radio. It's a sine wave contaminated with noise. It's maybe a couple of decibels above the noise, so it's got lots of squiggles contaminating it. What's the first thing you do? Well, put it through a bandpass filter. So the blue is the signal, the red is the bandpass version. It looks a whole lot more like a sinusoid, but it's still not a sinusoid. It's contaminated in noise. The underlying math of it then is that you have a sinusoid, a theoretically pristinely perfect sinusoid at one frequency that has an amplitude, some number of volts. It's contaminated by additive white Gaussian noise, uncorrelated noise. All of the information of the sine wave part is contained in the zero crossings. So let's see what we would do with an FM receiver's limiting amplifier. Well, that's a frequency counter. We've all seen and used frequency counters. They're certainly a whole lot better if they have Nixie tubes. We like Nixie tubes. We haven't quite won the FMT yet. Let's take a look. The idea of a frequency counter is that the sine wave gets squared off. The squaring amplifier leaves behind only the zero crossing information. WWV and the NIST come in generating an accurate time base, essentially to run the stopwatch. The time between the rising edge that will control the gate and the falling edge that will stop the signal passing through the gate has to be precise. If you use a GPSDO to run it, you can get it to about 10 to the 12th. All right, you open the gate, you read off squiggles, count them one by one, you close the gate, whatever is left, you display. That's the frequency. It's very comforting to have a digital frequency displayed on a digital display. It must be correct, it's digital. The problem is, noise might create more zero crossings. If you're having a bad day, it might be that those high frequency squiggles or those poorly filtered squiggles of the noise will be right at the zero point and will cause erroneous counts. The second problem is that in 1 second, you only get to count 1 hertz precision. This is an integer counting. So every additional count counts up 1 more hertz. In 1 second gating, there won't be fractional hertz. There won't be fractional zero crossings. It's not good enough for HamSCI. You know something? It's not good enough for Connie either. Well, it is about 1/10 of a part per million error, though. So we have improved on things. We're doing better than the BC221 did. Can you filter it well enough? Can you filter the signal coming out the speaker output of your receiver well enough to use a frequency counter? You're going to need an awfully high Q filter for this if you're doing it at the actual radio frequency. A Q of 1,000,000 is really hard to attain. It's hard to tune. And you want to win. So you're going to have 10-second gating times, 100-second gating times. Connie only goes key down for 2 minutes, and the atmosphere is changing during that time. You won't be able to find the signal fast enough. So maybe this isn't exactly the right approach. Down conversion can help. That's the BC221 approach. If you have a high-quality local oscillator, this is where calibration against NIST or the GPSDO comes in. You have your incoming signal, you mix it down. Now you have an audio level signal, say a low IF, maybe a kilohertz. And you still can use a frequency counter. It still has the time frequency trade-off. 1 second only gives you 1 hertz precision. We still haven't won the FMT. This is a really odd graphic I found somewhere. Who's selling ham radio jigsaw puzzles? Okay. The FLDigi analysis mode, FLDigi, more or less does this. It does a time domain computation where you set the cursor, it generates a signal at the cursor, your best guess, mixes the incoming signal down, and measures accumulated phase error during the measuring time. Well, actually, that's a way of statistically improving on the inverse gating time precision problem. Not a bad approach. You can get 10th of a hertz, 100th of a hertz this way. It turns out not to behave well in noise. This is what the screen looks like. This is WWV's carrier, and we've set the cursor there. So we have our receiver set a kilohertz down. We've set the cursor at 1 kilohertz. So the estimation is 10 megahertz. And we're measuring now our error against the zero line. It's not a bad way to do it. WADDU has nearly won the FMT this way. But you want to get rid of as much of the noise as you can. You want your estimator to be zero biased. and you want it to be close to the Rao-Kramer lower bound, to have as low variance, as low standard deviation as you can possibly get. Well, let's go to the frequency domain methods then. Now, you collect samples for a second. You don't take a sample and just do something with it. You collect them and compare all of the seconds against each other. That's the notion of a discrete Fourier transform. It may be that in a discrete Fourier transform, in this example, we have 3 signals in the frequency window. Each is a sine wave of same amplitude, of constant frequency. They get transformed in the frequency domain. They've had noise added to them. So you have noise under here, but you do have 3 distinct spikes. So maybe you can just read off the digital frequency bins that have the most amplitude, read off the spikes, and report those as your estimated frequency. Actually, you got the same problem that you did with the frequency counter. The bins are too wide. If you've read 1 second of data, you only have 1 hertz wide bins. You need more math. The DFT filters are more or less a digital inner ear. Each one has its own Q. Frequency resolution is Q. Well, okay, you have 1 hertz wide bins, but you haven't discarded all of the information on either side of the bins the way that the FM detector's limiting amplifier did. You did a whole pile of linear math, and you've retained a lot of information. So what can we do with it? Steve Serwin collected data for a longer period of time in an overlap way. So he had a running averaging system of frequency with higher resolution. You get time smudging, but you do get frequency detail. Let's take a look at what he did. At night, time's advancing up. At night, the ionosphere looked unstable. Day broke, there was a Doppler shift up. In fact, there was a second Doppler shift, maybe from another forming layer of the ionosphere. As those layers were coming down and the path was shortening, there's high frequency shift. As the path shortening slows, both of these converge back on the stable frequency at 10 megahertz. And finally, as the ionosphere stabilizes during the day, the 10 megahertz signal becomes stable, and you get back to reading only 1 frequency. You get 10 hertz, you get 1/10 of a hertz resolution for 10-second windows. In overlapping them, you get a running average in short time intervals, but it's still a running average. It's the average of frequencies over the interval, and you don't get to do very fine frequency resolution and very fine time resolution simultaneously. There's another way of doing it, though. You don't have to use linear approaches. A statistical method that uses nonlinear approaches is a data compression in the same sense that taking the average of a bunch of data is a data compression. Taking the standard deviation of a bunch of data gives you more information than just the average, but it's still compressed data. You haven't retained all of the separate information from all of the separate data points. So let's take a look at a quick example of this. We have 1 second of sampling here. So we have 1 hertz wide bins. A 50 hertz signal gets exactly in the center of a bin. That's the blue here. It's the spike, my pointer is red, I'm sorry, but the blue spike here has all of the energy contained within it. The blues below it and above it are all exactly 0. The purple spike from frequency just a tick above it, it's a lower spike because it has spilled some of its energy into higher frequencies and into lower frequencies. You notice that the distribution here isn't symmetric. Well, okay, of course it's not symmetric because you have a 50.1, it's just into the next bin. Well, zoom in on this. Let's do an interpolation. Let's do a parabolic best fit from the point below, the point above, and the point itself. That's an exact parabola that will give a peak just above the peak that's here, just above in frequency to the peak that's here. And in fact, if there's no noise and everything is done mathematically perfectly, the peak of the parabola will in fact be at 50.1 hertz. If there's noise, then these will be bobbling around. So you may want to include more points and do a least squares best fit parabola, read off the peak of it to approximate the 50.1. Now it's a statistical problem. your least squares best fit might not be exactly 50.1. It will have non-zero variance, but it may be pretty close, and really that's not a bad starting point for all of this, drawing a spline. The new FLDIGI FMT mode, the frequency measurement test mode, to which we give credit for a lot of code work by David Friess, W1HKJ, the maintainer of FLDIGI, it uses a different nonlinear approach. The parabolic spline is not bad, but this one, it's not what he uses. He's now using this work by Tsui and Reisenfeld, two Australian electrical engineers, who use a mathematically rather involved approach that's not within the scope of this talk, but we'll see to it that it's uploaded to the TAPR reservoir of papers, repository of papers, and you'll be able to read it on your own. It uses a nonlinear and recursive estimation method that turns out to give frequency, phase, and amplitude all in the same measurement, and demonstrably it gives it very close to the statistical theoretical best possible estimation. It hits what's called the Rao-Kramer lower bound within only a few estimations, few recursions, and is the current version of this. Here is the new FLDIGI screen. I don't have data on this one, but this is what the screen looks like. And in fact, with this, people are now winning the FMTs at precisions somewhere between a millihertz and 10 millihertz. With modern equipment, it's really quite a substantial improvement using modern math. Okay, how are you going to estimate your frequency? Make sure you're asking the right question. Is your signal high amplitude, noise-free, stable, perfect, everything else? You know something, just use a frequency counter. If you're at a test bench and you want to measure the frequency of your 2-meter handheld, a well-calibrated frequency counter is what you want. If you're trying to measure a signal in noise, it's a different story. Probably discrete Fourier transform techniques with long time averaging will be what you're after. They will give resolution, your signal stable. If your signal is noisy, it has only short-term stability, but it's single frequency within those short terms. A nonlinear DFT technique might be good, and maybe there's a way of using several of these simultaneously across the spectrum. That's what the newest FMT does. But you know something? You can't have it all the time. You're going to have some trade-off of frequency precision and localization of transient effects in time. That's the HamSCI WWV problem, and it's not a solved problem. If you want to join us, if you're the mathematician here, you get to work, do some research with us, write a paper on it, be famous. You get to do next year's ARRL TAPR HamSCI program. There's a lot of background work to this, and we'll guide you through it. One of my professors, Jerry Lefman, used to say, more data, more noise. It's the stuff of physical measurements outside of the math realm itself. The wisdom of Bob Leskovic, who is a senior member of WADDU, everything must be done first. We're all still doing our homework here. I want to close by saying outside my office here where I'm recording this, at night the crickets are singing. The crickets are singing, summer's over. Everyone stay healthy as the nights get longer and you're more indoors. Stay healthy in the days of the virus. Enjoy this conference, and I hope we all get to meet in person next year. I hope the days of the virus are over soon. Take care, everyone. Thank you for your kind audience, and if there are any questions, I'll be around for a bit.
And with that, David?
So David, there was some questions, some discussion on the chat room about how you pick 30 megahertz IF. Was there anything more you wanted to add to that? You have to unmute.
I need to unmute, thank you. It's the old guy's problem. I'm not sure that we did choose 30 megahertz IF. Did I misstate something there? This is a low IF receiver. It's not direct conversion, but it's low IF. So in the fully simplified form that we are using in the grape receiver, the local oscillator is 1 kilohertz offset from the signal that we wish to evaluate, and the low IF then is 1 kilohertz. Does that answer the question? Oh, from radar days, 30 megahertz was the standard. I'm sorry. I have seen that. I don't know why 30 megahertz was chosen. I'm riffing through my head of when I took the radar endorsement on my commercial radio telegraph license test. I think 30 or 60. I'm not sure there is a single standard for radar IF. Let's do some checking. I'm sorry, I don't have a better answer. Okay, as I said, it's a math topic. At least some people actually stayed awake through it, and I appreciate that. It's an interesting topic. All right, as long as we have a minute then and nobody's asking. One of the interesting parts of the problem, if you have identified multiple frequency streaks, the way that Steve Serwin did, you can't do it by hand. You have to automate. You have to have a statistical test that reports back, is there unimodal data or are the data multimodal? And it turns out that's a nasty problem in hypothesis testing statistics. That's why I said in the last couple of slides, this is a remarkably unsolved problem, and I hope that some better mathematicians out there can give us a hand. I think the basic approach is going to be using that last algorithm that I mentioned, the Sui and Rosenfeld recursive algorithm, but having alongside it a sample by sample examination of multimodality and bring multiple decoding channels when the multimodality is detected. But I want to say again, this is a nasty statistical problem. It's not an enormous statistical literature, the examination of multimodality in a data set. And even some of the hardcore statistics authors say often it's better to use your intuition here.
Yeah, so David, there's another question on which windowing function you used in the FFT.
Oh, yeah, that's a good question. Sui and Rosenfeld did specify one, and I don't remember if it was a hemming or a raised cosine. I'm not sure that it makes a great deal of difference. Once you have chosen a window other than square, in all honesty, there isn't that much frequency leakage one side to the other. And what is the possible frequency error in a root WWV signal? If what you mean is the ground wave, how accurate they are launching the signal, they're pretty much guaranteeing these days a part in 10 to the 12th. When the F2 atomic fountain is working and they have a proper microwave signal from the time and frequency division of NIST from Boulder, I think on an excellent day they can hit 10 to the 16th. CHU Canada is guaranteeing 10 to the 12th, and I think that's what most of the national standards transmitters are doing. And the FMT is great fun. I encourage you to give it a try. The official ARRL one is twice a year, but there is a pre-FMT, a practice one that is run at least once a month, and there's a practice one that's being run twice a week, Tuesday and Thursday evenings. Sign up for the FM Nuts mailing list on Google Groups if you want to participate in that. A surprisingly active group. Who knew?
Yeah, you got several kudos on YouTube. They're very good talk.
I appreciate that. Thank you, everyone. And I hope this is of interest. I hope you want to join us. I've already gotten several HamSCI new membership requests that I've signed off on during the conference, especially from Christina's talk.
Well, very good. And we also have John Gibbons, N8OBJ, with his mic active, ready to start his presentation in about a half a minute.
Yes, this is John Gibbons. I'll be giving an overview and status update of the low-cost personal space weather station, which we've nicknamed the Grape, for the personal space weather station project. This is as of September 2020. And for starters, let's take a look at where we're at. Right now, I have in the field approximately 7 of these units collecting data actively. This is what we call the Grape Gen 1. The dotted box is the actual receiver. The internal, external, and antenna input comes in on the left side over here. Comes into a input protection and second order bandpass filter, which you select with a jumper to either be a 2.5, 5, or 10 megahertz. And we feed that signal directly into a SA612 mixer for the low IF mixing. On top here is a GPS amplified antenna going into the Leo Bodnar GPS DO, whose frequency has been set to 1 kilohertz below the selected beacon, so we get a upper sideband frequency of 1 kilohertz. And then the mixer mixes those two signals and spits out a 1 kilohertz signal, which then we bandpass, audio gain it up by 22 dB, do some more filtering on it, and then spit it out to a USB dongle that's plugged into our Raspberry Pi that is running a modified version of FL-Digi, which I modified to accept a 1-second sampling and saving of the frequency estimation for the frequency being received on the audio input from the USB stick. On the end of the day, the 0 UTC, the file gets closed and opens a new one. It also, if gets accidentally shut down, it will keep saving in addition to and adding on to the file rather than deleting it and starting over. This is a schematic of the Gen 1. The antenna input is here. We have a transient voltage suppressor diode here. It clips at plus or minus 5 volts and presents a 2-puff load to the antenna, which is completely swamped out by this 2200 puff right here, so you never see it. I also have a 1K resistor for a DC path to ground, and this is done intentionally to, it slightly widens up the Q, but its main purpose is to bleed off any static charge built up on, if you have just a wire antenna hanging in the tree, air scrubbing over it will scrub off the electrons and build up a static charge, which will attract lightning. And so for that reason, that's there to help lead that off and protect the station from attracting lightning hits. We then go into the resonant filter here and you select the inductor set for either 2.5, 5, or 10 megahertz. And then that output feeds directly into the SA612 mixer. The top portion, or the bottom portion here, is the Leo Bodnar input, which we bring in. It's set to an 8 mil current drive. We divide it down here with this 100 ohm, 400 ohm resistor, AC couple it into the mixer, which then mixes the two signals and spits out the 1 kilohertz signal. We then have a high pass filter it here. We have a low pass filter built in here, and we have another high pass filter built in here, which then filters it. We have a gain of 22 dB here, and then that goes through the output to the out connector to the USB dongle, which then goes on the Raspberry Pi, which is then read by FL-Digi running on the Raspberry Pi for the frequency estimation. This here is a picture of the Gen 1 receiver board. It's not very big, as you can probably tell. I think it's roughly, I think I want to say 1 inch by 1.25 inches, 1.5 inches, something like that. But that's a 1N4000 diode, and these are SMA connectors, and these are 0805 resistors, so you get an idea of the scale of it. The antenna signal comes in here. There's the transient voltage suppressor diode there, the 1K loading resistor. This is the LC filter, which then gets coupled into the SA612 mixer, whose local oscillator frequency comes from the Leo Bodnar input jack here. It's divided down with these two resistor AC couple and goes straight into the reference pin. The output of the mixer goes through the filter here. This is the linear audio op amp that gives us the 22 dB gain. We output filter it here and then spit it out here, and this goes to the mic input of a USB dongle that's running on the Raspberry Pi. The picture below is the Leo Bodnar GPS DO that we're using. You program it from the Raspberry Pi, and I have created scripts to be able to set up the frequencies for all of the 7 beacon frequencies we're after, which is WWV 2.5, 5, 10, 15, 20, and 25 if you want. It also does the 3.33, 7.85, and 14.67 megahertz CHU frequencies. So you can actually reference all of those, and the FLDigi auto recognizes the frequency and sets the appropriate label based on the beacon you're listening to at the beginning and the start of each day. This is the Raspberry Pi 4B that we're running the newer ones on. The previous ones are running on 3B with 4 gig of memory, I believe. Or is it, no, the 3B's got 1 gig, and the Raspberry Pi 4Bs are 4 gigs, sorry. But one thing I should note is the 4Bs require heat sinking. It's not an option. If you don't, the CPU will throttle itself back during boot. It gets hot that quick. So I've put these copper heat sinks on here, and also you'll notice there's a fan on there that helps keep it down, and we can keep the CPU down to about 40 to 42 C without the fan. If you take the fan out, it gets up to in the upper 50s or the low 60 C. So it does make a significant difference. The lower left corner here is my little 5 volt 3 amp switch mode power supply, which takes its input in from a DC voltage of 9 to 16 volts DC in and creates the 5 volts that runs the Raspberry Pi. I also tap off 12 volts that goes off to the receiver, which then divides it down to 5 volts to run the SA612 and the linear op amp. You can see here, this is the USB dongle for the audio input, and this jack here is running off to run and power the Leo Bodnar GPS-DO. Generation 2 that's on the design board right now is basically Gen 1 on steroids. Each one of these is one of the receiver boards that I was just showing you the schematic for, so we're replicating that 4 times. And we're going to fix the filters on these to 2.5, 5, 10, and 15 megahertz, which will also give us overlap nicely for the 3.33, 7.85, and 14.67 megahertz CHU beacon frequencies. We are intending to create our own GPS-DO. There will be a GPS on board to allow us to get time synchronization accurately, and I'm actually setting the OS up to be a Stratum 1 time reference using the GPS as its standard. So that will be incorporating, it's built into the operating system with a few mods. It's very nice to do, so we'll have an accurate timestamp. We're also planning on using the 1 PPS to, actually it runs the OS 1 second tick input for running the Stratum 1 clock. We're also going to use that for creating the GPS-DO reference, which I'm hoping to get from the clock group, and implementing that on this board to create a reference frequency that's a TBD that will feed most likely 4 PLL synthesizers. I might be able to double up on these, but they're only 96 cents a piece, so I'm not too worried about if I have to separate them out or not. But that will feed these frequency synthesizers, which then will feed the mixer directly for the mixing for the beacon frequency you're after. We'll have to have an antenna buffer this time because the filters are LCs and they look like a short when they're off frequency. So the other 3 frequencies will be shorting out the one you're looking at. So we need to buffer these and separate them out, which is what this antenna buffer block is for. This is my 5 volt 3 amp switch mode power supply. I'm planning on having a DC wall wart input voltage to it, as well as a separate 12 volt battery backup for power fail retention of the unit, so we don't have to worry about that. And the interface to the Raspberry Pi will have the local temperature sensor, a 4-channel A to D to be able to read these channels at most likely an 8 kilohertz, either a 16 or 24-bit depth A to D sampling. We haven't figured that out yet, or actually I haven't figured that out yet. I haven't figured out where we're going with that. Most likely the A to D will be running on a SPI interface, since we've pretty much used and utilized the I2C bus already. The Raspberry Pi will be running the local temp sensor and the remote interface to the remote temperature sensor and the remote magnetometer for the part of the science experiment, as well as the PLL synthesizers, I believe, are on I2C, but they're only getting set when you change frequency. So their bandwidth utilization of the I2C bus will be rather low. So that's basically where we're at. If there's any questions or problems, please contact me, but that should do it.
That was great, John. Thank you very much.
You're welcome.
Yeah. So we do have some questions for you.
Okay, fire away.
All right. So Peter Laws asks, how well will these work in the presence of a 100-watt class amateur HF station?
Depends on how far off the frequency you're operating at. I actually have an HF station at home here. It's a Flex 6500 running 100 watts. And if you're in the same band within the queue of the receiver, it does affect it. But if you're out of the band, it doesn't seem to cause too much trouble. But it's depending on your antenna setup and how close you're transmitting and how close the antennas are. I mean, there's a lot of variables, but chances are it's, like I said, it's going to be on a case-by-case basis, but it can be made to work. But if you're running 40 meters at 7 megahertz and you're listening to CHU on 7.85, you're going to clobber it. So,
but a lot of times, so CHU, those frequencies are very close to the amateur radio bands.
Correct.
Generally. But WWV, they're a little bit farther apart. You're typically listening to like 2.5, 5, 10 megahertz, right?
Correct.
So unless you're operating, say, like 60 meters or you're operating 30 meters, you're probably not going to interfere with this device too much, right?
I have not seen an interference problem, but I have been operating a lot either. So, but I'm not expecting a problem.
Right. So I think this is something we're going to keep learning about as we, deploy some of these, more of these prototypes, and we'll want to have people be able to test them in, in a more difficult RF environment. I know Tim Duffy has told us he'd be willing to help us out. So maybe he would put one over at his station during a major contest, and we could see how it performs after K3LR operates one of the major contests. But I think another place we can look for for inspiration on this is, I think another place we can look for an inspiration on this is maybe like people who run RBN nodes, because a lot of those people want to do RBN skimming or spotting so that they can, basically have a spotting network for their home station. And so they've worked out different mechanisms for being able to have their RBN receiver work simultaneously with their HF transmitter. So you might see a scenario where like you either have some sort of interlock between the personal space weather station receive antenna to prevent damage. So if you're transmitting, it would turn off like an amplifier if you had an active antenna. And then we just wouldn't get personal space weather station data during that time. But I think that's fine. I think one of the things we do need to work out throughout this project, and it's going to be a little bit of a process, is figuring out how we really do make these, work within someone's amateur radio station so that, people can feel free that they can operate, the way they want to operate on the amateur radio and still have the PSWS, work at the same time and not have them interfere with each other. And
that's the challenge of a low-cost station, is being able to handle those kinds of overloads and interference at a low cost. So it's kind of a mutually exclusive. I don't have the capability of doing, the roofing filters that the 7851 does for $12,000 a pop.
Right.
I don't have that kind of budget. So
no, and so then that's a good point too, because at that point you say, okay, if you're running the low-cost personal space weather station, these are some of the compromises you might make. And,
right.
And what we would say is, like, if someone's worried about that, you say, okay, well, when you're operating the when you want to go operate DX or talk on HF, maybe it does interfere with the data that the PSWS is collecting a little bit, but that's not a bad thing. We can just, filter that data or not use it. And when you're not, when you're sleeping, when you're not using your ham station, it'll be collecting good data, and that'll be fine.
Yeah. if anybody is interested and we have the time, I've got access to 3 stations running currently, right? Raspberry Pi grapes running at 2.5, 5, and 10 in real time if people are interested in seeing them. But let's answer some more questions first.
Yeah, so I think another question is, and this question keeps coming up, how much antenna will each unit need? So what are you running for antennas right now? Because I know you have about 9 stations, 9 of these low-cost personal space weather stations running right now. What different antennas are you guys using for that?
Right now, my 2.5 and 5 megahertz is running off of a single off-center fed Wyndham, 80-meter Wyndham, which is 135 feet long. It's 30 feet up in the air, so it's horizontally polarized. I'm actually feeding that antenna input into 2 grapes without a buffer, which by my definition should have problems, but it seems to be working just fine. And for my 10 megahertz station, I'm running that off my Gap Titan, which is a vertically polarized antenna. But the intention is to be able to run this off a simple piece of wire strung up in a tree, which the Wyndham pretty much simulates, but it's about a 135-foot piece of wire.
Mm-hmm. So, I think one of the nice things about focusing on the frequency measurements, measuring varying frequency, is that it really, does not put many restrictions on the type of antenna when you're just measuring narrowband frequency, because we're not worried about, calibrating the amplitude per se. We're not worried about exactly what angle of arrival you're looking at. All you want to do is make sure that you can receive the signal in question, which is typically WWV or WWVH. So then, you can go from as simple as a random wire that you throw out the window to a K3LR class station. And then you are able to, as long as you can receive the signal with decent quality, you're able to contribute good measurements.
I know that I think it's KB3UMD in Pennsylvania has a wire strung in his basement that he's running his Pi on, and he's doing work. So he's got a little bit more noise on it, but he's picking up the station, which I find kind of amazing. But it's the intent is to make it simple and cheap, because if you're going to have a lot of people doing it, you can't be expecting them to spend thousands of dollars on the expensive antenna system and towers and all that kind of stuff. My intent is you get a cannonball or a tennis ball cannon, you shoot a wire up into a tree, you tie it into the valve, and you're done. So that's the intent of the philosophy of the personal low-cost station.
Yeah, I think that's a really good philosophy, because one of the things I think we're trying to do is we're trying to make these, high-quality FMT frequency measurement test type of measurements, which typically it takes a lot of skill. Like we saw Steve Serwin's presentation earlier, where he had these beautiful, spectral displays showing the different modes that are being received. And then we had Dave Kasdan, 88Y's talk, where he was talking about, again, different techniques for both understanding and measuring and understanding the frequency characteristics of the signals you're receiving. And these sorts of things are, it takes a lot of skill to do this, doesn't it?
Yeah.
And essentially what you're doing is you're trying to take those skills and in a way automate it so that, we can make those sorts of measurements. We can make it more accessible to people who don't necessarily have that level of skill or equipment, but this would give them the opportunity to make those types of measurements and contribute high quality measurements to the project.
The biggest compromise, or the biggest cost adder that we put in that we found to be essential for making really good measurements, is the GPSDO. That's where we've put a lot of the money into. The receiver itself, the chip is, the receiver and the whole thing is probably less than $10 of parts. Mm-hmm. Getting an accurate frequency standard to make the, the 0.1 or the 0.01 hertz measurements day in and day out is where we need to put the money. So that's
really the heart of this, right?
That's the heart of this whole thing. Yeah. And I'm looking forward to working with John Ackerman about getting his discipline oscillator into my design so we can get a cheap version, because I know we can buy the GPS unit even from Adafruit, has it for like $30.
Right.
And that spits out the one PPS signal, which, to answer another question I saw going by in the chat window, I am bringing the one PPS in on multiple pins, GPIO pins on the Raspberry Pi, because the OS grabs one for the Stratum 1 clock. And I'm bringing a separate one in that I can grab for my data collection engine to know when to take the sample. Mm-hmm. So you have access to it. And I've actually, on the design, I've actually coming on 3 different pins. And it'll allow you to do whatever you want with the 3rd pin, which will probably be for the magnetometer data too. So there's a lot of stuff going on.
Yeah, there really is a lot going on.
But it's intended to be as flexible as it possibly can.
Yes.
But that's the challenge, is to make something that works really well for really cheap. And usually they're mutually exclusive.
Yeah, it is a real challenge. But I think even the ones that you've developed so far, these initial prototypes, I think we've gotten some very interesting results from them.
Yes, we've learned a lot from the frequency analysis that Steve did, that having a single top bin frequency estimation works fine during the day, but during the transitions, when we have the ionosphere changing, we need to be able to measure the multiple frequency paths that pop up for a half an hour.
Yeah.
We're working on that. The personal space weather station I'm designing will support any new software that allows you to measure that stuff, because it's really data processing once I've captured the 1 kilohertz tone coming in that you're looking at. So that allows us to have this be a work in progress and still use the existing hardware, both for the station that I have running now and the new one that I have coming out, which will do 4 stations simultaneously. So that's the intent.
Yeah, and it's really important to get that frequency diversity, because not simply because you hear different frequencies at different times of day, which is often true, but it's also incredibly important to get that frequency diversity across CHF band, because those different frequencies are going to be taking different paths through the ionosphere. So for instance, one frequency might be refracting off of the E layer, one might be refracting off of the F layer. And let's say, I've looked at some of Steve Serwin's data, and, in one track, you might see traveling atmospheric disturbances on one frequency, but not in another. And that may be able to tell you, what's happening at one height in the ionosphere versus another. So,
yeah, what I'm sharing here is one of the GRAPE stations currently running at 2.5 megahertz. And if I click that, this is a typical fingerprint for the 2.5 megahertz signal. If I go back a couple of days, you can see it varies a bit from day to day, depending on what's going on. But you get a general idea what the fingerprint looks like. And this is for 2.5, where you have a very, very abrupt, this is a good 50 dB drop in signal. If I go here and I look at 5 megahertz, this is a station running now at 5 megahertz. Pop that up, you'll see that it's similar, but this drop off here is much more gradual. And it's very much, during the daytime, you've got that. These are probably really good because you see the Doppler shift as the ionosphere forms a layer and drops the distance, you see the shift up. And then at night, when the thing dissolves, you see the Doppler shift down. So this is a fingerprint of 5 megahertz. And interestingly enough, when I pop up 10 megahertz, which right now I am receiving, this is real time, it's a completely different fingerprint. It's gone during, or there during the night, but gone during the day. It's kind of an inverse. But these are typical plots for 10 megahertz. So even from 2.5 to 5 to 10, the fingerprint of what you see during the day is completely different. And this changes with, well, we have the different storms going on. There are all kinds of different effects due to solar flares, to it just, like I say, it's space science, and that's what the whole intention of this is. And I didn't realize how much was going on and how complicated it was, but there's a lot to be learned here.
Yeah, we go in. I know I certainly went going into many things in life naively, and we learn a lot, right?
You realize how much you don't know.
Yeah.
I don't know a lot about this.
And we continue to learn.
Yes.
I think some of the other questions, well, a couple more things on antennas.
Okay.
Yeah, people keep asking about the antennas for the personal space weather station. And I think, the jury's still out on a lot of this. And there's a couple of lines of thought here. Certainly with the personal space weather station, we're saying that any antenna that you can use you're able to receive the incoming signal, I think is something that's of value. So, whether you're using an active, a smaller like active magnetic loop or active, receive whip, DX Engineering has a few nice products of that, or using a random wire or using, something much more elaborate. I think those can all be very helpful. We're also, for the Tangerine personal space weather station, we're still evaluating, different, we want to say recommended antennas. We might, with the Tangerine, one of the things we might be interested in is sampling 2 different channels simultaneously using orthogonally polarized antennas. So you could measure Faraday rotation in extraordinary and ordinary modes and things like that. And so the exact design for that, hasn't been totally worked out yet. Tom N5 EG is working on one possible design for an active mag loop. So he's presented that at some of the both TAPR and HamSCI telecons in the past. And Zach Lefke, KJ4QLP at Virginia Tech, he's working on a design that he's going to present tomorrow as well. And so I think at the end of the day, we're probably going to have, with the personal space weather station, maybe 2 or 3 recommended designs. But one of the things we have to remember with citizen science too is there's only going to be so much control we have over, what people are contributing, because the bottom line is if you set up a personal space weather station as a ham, you have a lot of control over how you want to do the thing, how you want to do this, and what you have access to. So I think there's one of the things that I think we will be doing in the personal space weather station, I know we'll be doing, is we're going to ask people to keep track of what type of antenna they have connected and maybe what its characteristics are. So really the metadata we collect on this project is very important for helping us to understand, what's going on. And hopefully that will lead to good measurements. Let's see, maybe you can help answer this question. The other question that keeps coming up from people is, when can I buy one? How do I get one of these? What do you want to say to that, John?
Well, so far I've hand assembled all of the great generation 1s. The intent is for generation 2s to have it vendor made.
Yeah.
That's probably going to be coming out, I'm guessing, in the next couple of months. It depends on the GPS DO, if I can get that design working quickly. Or I have to talk to John, and I'm not sure where he is at on that. We could revert back to using Leo Bodnar GPS DO initially until that comes out. But that adds $140 to the cost in single quantity. In bigger quantities, we can probably drop the cost down to $110, $120, but still that's breaking my price point for the low cost station. So to answer your question, I don't know. It's basically, it's coming, but it's not ready yet.
Right. And I think the way the development is working is, like you said, you showed schematics and drawings for the generation 2, which is what we want to be able to scale up to production quantities. But I think, for people who are asking what's the best way to get involved, it's to go to hamsci.org, click the Get Involved tab, go to tangerinesdr.com, get involved. If you participate in the telecons, if you participate in the listservs, that gives you a voice at the table. And and then we are, like you said, John, he is hand assembling these prototypes right now, and so we really only have like a few small prototypes at the moment, and we start distributing them to core members of the team who've been contributing. And then we also look for certain other, key locations for various reasons, like they're looking for Des Moines, Iowa. All right, it looks like we are getting over to the end of this session, so I'm going to hand it back over to George. Thank you very much, John. Any OBJ?
7 threes from my basement. Take care.
Back to net.
And while George is queuing up the next talk, so we'd like to make an introduction to Bill Enkel, AB4EJ, University of Alabama, and his talk title is the Personal Space Weather Station Control Software and Database. And Bill, are you online?
Bill is queued up and ready to go. His talk is ready.
Okay, and Bill, are you online?
Yes, I'm here.
Okay, great. So keep an eye in the chat window. If folks have questions for Bill, he can answer them as the presentation is going forward.
Personal space weather station network that it connects into. I'll talk about the control software and database and design and the status of all of that. Here's an overview of the presentation. First, I'll tell you briefly about what the Personal Space Weather Station network will be. And I'll talk about how the Tangerine SDR will work within this network, and talk in quite some detail about how our progress is going so far. The goal of the project is to create a crowdsourced ionospheric observation system. We want to build a network of receivers that can observe the ionosphere by watching Doppler shift in WWV and other stable signals, plus other analysis as well, such as signal-to-noise ratio. This will be done at individual stations and then upload to a central host. What will this network be? Well, this network is organized by a group of universities and research facilities. We hope to have several hundred and maybe even thousands of software-defined radios scattered across the globe in shacks, schools, universities, so on. Each will include a low-cost yet powerful single-board computer with a data collection system. There are two versions of this, the Tangerine SDR and the great ultra-low-cost version, which is being developed by Case Western Reserve University. All these will be tied together into a network for doing data analysis for science objectives, as well as we plan to let each station to be a personal propagation monitor. Here's what we'll be able to do. We believe we'll be able to do high resolution of observations of geomagnetics, the ionosphere, and other near-Earth space environment, so that we can improve our understanding of RF propagation and improve forecasting. We want to understand what happens during solar-caused radio blackouts, what to expect. We want to provide hams with their own local propagation information, and to advance scientific understanding of the ionosphere and magnetosphere. Some kinds of discoveries we think could come out of this project. We want to discover more about the causes of a range of so far poorly understood phenomena like traveling ionospheric disturbances. It seems when certain things happen, like a coronal mass ejection coming from the sun, it rings the ionosphere like a bell, creating ionospheric waves. There are other things that move the ionosphere around. It's in constant motion, such as what we call gravity waves that's caused by tides moving through the ionosphere. This is not to be confused with gravitational waves caused by collisions of black holes. This project is not studying those. There are other interesting things that occur, long delayed echoes, sporadic E, ionospheric movements that occur that are linked to a whole range of things, tsunamis, upper level lows, volcanic eruptions, storms, all kinds of things that result in energy transfer between the troposphere and the ionosphere. And we hope to improve the accuracy of ionospheric models used by NASA. Let's talk about how a station actually works. If you observe the carrier frequency of WWV, you will see that it changes due to Doppler shift as the ionosphere moves around. This occurs very clearly when the sun goes up and down, and when an eclipse comes through the area. The range of these movements is in the order of plus or minus 0.5 to 1.5 hertz. But you can see this clearly with a stable enough receiver and a GPS-disciplined oscillator. By using two orthogonal loop antennas, you will be able to study polarization as well. All these other things that move the ionosphere around, we will find these and characterize these to understand them better. Now let's talk about the network, a 20,000-foot view. The network consists of all these different systems, the tangerines and grapes, that are tied via the internet into a database system that will first run at the University of Alabama. And in further phases, we plan to make that database available other places. We're starting out studying North America, but users in other locations are also welcome, and we hope to spread this worldwide eventually. Let's talk about the logical architecture of the personal space weather system. Now, on the left, you see the Tangerine software-defined radio in that orange box. That is the Tangerine itself, including the data engine and local host, which I'll talk a little bit more about later. Some local sensors, such as a magnetometer, can also be added in order to study the magnetic environment at your location. These tie together through the internet into the space weather network. This over here is a network which will start initially at UA and then be rolled out to other locations as possible. What's in the Tangerine SDR itself? There are 2 ports for antennas, and then, well, let's talk about first the overall view. There's 2 parts, a data engine, which collects data from off the air, and then a local host, which is a small board computer used to collect that data, package it, and upload it. This data engine includes an A to D converter and a field programmable gate array to do signal processing, to do the filtering and other activities you need to do to prepare the data to upload. The data then is collected. It moves through a 3-port gigabit switch into the central, that is the local host. And the local host is tied by internet up to the central control system. Today, we're using the Odroid N2 4GB RAM single board computer. We hope to make this work on the newest high-end version of the Raspberry Pi as well. The hardware design status, a status report on that is given by Scotty in a separate presentation, so I won't go into a whole lot of detail on this. The magnetometer has been designed and built. Version 1 is now being tested by comparison to research grade magnetometers. The data engine and radio modules for collecting the data are in final design, and also the final, the GPS-DO, the GPS disciplined oscillator for the clock is in design. Now, the software that runs on the single board computer, that's what we're looking at here. It consists of 2 parts. You see, we use a web-based user interface. That is what I call a web controller. That's written in Python. It runs Flask and Flask WT forms. We hope to make this system such that you can configure it using a user interface rather than having to go in and edit configuration files and do other engineering work on the system. Those files will be there and you can edit them if you want by hand, but we hope to be able to do that completely through the user interface to make this thing user-friendly so that it's quite usable by schools. Now the system, you've got a thing over here, a module called main control. That's written in C. That's in order to be able to have enough performance to handle the high-speed data coming from the data engine. That is able to decode the FT8 and whisper signals. It's able to store data to a local ring buffer, and if we plan to interface it to GNU radio. And typically the way it works is the user will click a button to turn the system on. This will pass, this web controller will pass that command to the main controller, which will then trigger the data engine to start working, and then spawn off a sub-process to do the recording, the frequency analysis, and your local propagation decoding. Data collection, we think we could be able to monitor up to 16 band segments at a time. It may be more or less than that. We have to test that to determine system capacity. We foresee 4 kinds of data collection that we're planning to support. First, the snapshotter. That's a once per minute waterfall snapshot. That's a conversion of data from time domain into frequency domain, and once per minute upshot, that is snapshot upload. That is good for cases of low internet bandwidth because this is not a great deal of data. Second option is a ring buffer. That's continuous local storage for 24 hours, then upload on request from central control. You'll be able to set a throttle on that so that it doesn't necessarily monopolize your entire internet connection if you have DSL. Then Firehose, there are two submodes of Firehose. Continuous transfer to a local supercomputer is one. Basically, in this case, the small board computer basically turns the data engine on and then gets out of the way, and the data engine just puts everything it can collect out on the data on the network and is picked up by a local supercomputer. Another option is Firehose. This is an intermediate level of bandwidth. Firehose to a remote server, be able to send it to your central control system with throttling is available there as well. And propagation monitoring, decoding of FT8 and Whisper on up to 8 bands each. Again, the total capacity on that is yet to be determined. Handling of collected data. As I said before, the data goes on request from the ring buffer up to your central control system. Snapshotter, same thing. You can just store this locally and play with it locally if you wish. Local propagation, we're also going to support uploading of spots to PSK Reporter and WhisperNet. And the Firehose goes either to a local supercomputer or in remote mode is throttled up to the central control system. As far as the central control system, it's very similar to the SatNOGS network. You have a data cross-reference and user account cross-reference, and then the data itself, the spectrum data, is stored as files, not as tables. The system is going to be based on Django, Celery, Rabbit, MQ, and use a Maria database as a database. Very similar to the way SatNOGS works. You're familiar with that. Here's how you use this network. First, you build your Tangerine system, get it working locally. We'll provide some test routines that allow you to verify that your system has been plugged together and configured correctly and is working. Then using your browser, connect to the central control system, sign up for a free account. Get a security token from the central and paste it into the Tangerine web interface. That will identify your Tangerine to the central control system. Again, this works almost identical to the way the SatNOG system works. Then you start collecting data. You can also turn on local propagation analysis at the same time. Data analysis, we're still discussing what analysis we're going to do on that, so I don't have a lot of detail to give you on what analysis we're going to do with this data. That's going to be designed in conjunction with our science partners. Here's an example of what some of this data looks like. Before I had anything working on the Tangerine prototype, I collected this data using a flex radio and use a spectrum lab. This is 4.999 megahertz. That is, we have set the radio to 4.99 megahertz, and then you have a 1 kilohertz carrier tone. You can see as the sun rises here, the frequency of WWV seems to shift, and then it's after about 15 minutes, it splits into layers, and this layer then disappears. We see a little jog here. What was that? Was that a minor solar flare? We don't know exactly what all these things are. You can very often figure out what they are by correlating this with satellite data. So that's an example. Here's a second example. I actually took this data with the prototype Tangerine running with the flex radio simulating the data engine. I'll talk a little bit more about that later. But again, you can see some things that happen. First, we see we've got this one starts in the evening. So first we see the sunset occurring where the frequency drops a bit as the ionosphere moves up. Then we see little jogs here and there. Some of these things that occur in the middle of the night, we don't understand yet what they are. Perhaps there's interaction of the ionosphere with the magnetosphere of the Earth. And then finally, you can see out here at sunrise, the D layer absorption occurs and lose 4.999 megahertz, you see how the strength of the signal drops off. But we can still collect some good data on what's happened to the frequency. So this is just an analysis of just the frequency using FFT signal peak detection. The top is the frequency spectrum of that sample. Here is the Tangerine prototype. It consists of two parts. First of all, a simulator, which I wrote. It connects to a Flex Radio 6600 to pick up IQ data of the DAX IQ, and it simulates the Tangerine data engine. It outputs data the same way the data engine would, using original data coming from the Flex. That then is then picked up by a second system here. This consists of an Odroid N2 and a Western Digital Purple series a hard drive. The purpose of that is to use a video surveillance type of disk drive so it can survive the large number of reads and writes necessary to do the ring buffer function. The system over here, there's a couple of controls. You can start monitoring FT8, and it's got an output over here which allows you to monitor everything that is going on. It shows that FT8 is going to start in 13 seconds here. It has to start right at the top of a minute. And we can, at the same time, we can start data collection on our ring buffer. And we see we've got the hard drive flashing there. So we've got both FT8 and a ring buffer running at the same time. So this is the prototype Tangerine, which is going to be developed for the software to go on the local host. Looking a little bit more closely at the software interface, the user interface for the Tangerine local host, you can see that it's a web-based system, and the idea here is that all configurations should be able to be done just using this interface, so that you don't have to do editing of configuration files. Those configuration files are there in case you do want to edit them by hand, but we want to try and avoid that. Here is where we can go and set up the number of channels we want to run and the frequencies of each. Here we can see how we can go in and set up the FT8. Whisper is still under development. I don't have anything I can display on that yet. And the idea here is that it should be possible to do all configurations and without having to do any engineering work. The system here also allows you to set throttling of upload data, depending on how much upload bandwidth you have. You can also put in a number of call signs, and I'll also be adding grid squares to this so that you can get notification when a certain signal is heard, a certain that is a certain call sign or grid. Notification will go through email, which you can also configure to send you a text message in case you'd like to get a text message. You don't have to sit in the shack all the time to watch for a particular station. At least on Whisper and FT8, when they come on, you'll get a notification that they are there. We may add other features to this, but this is where it is today. So that's our user interface. So let's talk about the status. I'm not going to go into a lot of detail on this, but you see we're moving right along in making progress in getting the Tangerine working. We've got many of the modes already working, and we have FT8 decode and upload working. I'm working on Whisper right now. The design of the central control system and database is just getting started. That's being done by our computer science department. And this is something that made me very happy. I was able to run the FT8 data collector for a while and upload spots. So here you see spots collected and displayed on PSK Reporter. So that made me very happy to get that working. finally, why would anybody participate in such a project? You can be part of new science and compete for wallpaper. The personal space weather station can provide ongoing propagation monitoring your location with multiband FT8 and Whisper, and actually be a part of this interesting new project. So I'll throw open the board for any questions and answers, and then we'll cover those now.
Thank you so much, Bill. That's great.
I do see a question out there. Does a Tangerine use a Linux OS like the Raspberry Pi? Yes, it uses the set whatever flavor of Linux is pre-installed on the Odroid N2, which is Ubuntu, I think. Yeah. The question is, where does Grape fit into this? Well, my presentation focuses on the Tangerine. We are talking with Case Western Reserve about taking and providing a flavor of the simulator that will talk to the Grape, so that you can use the same web interface to control the system, and then data from the Grape will be picked up by the simulator, pushed into the local host, and then uploaded to Central. So we hope to get those interoperable to work the same way. So let's see. The PSWS software is on GitHub, although I will have to say it's pretty immature right now. There's a lot of features that haven't yet been implemented. It still has the occasional bug here and there that I have to work out. So we're 9 months into a 3-year project, so there's still a lot I have to do. The coverage of unit testing of the software routines in the personal space weather station software has very minimal coverage right now. I hope to get unit testing to be able to cover most of the functionality of the Tangerine. But it's out there on GitHub now, but buyer beware. It's, it takes a lot of tinkering to make it work right now. Here's a question. The ring buffer can be used to record collected data locally. That capability is to be included in the final solution. Oh yeah, absolutely. The way it's supposed to work is whoever wants to participate in the project is encouraged to run a ring buffer. And we encourage you to do this on something like what I have implemented, a Western Digital Purple Series hard drive, rather than writing it to the virtual disk that's a part of the Odroid, because you will wear out, you'll actually literally wear out your solid state drive if you do this kind of read and write functionality. And the idea is that the Tangerine is going to have a heartbeat where it checks with central control every minute or two. If one of the science users had said, oh, we want to get some data. So for example, a science user, a super user, has observed there has been a solar flare or coronal mass ejection, they'll be able to put in a request. And then the next time all the Tangerines do a heartbeat, they'll get a data request from Central that gives the time frame. So for example, okay, we had a solar flare, give us the 30 minutes of data before that and the 30 minutes after a certain time so you can see what led up to it. And then the Tangerine will begin packaging and uploading that to the central host. All that's working. I've got that working and tested. I'm testing it with a virtual machine at home. So we'll have to see how well this works when you go run it across the actual public internet. So let's see what other, are these stations expected to run 24/7? Well, that's best. If you want to be a full participant in all of this, we'd love for you to do that. I mean, there'll be a Tangerine data engine up and running, and the local host connected to your local internet. I don't know that these really draw that much electricity. I mean, anyway, I think it's best if you can have it running all the time. Let's see, what other questions do we? Does anybody else have any? I've tried to answer. You go ahead.
I have a question. Is what was the data rate for the ring buffer?
The data rate for the ring buffer. Right now I'm doing that based on what the Flex Radio default speed is, 48,000 samples per second. That is a single channel, 48,000 samples per second, using IQ samples that are each the 32-bit floating point. So that simulates, we've been talking about using 8 kilohertz wide sample rates per WWV station. So 48,000 samples per second is a simulation of the data rates we'll run if we run 6 simultaneous 8 kilosample per second subchannels. And I'm able to run that. And by the way, I got Whisper working now and Whisper uploading. So right now I'm running the system with that simulated in other words, 48 kilosamples per second, as well as 2 FT8 channels and 1 Whisper channel. That's all I can run with a Flex 6600 because it only supports 4 slices. If I had a 6700, I could test it with 8 slices. But anyway, I'm not trying to make the Flex the be-all and end-all of everything right now because it's just a stand-in until we have the data engine, the Tangerine hardware. What minimum local data rate is needed for uploading to UA? That is going to have to be determined. I have played around with my own AT&T DSL, and it seems to be able to upload at about 1.7 megabits. And also on the data, by the way, we're recording this data in digital RF format, which is the MIT Haystack flavor. And I found out it runs just fine if I use a compression level setting of 1, which is the minimal compression setting. But because of the nature of the data, it still cuts the data size by about 70%. So you can run a lot of data. So I see a question about the 384 kbytes per second uncompressed. So if you take that and multiply it by 0.3, you get about what I'm running. But a lot of this is going to have to be determined experimentally. And since I don't yet have the central host software is just in first design, so I don't have the ability to upload to it yet. I can only do it with a local virtual machine that I'm running in my own local network. Expected time scale. No, what can somebody amplify the question? The expected time scale. What does that mean? If I had to shut down my Tangerine for a period, do I have to tell someone I did this? Well, the standard configuration is that the Tangerine is going to heartbeat to the central control system every minute or 2. That's configurable. It works like sat-navs. If your heartbeat goes away, we know your station is offline. And then when your heartbeat comes back, we know that you're back online. And, this is a volunteer project. Just do the best you can. If you can keep it running all the time, That's fantastic. If you have to take it offline from time to time, that's expected too. Oh, when is this ready for first rollout is really the question. We're planning to have this system ready to roll out prior to the, I believe there's an eclipse in 2024 that somebody can Nathaniel's online. Tell me when is our rollout?
Yeah, so 2023 there's an annular solar eclipse. So we'd like to be ready for that.
Yeah.
I think one thing, so this project, it's a 3-year project that ends December 31st, 2022. So our goals for the end of that period, we have to prove to the NSF that we have a working prototype system. So that's basically what we've promised to the NSF. So basically by the end of 2022, we should have something that, you know, we can really show does something well. And I think we're well on our way to that schedule. So I certainly hope to have you know, more wide scale deployment of these things before that date. But you know, that's what we absolutely have to do.
Somebody asked a question about the ring buffer. We recommend that you configure the ring buffer to save 24 hours worth of data. The system will work fine doing that. We're finding that the choke point is upload speed. Again, we're going to have to determine that experimentally, but with throttling, we hope to set it up. So, I mean, if central control asks for 2 hours worth of data and it takes 10 hours to upload that, okay, just as long as we don't request too much.
Yeah.
You know, we're out of time here, so.
Yeah, I think we can go and keep talking about some of this during the break. So why don't we turn it over to George for the break, and then you know, we can keep chatting about things once he puts up the break slide. So go ahead, George.
Oh, thank you very much. But I would much rather that Steve N7HPR took over so that I can concentrate on running as much as possible.
Oh, sure.
Steve, do you have that break slide ready, or any comments?
I do. And for everyone, we're going to segue into the break. However, you know, feel free to continue chatting, and especially for Nathaniel and Bill, if they want to hang around and continue answering questions, that's good as well. So I'm going to put up the break slide, but continue the conversation.
Right, and I see at least one attendee with their hand raised. I bet they want to talk during the break, so I'll just enable them. So
when you guys got a moment, I have some questions left over, I think, from John and at OBJ's talk, if he's still on.
Yes, I'm here.
So I guess we're free for all here, right, George?
Yeah, and I see
you got it.
So attendee KF5 IDY Kilo Foxtrot 5 India Delta Yankee, you have the ability to talk now, so you can just click on mute and join the conversation. And anyone else who's an attendee that might want to do so, you can just raise your hand and we can give you the ability to talk and join the conversation.
So John, let me get these quick questions over with because they're kind of lingering that I didn't get answered. The 1 pulse per second, you are feeding it into a GPIO, right? I think you answered that question.
That is correct.
What is the frequency of the I2C bus was another question.
That's really being limited by the Tangerine design. I think it's going to be either 100 kilohertz or 400 kilohertz. Actually, Scotty, you can answer that better than I can.
Probably 100 kilohertz, I think, is the answer. So.
Okay, 100 kilohertz.
Yeah, and then the question was, will you be able to use Odroid C2, C4s, N2s, other single board computers in place of the Raspberry Pi if you so desire for the grape?
Being that it's written in C and in Python, it should be transferable to either operating system for Linux. So I would say that should be doable. It's intended. has not been tested yet, but I don't see any limitations that would prevent that.
Yeah, and I think Nathaniel pointed this out on the to chat on the YouTube channel, was that we'll have SD card images probably for the boards that we support, but if you want to use one of your boards that you select, you're going to kind of be on your own in figuring out the vagaries of whatever OS that board runs.
Yeah, for anybody who spins their own, the biggest thing they can add to it is the GPS discipline oscillator, because that brings you up 4 orders of magnitude in terms of frequency accuracy, and that's, we're looking for half hertz shifts on a 10 megahertz or 15 megahertz signal. So you need that kind of accuracy, and a standard quartz crystal will get you in the 10 to the minus 6, 10 to the minus 7, and we're looking for something that's closer to 10 to the minus 11 or 10 to the minus 12. So you understand why we're pushing on that.
Hence the GPSDO.
Exactly.
Yeah.
So it doesn't matter if your rig is quote unquote rock solid for ham radio applications. You can copy FT8 and Whisper and stuff like that all day long, but they don't have to be within 0.01 hertz to be still rock solid. But for this application, you do need that. You got to have a GPSDO or an atomic standard.
Did you have a comment, Nathaniel?
Yeah, I wanted to address some of the questions that were coming up regarding the length of the ring buffer and how much data you should be storing and sending to different places.
Okay, I just have 1 or 2 quickie questions for John as a joke. I think they want to know what your power bill is. and the last one, oh, sorry, go ahead if you got an answer.
For the 3 GPS or the 3 Raspberry Pis and whatnot, with the switch mode power supply, all total 3 of them only pull about an amp at 12 volts. I'm spending about 12 watts per hour.
Okay, so a couple
doesn't add up to much.
So last question, this might be for Nathaniel also, is there been any interest in WWVB data collection?
Yes, I think there absolutely is. Well, there's certainly interest in VLF, and so I think there will be. I don't have all the details right now, but I think there will be.
Yeah. Oh, this is John. WWVB has an interesting challenge because we used to be able to track the carrier at 60 kilohertz and we actually use it as a very stable frequency source. But about 10 years ago, the modulation was modified to add a BPSK signal on top of the carrier. And the result of that is that a carrier tracking receiver no longer works. So some folks have done a little bit of work on ways to take advantage of that. But at the moment, we're lacking hardware that's really capable of doing what we could have done with WWVB several years ago. But the modulation has complicated that a bit.
Yeah, I just I brought on Bill Lyles here as a panelist. If he's able to say something, he might be able to say some things about that. WWVB as well. But anyway, going back to the compression issue, or not the compression, the data rate issue, I think that and how much you should save in the ring buffer, I think that could actually be a bit of an open question too, because, depending on what your science target is, you could be running in the radio in a different mode. And over time, we're trying to design this. People keep asking me, well, what do you want to measure? What do you want to study? And what we're trying to do is we're trying to design a platform that can be changed for studying many different things. So that answer can change over time. So for instance, if we want to develop one particular mode that the Tangerine SDR is going to emulate what the low-cost personal space weather station is. And the idea there is that if we want to run a specific campaign and get as much uniform data as possible, we should be able to flip a switch and get all of the, we should be able to hopefully double the size of our network of getting uniform data by just emulating our lowest common denominator, which is low-cost personal space weather station. In that case, the low-cost personal space weather station data rate is likely going to be much lower than what the Tangerine is capable of. So that one might be able to record, 4 slices at 8 kilohertz of bandwidth each. So then you might not need to be sending back as much data to the central control as if you're running a different mode, which is really taking advantage of wideband, some that requires wideband. So like my postdoc dev, he's looking at how can you look at wideband ionosons and use that to study the ionosphere. And that would probably require a higher amount of bandwidth. So depending on the mode and how things are being run, that could change the system. I think though, in terms of the ring buffer, I think my original thought was we would try to record basically as much of the bandwidth to disk as possible, and then be able to bring it back to central control. But I think we can also look at that on a mode by mode basis.
The speed of the single board computer at some point starts to become a gating factor too. You do have the option, I guess, of getting a high-end desktop, installing Ubuntu on that, and running your, instead of your single board computer. Why not put a couple $1,000 high-end desktop on there, and wow, you can collect some data, because if you have gigabit switches or faster. Because DataEngine, the Tangerine DataEngine can spit out a lot of data. And Scotty can address that in more detail about the theoretical high end on that. But
we do have a question on what size the drive should be, and what kind of longevity you can expect versus an SSD versus a mechanical drive. I think you talked a bit about that, about overloading it and burning it out, but
that is something we're going to have to determine experimentally. We haven't had enough time to do enough testing really to be able to determine that at this point. But as far as the size of a hard drive, a couple terabytes you can get for less than $100 in the Western Digital Purple series. So, and how will that compare to a solid state drive? We don't know that yet. So.
Yeah, the 1 terabyte solid state drives are a lot more expensive than that, but the problem is it's doing constant remapping to do write leveling in the drive, and they only have 80 or 100,000 writes per cell, and as you mentioned previously, you will kill the drive.
Yeah, a physical spinning hard drive actually has more longevity when you have very high read-write cycles.
And I've actually killed a couple SSD cards on the Raspberry Pi, depending on what series you buy. Some of them are really lousy. So you have to be careful with that too. Cheap is not always better.
Jonathan Dormany asks, Bill, what would be fast enough for the drive?
For a hard drive?
Yeah, the data drive.
Well, most hard drives that I have seen, even the cheap ones, will support in the tens of megabytes per second write speeds. And the gating factor in this is probably going to be the speed of whatever device you're using as the local host. There's a lot of questions here that we're only now just starting to think about.
Isn't there a limitation on overall number of writes to the drive?
More so with SSD than spinning magnetics. So I'd ask, is there any kind of data drive technologies that do and don't work? For controller bus, is SATA technology going to be sufficient? Something more exotic like M.2 or things like that?
Well, it depends on your objectives. If what you're going to do is watch WWV on 5 or 6 bands, you don't need a lot of capacity for that, because you're looking at a pretty narrow bandwidth, and you can just save the data that's a few hertz around your carrier frequency. You don't have to save these big wide bandwidths. But now, as Nathaniel said, there can be other experiments that the science community feels a need to run where a much wider bandwidth is needed, and maybe a small board computer, a single board computer, may not even be adequate. It may be that you have to get a high-end desktop with a nice RAID 5 high-end storage system that runs ultra fast with caching and everything. We don't know that yet.
I can say that from my standpoint, when we first started running the grapes, we were using the Raspberry Pi 3Bs with 1 gig of memory, and we were running out of memory issues, that we went to the 4B with 4 gig of RAM, and that solved the problems, because the operating system doesn't know how to shuffle things, and we were running into memory things and causing the Pis to crash. So right now our standard unit is going to be the 4B, probably with 4 gig of memory.
But bear in mind that is not storing, that's not a ring buffer either, though. That's memory for the computer to run with. But go ahead, Nathan.
Yeah, N9NL is asking, what I'm asking is, 1, is the ring buffer mode the most data you are expecting users to acquire and store? And 2, is that no more than 10 gigabytes per day compressed, so 33 gigabytes uncompressed? And 3, what is the maximum amount of data you expect to be uploaded to the central database?
I don't know that we have any expectations on that, really. That the limitation there is going to be the speed of your internet connection.
Yeah, I think one of the big differences between, again, this and like some other projects is, you know, we're kind of relying on volunteer networks, and so it's what people can and or want to bring to the table. So if you only have a 3 megabit DSL connection, we're going to have a way that we say, okay, these are the settings we recommend you use, and we have to have a way that, you know, when you hook it up, it doesn't swamp your entire internet connection. And conversely, you know, if you have someone who's really fortunate and has a gigabit fiber running to their house and they want to send us, you know, full, you know, as much data as the thing can pipe out, we want to be able to accommodate that also. So really, it's a matter of us kind of building into the software for that. What I see right now, I do see, I foresee a situation where you have, like Bill said, a purple Western Digital class hard drive, something that's really designed for like high read write longevity. That's in, say, the somewhere in the 2 to 10 terabyte range of capacity. So I would say that's probably what we're anticipating for the ring buffer. And then I could also see a situation where we'd say, okay, let's say we know there's an eclipse coming and we want to have a campaign where we get full data for that eclipse. We might tell people, okay, save the data for the entire day to your ring buffer, keep it there, and then upload it to us gradually. And we don't care if it takes, 30 seconds or if it takes, 2 months for you to get us all the data. We want it for that one particular day, and we don't care about what happens before or after it. Conversely, we're going to want to have a mode where we say, okay, we can leave this mode running continuously, and this is a sustainable sort of thing. So we want to accommodate both scenarios. Does that sound reasonable, Bill?
Yeah, that's basically what I had in mind, yeah.
Yeah, and I think the other thing that's tricky too is right now we're still talking, very theoretically, because we don't actually have Tangerine SDR hardware yet, and we're not actually, messing with the the data that's actually going to come from the system. We don't really have it in a box. So right now what Bill is working with is he's working with his Flex radio and using that as a data source and doing the testing like that in the simulation. But that's still going to be very different from when he actually has a real Tangerine SDR and actually really gets to, put the system together and see, okay, where are the actual bottlenecks, and with whatever, version of single board computer is available on that particular day when we actually get to that point. So
yeah, I think it'll be possible, I think, to when we have all the final hardware, for you to set settings on this thing that the thing actually can't do. It's like, okay, yeah, give me 8 channels of wide bandwidth, and then turn on 8 channels of FT8 and 8 channels of Whisper. The system's just going to choke. So, of course, faster and better single board computers come out all the time. Even since we started working on this project, the Odroid N2 version 2 came out, which is considerably faster than the existing Odroid. So we're just going to have to see. I mean, when we roll this thing out in 2 years, whenever it is, there's probably going to be another, that's time for 2 more generations of single board computer.
I look forward to burning
easily.
out hard drives. I look forward to burning out hard drives. It'll be fun.
Even within the development of the grape, the 3B is what I started on. Then we jumped over to the 4 when it came out. We'll probably have the 5 or the 6 before we actually do the final dissemination.
Yeah, that was one of the reasons why someone said, well, why don't you use an FPGA on the Tangerine that has an onboard dual core ARM and run Linux on the data engine? And I'm going like, well, the reason is because it has a minimum of $100 to the cost of the data engine, and I can buy a Raspberry Pi for $35. I can buy an Odroid for $60. And in 2 years, like you said, John, what will I be able to buy for $60 to $100? A lot more, probably.
And the FPGA can only be clocked internally to probably something under 1 gigahertz, and we're already over that with 4. So, yeah, you're not going to get the performance of the bandwidth or the peripherals within the FPGA to do that.
Well, you can get to 1.5 gigahertz dual core ARM, but the core is not the latest core. Right. And once you design that part in, you're stuck with that core. And so it just makes way more sense to use an external single board computer and then couple to it.
And choose a good common denominator computer like the Raspberry Pi Current when you're doing things. And for something at the other end, you can choose what? Mac OS, Windows 10, a stable Linux distribution, and eventually people will likely fill in things in between with things like NVIDIA Nanos and things like that.
Yeah, and one of the comments on YouTube that was that over 30 million Raspberry Pis have been shipped as of last December. So that gives you
a common denominator.
Pretty good base for you, right? A de facto standard, I think, is the right answer.
Yeah.
So, and the reason we went to the N2 on the Tangerine was just because of performance. And I think Bill can attest to that because you've seen a lot better performance on that than on a simple Raspberry Pi, right, Bill?
I'm sorry, repeat the question, Scotty.
You've seen a lot better performance on the N2 than on a common Raspberry Pi, right? Like a 3B.
Well, I haven't gemmed the software to run on a Raspberry yet, so I don't have a comparison between the Odroid and what the Raspberry will do. I'm planning on porting over the software to get it to run on the Raspberry Pi 4. That's what I'm planning to do. See how hard that is. It might be a walk in the park. I don't know. I haven't tried it yet. I've been focusing on building out the functionality of the Odroid N2 and say, okay, we're essentially feature complete. Now we'll try and do some of these other things like doing capacity measurements and porting to other systems. Yeah. I mean, one thing we're definitely not planning on doing in this phase is to port the whole thing to run under Windows. That's too much. I mean, I can tell you how you could do that install VMware, install Ubuntu in a virtual machine, and then
no. You don't have to do that. You can just use you can just use the built-in Bash shell under Windows 10 and run the Linux app direct.
No, haven't you heard Windows has a Linux scripting
Scotty, yeah, it has a Bash shell. It runs Ubuntu Linux stuff just fine. Yep. I've run GNU Radio Companion and everything there is in the native Ubuntu distribution.
Well, all the software has been compiled to run on the ARM architecture. So you got to at least recompile it to run on the i86
That would be true.
So
that would indeed be true.
I mean, it'd be so much easier. I've done this. I mean, I've ported it over to run on Ubuntu, running on a virtual machine on my machine. You can do that. I mean, the performance is not that great, but you can do it.
Well, it's long-term performance as well, because most of my Windows machine, you leave them on for more than a week, they end up crashing. Whereas Linux, I've had systems running for a year and a half. I haven't touched them, so that says something.
Yeah.
But I don't like Windows, so take it with a grain of salt.
Yeah, I mean, I've done a lot of work on Windows because the UA department that I work for is a totally Microsoft shop, and that's the software that we roll out to our customers and everything else. But Linux has a lot of advantages. It really does. So
let's just say you'll never see a Windows machine running as a internet provided server. They're all Linux, or all, yeah.
Or other flavors of Unix.
Right. I rest my case.
Yeah, and that's all because of software licensing fees, you know.
Well, also stability. I mean, the Linux, it doesn't have a lot of proprietary stuff where you don't know what's going on underneath the covers. So
do we have any other questions, Nathaniel, that we missed?
Yeah, I think there was one. I know your team hasn't really started designing the central database yet, Bill, but do you have some sort of preview as to what types of technologies they might be thinking of or considering for the central database?
Well, we're taking a lot of design tips from how the SatNogs team has done the SatNogs network. Our team evaluated all of the recent platforms that you use for web hosting and kind of settled on the same stuff that SatNogs uses, which is a Django front end, which gives you your web front end, with the back end being Maria database, which is a freeware version, and some of the other machinery that goes in between for managing queues and workload management and this kind of thing. Will we need to manage rotating for load balancing between servers and stuff? We don't know. I don't know that we're necessarily going to have that huge of a number of simultaneous users on this thing, at least in phase one. But that is something the computers, it's in the wheelhouse of the computer science department, and they're going to do that part. So, I mean, did I answer the question?
I think so.
Okay.
Yeah, they just asked what the technologies were that were going to be used. So, yeah, I think that answered it fine. Okay. I think that's really good. We're almost getting up to John Ackerman's presentation, and which is going to start in 2 minutes. And I thought maybe John, well, first of all, I want to thank Bill for his great presentation, the discussion. So thank you very much, Bill. It was wonderful. And next, maybe before the presentation starts, John Ackerman, maybe you can give us a little preview as to what we're going to hear and why you did what you did. And then introduce who you are too. Why are you qualified?
In exactly 50 seconds.
Okay, well, I like to measure things, and I started measuring some GPSs. And the first presentation that I'm doing is going to talk about the performance of some modern GPS modules, and then that sort of segues into the Tangerine SDR, where I'll talk for just a couple of minutes about the clock design. With the choice of GPS module ties directly into what we're doing for the clock module.
And one thing that we might want to hear about more later is, someone posted a link to a very inexpensive GPS module earlier on one of the chat windows. I can't find it. And puts out pulse per second and things. And a good question to answer might be, why do we need these fancy GPSs that are more expensive than something that's super cheap? And are there any ways to make these quality measurements less expensive? But maybe we can answer that after your.
Yeah, it's a great question, and hopefully the presentation might answer part of it, but we can talk about it afterwards.
That sounds great.
Hi, I'm John Ackerman, N8UR, and this morning I'm going to talk about the results of some measurements that I recently did on a number of U-Blox GNSS or GPS receiver modules. This is work that's related to the clock module design of the Tangerine SDR. GPS systems have been used for precision, frequency, and timing for a long time, and board-level inexpensive GPS modules have offered a pulse per second output for many years. And even the old receivers got what's really remarkable accuracy if you think about it. You can get a time signal out of those receivers that's within 100 nanoseconds of the official US Naval Observatory time. Just amazing. And with some effort, you can get closer to 10 nanoseconds. Now, a time pulse like that can be used for a number of things. You can set a clock with it. You can use it to timestamp data that you're logging. And you can use it as the reference for a GPS disciplined oscillator. Basically, you adjust your local frequency standard to track the pulse per second, and now you can reproduce the frequency, accuracy, and stability of the GPS constellation. That's what I was interested in, and I'll talk more about it in my other presentation. But in using it for that purpose, there's a problem, because the pulse per second output from the GPS, although it's very accurate in the long run, is kind of noisy in the short term. There's a second-to-second jitter that can be 50 nanoseconds or so in an older unit, less than 10 in a modern one. And those are very small numbers, but they're enough to complicate the design of the GPS DO. So I wanted to see whether more modern receivers might be able to offer lower noise and thus allow us to do some different things in our GPS DO design. So why did I think that there might be an improvement? Well, the new devices are just incrementally better. They have faster clocks, faster processors, some software capabilities that are important. But perhaps most important, we now have, for the first time, affordable dual frequency GPS receivers. What does that mean? A traditional consumer GPS listened to a single carrier frequency at 1575 megahertz called L1, and it decoded a single digital code that's modulated on that frequency called the CA code that runs at about 1 megahertz. By synchronizing to that code, the GPS could establish the timing and distance from the satellite and then the navigation position. But the satellites also broadcast a second carrier called L2 that's at 1227 megahertz and modulation codes that run at a faster rate, which means that they have better resolution and you can get a more precise timing. A dual frequency receiver has a huge advantage. One of the main error components of GPS fixes is the delay of the signal passing from the satellite through the ionosphere. That delay varies with time and location, and it's one of the single biggest sources of error in a GPS fix. It turns out that if you have the same signal modulated onto carriers a couple of hundred megahertz apart, like L1 and L2, you can work out that delay and compensate for it. So a dual frequency receiver is able to take out the ionospheric delay, and that produces much better accuracy in its results. It's really a great advantage. The problem is that until very recently, a dual frequency receiver was a commercial survey or geodetic scientific unit, and the starting price was in the $10,000 to $20,000 range, completely out of reach for hams. But in the last 2 years, u-blox has introduced a couple of new units that are ZED F9 series that are dual frequency receivers for less than $200. And that was really exciting, and I wanted to see how they worked. So it was time to do some tests. And thanks to the HamSCI consortium, and I do want to acknowledge the support from the NSF grants that are shown on this slide, I was able to get my hands on several of the current u-blox receivers. They're shown in this table. In this short presentation, I don't have time, unfortunately, to go into details about all the receivers or all the tests that I performed, but I have a paper in the proceedings that has more than you would ever want to know about GPS performance, and I encourage you to look at it if you're interested in this sort of thing. It might fascinate you, or it might put you to sleep, or it might even do both at the same time, but it will have a lot more detail than I'm able to provide now. In this presentation, I'm just going to have to skim over some of the really high points. So the test plan was to compare the PPS outputs, which u-blox calls time pulse outputs, from all of the receivers against the local atomic clock that had a known stability and accuracy. I wanted to measure all the receivers simultaneously using the same antenna to allow direct comparison. I wanted to measure for several days to get long-term data, and I wanted to do additional runs targeting some specific capabilities and options that some of the receivers have. The first problem was, how do I measure 7 receivers at once? A few years ago, I designed something called the TIC, timestamping counter, which basically is a stopwatch with 60 picosecond precision that can measure 2 inputs. So I took 4 of those, put them in a box, linked them up to a common time base and synchronization and a logging system, and came up with a multi-tick, which was a fascinating project in itself, and I wish I had time to talk about it. If you're interested, the paper that's referenced on the slide has all the details about both the hardware and the software that's involved in doing that. Once the multi-tick was ready, I set up the experiment. All 7 receivers were set up with their default configuration, except that where the receiver supported 0D or timing mode, that was selected. 0D means that instead of having to solve for 4 variables, latitude, longitude, height, and time, the receiver is told its latitude, longitude, and height, and only has to solve for time. In theory, that gives a better result. For those receivers, the fixed location was set to the previously surveyed position of the antenna. The receivers were all connected to that common antenna through splitters. Their time pulse outputs were connected to the multi-tick, and a 10 megahertz signal from an HP 5071A cesium atomic frequency standard was used to drive the multi-tick as the reference that the PPS signals were compared with. The data output was logged to a computer, and we collected PPS data for just under 6 days, about 510,000 samples per receiver, and then analyzed that with the most excellent time-lapse software that John Miles, KE5FX, wrote and has made available to the community. The results showed that there were 2 groups of receivers, basically, in terms of their timing performance. On this slide, we see both a plot and a table. And I want to introduce you to the Allen deviation, which is the standard statistic that's used to determine the stability of a clock or an oscillator. It's a little bit like standard deviation, but tuned for the purposes of clocks and oscillators. The plot shows on the x-axis the sampling time. We may have a pulse per second signal, but we may only want to look at it every 10 or 100 seconds. So this plot shows time from 1 second at the left to 1,000,000 seconds at the right. The data only goes out to about 100,000 seconds, and that's a logarithmic scale. The y-axis is fractional frequency difference. It's a complicated word and concept, but think about it as analogous to a percentage of how much the signal wanders around in relation to the sampling interval. The Allen deviation tells us essentially, if we take a number of readings at the same interval, what's the likely range of the data in all of those readings? And a lower number is better. And it's a fractional frequency, and in a good system, it's going to be a tiny number, so we use scientific notation. If you look at the table, you can see that the receivers broken into the 2 groups, the line of good ones that's lower and the other ones that are a little bit higher on the plot. The 3 good ones are the LEA M8F, which is a single frequency receiver. It's fascinating. It's got some unique capabilities, but unfortunately, I don't have time to talk about it. In the paper, I have several pages of discussion about what the M8F can and can't do. The other two good receivers were the dual frequency ones, as we had hoped. The F9P and the F9T are both substantially better than the others, and that's exactly what we wanted to hear. And in fact, if we look at the plot on the left, you can see that the blue line, which is the single frequency M8 receiver, is about a half an order of magnitude worse than the dual frequency on the magenta line. If you look at the plot on the right, that's simply the raw data, the time interval that was recorded with the seconds on the x-axis being just the length of the run, and the y-axis being the absolute noise in seconds, and the scale here is nanoseconds. If you look at the blue line, which is the single frequency receiver, you can see there's a lot of noise. The magenta line, the dual frequency receiver, has a lot less noise. And that's the eyeball reason why the Allen deviation plot shows better results for the dual frequency receiver. Now, there were two models of the F9. The P model has an RTK engine, basically a differential GPS where correction data can be fed in and the output can be reduced down to uncertainty of a centimeter or two. It's really quite remarkable. The P model is what you'd want to use for surveying applications. The T model is the same basic receiver, but does not have the RTK. Instead, it does have some extra input-output, and it costs a little bit less. We're looking at using the T model in the Tangerine SDR. So the first question about whether the dual frequency receiver gave us better timing is answered clearly yes. It's about a half an order of magnitude better. The second question is, can we do better than that by using some of these software features that I mentioned? There's a thing called sawtooth or quantization error that's in almost all GPSs. The problem is that while the GPS computer can calculate when the beginning of the second is with great precision, perhaps to within a nanosecond, the clock hardware is only capable of generating an output pulse based on the speed of that clock. If the clock were running at 10 megahertz and you trigger the pulse per second output off of the edge of the crystal clock, that means that although you may know the time to within a nanosecond, you may have to set it to the tick 100 nanoseconds. It could be several nanoseconds on either side of the actual time. And that results in a sawtooth error, and you can see very clearly in the right-hand plot, which again is just the raw data zoomed in to show a couple of hundred seconds, and we see this jagged sawtooth pattern as well as some other interesting patterns laid on top of it, and those patterns and that noise interferes with the ability to get low noise results. The modern receivers have the neat capability of knowing how much the difference is between the hardware signal that it can output on the PPS and the actual time. And they can provide that information in a message as part of the serial data output. In theory, we can take that message and then add or subtract that error from the recorded data and remove the sawtooth. And these plots show that that actually works. Again, the blue plot, the blue line on the right-hand plot is the raw data. The magenta line is after we just mathematically remove the noise using the sawtooth correction message. And we can see how the noise almost disappears. Looking at the Allen deviation plot on the left, the blue line is the uncorrected data. The green line is the corrected for the F9T receiver. And you can see about an order of magnitude improvement. The single frequency receiver has also benefited, a huge benefit at short term, but as you get out to 100 seconds or so, that benefit almost goes away. That's just the nature of the architecture of the receiver. So using sawtooth correction definitely works, and sawtooth correction coupled with the dual frequency receiver means that we can start with a noise level that's about an order and a half of magnitude better than the GPS that's probably running the GPS DO that you're using today. I also mentioned earlier the 0D timekeeping option, and I wanted to know whether that really made a difference, and it does. If you look again at the right-hand plot, which is the raw data, the blue line is the 0D mode. This is the F9T receiver, and the magenta line is the 3D mode. And you can see how much more it wanders around. If you look at the Ellen deviation plot, you see that at short tau or sampling intervals, there's almost no difference. But as you get out past 100 seconds, the 3D results become significantly worse than the 0D. So the question of whether we should use 0D is definitely a yes for the answer. Another question that's not really related to the GPSDO but has come up is that these receivers actually allow you to set the time pulse to much faster rates than PPS. And in fact, you can set them to 10 megahertz or higher. And so the obvious question is, can I use that as an RF source? Why not just take that 10 megahertz directly? Well, the problem is the phase noise is horrible. The plot on the left is a phase noise plot, and it's very noisy, if you'll excuse the pun, because it's showing 7 receivers, all 7 of the units. But having the lowest point on the chart at about minus 100 dBc indicates that for RF purposes, these are not good devices. It may be more intuitive to look at the right-hand image, which is a spectrum analyzer plot. The green trace is a good quality signal generator at 10 megahertz. The black trace is the 10 megahertz time pulse output. And you can see that it has noise about 30 dB higher than the signal generator. So the answer here is that you really cannot use this as an RF source unless you either have extremely lenient requirements or a way to clean up the signal before you apply it to a receiver or a transmitter chain. It's just far worse than any sort of RF synthesizer or other signal source should be. Now, I've been told that some people use GPS for things other than timing, some edge cases like knowing where you're located. So I thought it would be worthwhile to do some measurements of positioning performance as well. So all 7 receivers were set up with a common antenna, and I logged 12 hours of their data to a disk file getting just their position ASCII data output. And then I processed the data to generate what's called a circular error of probability, CEP, and you assign a percentage to it. So CEP 95%, which is the most commonly used one, that's the radius of a circle. It contains 95% of all the plots in the data set of all the individual fixes. So it tells us kind of how big a circle the data will fall in if we measure it for some period of time. And here we can see that all of the 8 series receivers have similar performance, about 2.3 to 2.9 meters. And that's about what you'd expect from a modern single frequency receiver. The M9N receiver is very interesting. It's a low-cost unit. It replaces the M8N, and the N stands for navigation model. This is the kind of receiver you'd put in a car. And notice it's 1.68 meters, so it's significantly better than the other single frequency receivers. Then we get to the ZF9P, the dual frequency, and again, it's significantly better still, 1.449 meters, which again, we would hope that with dual frequency, that's the result. The problem is the ZF9T receiver. Its performance really should be about identical to that of the P, but here we look at it and it's among the worst of the units. So there's definitely something wrong. I don't know whether it's a hardware problem or a configuration problem or a firmware issue, but the results for the F9T are I think, clearly questionable, and we need to do some further investigation. I mentioned the RTK engine that the P receivers have. I had a chance only to do one very quick test, but I was able to apply the RTK correction using the single frequency M8P receiver and the dual frequency F9P. And you can see the results are really amazing. The CEP 95% is now 25 millimeters, 1 inch for the F9P, and 29 millimeters for the M8P. So that's just kind of astounding, 1 inch accuracy. Now, I do question the M8P results because that receiver is performing far better than it should. I would expect to see something more like 40 or 50 centimeters. So again, this was a quick test. I need to go back and do it more carefully and more thoroughly. But the short answer is RTK processing certainly can provide dramatically improved positioning performance if you're able to provide that correction information. Doesn't really help you with timing though. This is purely for positioning. And finally, these receivers are able to log raw satellite observations that can then be sent off for post-processing. I did some measurements with the single frequency receiver and both the F9P and the F9T, receiving just the GPS constellation and also in the F9T GPS and GLONASS, and then sent them off for processing by the Natural Resources of Canada web tool. The URL is shown on the slide. I also tested an old commercial survey receiver that was able to do the GPS constellation only. The results show about what you'd expect. The M8P receiver is in the 30-40 centimeter range with correction. All the dual frequency receivers are getting down to the less than an inch and sometimes less than 10 millimeters range. So they perform remarkably well. The F9P performs a little bit worse than the commercial NetRS receiver. The F9T with the GLONASS constellation enabled performs a little bit better. There are reasons for that I don't have time to go into, but the moral of the story is to use both GPS and GLONASS for measurements if you can. There may be times when that doesn't work, but it does improve results by having both constellations available. So I've told you about the timing performance and a little bit about the positioning performance, and now I'm happy to answer any questions that you might have.
Thank you very much, John. That was wonderful. So thank you very much, John. That was wonderful.
Thank you. Okay, I see a question about GPS plus GLONASS for only one location. Things are zooming quickly by here. For or only for location or also for timing. It's a really good question. For timing purposes, you really want to use only one constellation, because the GPS constellation is being driven by the U.S. Naval Observatory clocks, while the GLONASS is being driven by the Russian equivalent. And although they're both extremely accurate, they are slightly different. So timing purposes, you really want just a single constellation, but for positioning, additional satellites basically gives you better results. Let's see. How do you correct the quantization error for a GPSDO? Well, what we're going to do, and I'll talk about this briefly in the next presentation, the processor for the GPSDO will take the input of the time difference between the local pulse per second and the GPS pulse per second, and it will also read the data on the GPS serial port that tells us, hey, the next pulse is going to be 4 nanoseconds early, and it'll simply make that compensation in software. So we take the hardware message and apply the software correction to it in the FPGA processor that will be running the control loop.
John, there was a question on using Trimble receivers. He wants to know your opinion on the quality, I guess, of those, or whether you're just paying for the name.
Well, the problem is there's a whole wide range of Trimble receivers. They make some fairly inexpensive ones on up to the $20,000 surveying receivers. But they're one of the two main receivers used in the surveying and geodetics world. Leica seems to be the other really big brand. For timing, actually, there's a couple of other companies, Septentrio, and I think there's another one called Polaris that make specialized units that some of the timing labs use. But again, those are multi-$1,000 devices. So I'm focusing on the stuff that's potentially within our price range. But even the used surveying receivers, can be quite expensive. The oldest ones you can get for a few $100s on eBay sometimes, but you just never know if those are going to work or not.
Oh, sorry. Are you reading the questions, John?
Well, yeah, I'm seeing them here. And I'm sort of keeping up. Richard asked if for the F9 PT, did you pull the PPS straight off the dev boards or discipline an oscillator? All the PPS measurements were raw pulse per second from the time pulse output of the receiver. No GPS-DO was involved in those measurements. What kind of antenna do you need for the two frequencies? You do need a dual frequency antenna, and those have been a little bit difficult to come by. Again, you can buy the surveying ones, but even surplus, those are a few $100s. You can buy one or two hockey puck magnetic mount type for less than $100, but there aren't really many choices. And we've talked about whether a HamSCI project might be to try to do a dual frequency antenna, which has some interesting complications in terms of calibration and characterization, but that's something we're thinking about for after we get the first set of projects done.
So also, did you see the previous question, adding GLONASS, does that really help you with timing, or is it just for position?
I think I caught that one at the very beginning. It's timing only.
Okay.
I'm sorry, I said that backwards. It's positioning only. For timing, you have the problem of two different time bases because the two satellite constellations are run by different organizations, so their clocks don't quite track each other.
And then how long before you reach the limitations of the clocks on the satellite?
That's a really good question, and one of the things that I haven't had time to test for the really long term yet, but with the dual frequency receivers. But typically, we've thought that if you average for 24 hours or so in a GPS-DO, you can get down to an accuracy of about 1 part in 10 to the 12th, and that's kind of the noise floor. The work that I've done recently indicates you might be able to do better than that with the dual frequency receivers. So we may be able to get down to maybe 7 or 8 parts in 10 to the 13th with a long 24-hour kind of measurement period with those receivers.
And they're having a question on SBAS corrections and low-cost receivers.
Yeah, that's something I didn't play with very much. But a lot of the new receivers and most of the ones that I talked about have the ability to receive this. SBAS is a augmentation system where correction data is actually broadcast by satellites in the same frequency range as the GPS signal. And you can receive that data and get correction. And a lot of the modern receivers support that. It's typically specified to only be good to about a 1 meter or so CEP. So it's better than standalone. It's not dramatically better. The main reason it exists is to get down below the threshold that the Federal Aviation Administration requires for a GPS assisted landing. So it does that, but not much more. I don't think it's going to be useful for timing applications, although that is something that I should probably check.
How about a source for the F9T receivers?
Good question. At the last time I looked, only uBlocks makes an evaluation board for the F9T, and that board really, really sucks. It has almost no user-friendly components on it. I think that's because there just isn't that much demand for the timing version. SparkFun makes a very nice board for the F9P receiver. I think it's $219. That's great for the P, but for the T right now, there really isn't anybody that I know of that's got a nice evaluation board. You can get the one from uBlocks, but it's a pain to work with.
Okay, and I don't think you quite answered this one. Yeah, can you use GPS for the reference time and both GLONASS and GPS for intervals?
I'm not quite sure I understand the intervals. But see, the problem is just that GLONASS is running on its own clock that's separate from GPS. And I think that there is some capability in some of the receivers to tell you what the difference between the two is, so you can kind of converge the two systems, but you still introduce an uncertainty about what's really in control at that point. So kind of everything that I've seen and heard is that for timing, you want to stick to one constellation. You might decide to use just GLONASS because its quality and performance is going to be fine, but its mixing is where you start to introduce uncertainties. I don't know if that really answered the question or not.
And the last question is, are you using Lady Heather for 0D, Sawtooth, etc. corrections, or U-block software, or something different?
For most of the tests that I did for the presentation, I used custom software basically written in Python for Linux. And there are a couple of libraries that have been published to help communicate with the receivers to configure them. But basically, I tried to get the configuration set, and then I just recorded raw data to file, and then process that where I needed to, or for the pulse per second, I just, once the receiver was configured, I was just receiving the time pulse, and I didn't need to talk to the receiver any further.
Okay, I think we're out of time, so take it away, George.
Okay.
Thanks, John. It was great.
Thank you.
Okay, so we're getting ready for our next talk, which going to be, first up will be John Ackerman. And the update is on the Tangerine SDR hardware update. We got 3 speakers in turn. John Ackerman and N8UR will be first. Next up will be Tom McDermott, N5EG. And then last but not least is Scotty Cowling, WA2DFI.
Hi, this is a report on the design of the clock module for the Tangerine SDR. Tangerine SDR requires a couple of different clock frequencies. The most important one is probably the 122.88 megahertz that drives the RF modules, but there's also a pulse per second along with timestamps that are used for data tagging, and we'd like to have a 10 megahertz general purpose reference signal available. Those signals will all be generated by a GPS disciplined oscillator. In addition, the GPS module will allow us to generate a measurement called a total electron count, which is something that the science community would like. So we'll make that data available to the data engine as well. The GPS-DO specifications are a little bit hard to pin down because the science applications are so broad, but after talking with the teams, I think that the following specs will more than meet the requirements for all the science experiments that are currently contemplated for the Tangerine SDR. And that's a frequency accuracy of better than 1 part in 10 to the 12th, or a part per trillion, a frequency stability in the short term of better than 1 part in 10 to the 9th, or 1 part per billion at any tau or averaging interval from 1 second or greater. The absolute PPS time accuracy will be within 100 nanoseconds of UTC as realized by the US Naval Observatory. And the jitter on the PPS signal will be less than 10 nanoseconds. Because this is an RF application, phase noise of the 122.88 megahertz is important, and our target there is better than minus 80 dBc at 100 hertz offset, and better than minus 150 dBc at 100 kilohertz offset. As I mentioned in my previous presentation, a GPS-DO is really a way to get the best of both worlds of using the better short-term stability of a crystal oscillator and the long-term accuracy and stability of the GPS constellation. The magic is to use a PLL, a phase lock loop, with a time constant that allows the crystal oscillator to dominate in the short term, filtering out the noise of the GPS signal, which takes over in the long term. This plot, which I shamelessly stole from the SRS company's website, shows a GPSDO model for a little bit different environment. They're using a rubidium frequency standard, which is much better in terms of short-term performance than the crystal oscillators we're using. But the plot clearly shows how this all works. Here we have the GPS pulse per second signal at the black line, and you can see it's quite bad at short term. It keeps getting better and better and better. The red line is the rubidium standards raw output, and you see it's quite good, and it stays quite good for a long time, but ultimately it starts to become worse than GPS out here near the right of the plot. With a properly designed phase lock loop, we'll get this blue line where we get the short-term performance, but then we transition to the long-term of GPS. Now, we lose a little bit in this transition interval, but that still isn't bad, and it gives us a single source that has the best of the short-term and the long-term performance. And that's what we're trying to accomplish in the Tangerine SDR clock module. So to take advantage of the performance improvements that we get by using the dual frequency receiver, we can look at the previous chart and sort of redesign it. Since our noise after dual frequency plus sawtooth correction is down around 5 and 10 to the minus 10th, that's actually better than our short-term spec. We don't need a long time constant. We can use just a few seconds. And that allows us to use an oscillator that doesn't have long-term performance that's as good. And that means that's a cheaper, lower cost oscillator. And we can spend that money instead on the more expensive GPS module. So we may not save money overall, but we're transitioning where we're spending the money to be able to get other features. This Allen deviation plot kind of shows the tail. The green trace is the performance of a crystal oscillator that's very similar to the one that we'll be using. And you can see that its best performance occurs at around 1 second right in here, but it starts to go up fairly rapidly because of temperature and aging and other factors. This blue line is a traditional GPS, and we can see that the point where they cross over is out here at about 25 seconds, and the Allen deviation at that point is about 2 and 10 to the minus 9th. That's not quite as good as we would like our system to be. However, if we switch over and use the ZF9T PPS, which is the magenta line, now the intercept point is at about 2.5 seconds, and the worst case Allen deviation is about 2 and 10 to the minus 10th. So we've picked up an order of magnitude in performance, and now we can generate a signal that is actually quite a bit better than the specification, which is a good thing because we'll never quite achieve this absolute crossover in practice. The noise hump at the transition will probably be just a little bit higher. So this design should let us meet our design spec using a direct control of the 122.88 megahertz TCXO. And that means we don't need a 10 megahertz oscillator in the mix either, which is another cost that we can reduce. So the key design points of the GPSDO are, again, to use the low PPS noise to allow a short time constant. We'll phase lock the 122.88 TCXO directly to GPS. There won't be a 10 megahertz crystal oscillator. However, we'll make a 10 megahertz output available by synthesizing it in the FPGA. And speaking of that, the FPGA will serve as both the connection matrix and the processor for the clock module. Pretty much everything goes through it. And the reason for that is to allow us to reconfigure the system quite easily without having to move a lot of hardware around. The board will allow lots of extra I/O to allow different implementations. So for example, we could use a 10 megahertz crystal oscillator as our disciplined source. And then we could also generate 122.88 with a low noise synthesizer chip from that 10 megahertz. Or alternatively, we could keep the 122.88 megahertz oscillator, but instead of locking it to GPS, we could lock it to an external 10 megahertz source, like a local frequency standard. So we'll have the capability to implement the GPSDO in different ways. And it's also important that the module can be used independently of Tangerine SDR. We'll have some sort of an adapter to allow it to mount, for example, on a Raspberry Pi and serve as a standalone system. And of course, the hardware and the firmware are all open source. This is a block diagram of the clock module, and it's probably impossible to read, so I won't try to go through its details. But the key takeaway is that pretty much everything goes through the FPGA, which is this block here. That again allows us the flexibility to reroute signals and to try different implementations. The output is here the 122.88 megahertz oscillator, which drives a 4-way buffer and provides the 4 output signals that are needed by the RF modules. And then we also have other signals that go directly from the FPGA to the output connector, which is this block. So at this point, we have the block diagram finished. We're starting to think about turning it into a schematic and then a board layout. But now that we've tested the GPS units and we know how they work, we're very confident that this design will give us a clock module for the Tangerine SDR that not only meets the requirements, but provides in itself a test bed for further experimentation. So thanks much.
Hello, this is an update on the Tangerine SDR HF dual channel receiver module, and we'd like to acknowledge support from the National Science Foundation for portions of this project. The purpose of the module is to provide 2 HF channels from about 100 kilohertz to 54 megahertz. It uses the data engine portion of the Tangerine SDR to actually process the signals. So this receiver module is, in essence, a dual channel A to D converter, which is connected to the data engine by a double data rate parallel interface using LVDS, or low voltage differential signaling. LVDS is used to minimize noise, and pin count limitations on available A to D converter chips generally require use of DDR to get both channels transferred to the data engine. The receiver's been laid out and the schematic, of course, completed, but nothing's been fabricated or built yet, as we're awaiting the actual data engine and the final pinouts before finalizing the receiver. This is a high-level block diagram of the receiver. There are 2 antennas, channel 1 and channel 2. Each goes through a relay, and that relay allows selecting either the HF receiver antenna or a broadband noise source, which is about 5 dB excess noise ratio. The noise source allows calibrating the receiver input over its range, and it is isolated when not in use. There's also a pluggable optional filter, which is used, for example, to provide things like AM broadcast station rejection or HF shortwave station rejection. It may also be bypassed if not used, and there's a jumper to bypass it. The 2 antennas are isolated by transformers, and so those signals can provide common mode rejection without a significant amount of attenuation. There's an optional jumper to bypass those 2 signals and allow connecting the analog ground independently to the digital ground. The 2 signals then go into a dual channel ADC driver, and that driver drives the 2 channels of the 14-bit A to D converter. There's no active components in front of the dual ADC driver, and there are relay switched passive attenuators allowing selection of 0, 10, 20, and 30 dB receive attenuation. This is a layout of the module as we currently have it. There's 2 SMA connectors on the left side, 1 for each channel. Those go through the relays, then they go through the filter module, which again is optional, and if not in place, then it can be jumpered around. They go through a filter and transformer and into the dual driver chip in the center, and then to the dual channel A to D converter. On the right side underneath is an MEC connector, and this provides the digital signals that go from this board to the data engine board. This is a diagram of the AM broadcast band passive filter. This is a band stop filter, which is used to get rid of a wide range of AM broadcast frequencies if there are difficulties with strong AM broadcast signals at the particular site. This is a diagram of the filter response, and you can see that the return loss in red is low out of band and is high in band, and that's typical of reflective filters where the filter reflects those signals that are trying to be rejected as a band stop. One thing to note is that the group delay is quite nonlinear in band, and so there's a lot of equivalent time delay in the band rejection part of the filter. Many times one wants to power up remote antennas, and to do that using an isolated receiver would generally be done by using a DC power supply, a bias tee, and then a common mode choke. The common mode choke allows isolating the antenna from ground while still providing DC power to the antenna. The DC power cancels out the two directions in the common mode choke, avoiding saturating the filter. John and Scotty will talk about their portions of the clock module and the data engine respectively.
Hello, I'm Scotty, WA2DFI, and I'm going to talk to you today about the Tangerine SDR data engine, a quick hardware description, and a hardware status of the system boards. I'd like to thank the support from the National Science Foundation that generously granted us several grants in support of development of this hardware. Also like to thank ARDC for their generous grant on helping us build, helping us build additional hardware prototypes beyond the ones supported by the NSF. So here's a block diagram of the data engine. It's modular construction. The first module will cover the RF modules. They're used for getting the data from the antenna into our data engine. It consists of 240-pin connectors. Each connector will support up to 1.5 gigabytes per second of data transmission over 96 differential pairs. The two connectors are arranged so that you can use them in tandem to get 3 gigabytes per second over 192 differential pairs. Next, we have the clock module, which I believe John Ackerman has already talked to you about, but it's not required for a low-cost system. However, for higher performance, if you need a high stability VCXO or an oven-controlled oscillator or a GPS disciplined oscillator, that will be a socket that you can plug the clock module into on the data engine to get the higher performance clocks. The DE is based upon a Max 10 from Intel. We're going to use the largest Max 10, 50,000 LEs, and the highest speed grade, the Dash 6, and industrial temperature range. So we're going to use basically the fastest and best Max 10 part we can get. The Max 10 will be used for pre-processing the IQ data samples and packetization into Ethernet packets. We'll have a micro SD card for expansion or upgrades. And also, as far as additional memory, non-pluggable memory, we are going to have a bank of DDR3 DRAM, 4 gigabits worth of it, and we're going to use that to run microprocessor, softcore microprocessor code inside the FPGA. And as far as flash goes, we're going to have a 512 megabit QSPI flash and a 512 kbit serial flash. So we'll be able to store additional program data to be loaded into the RAM and executed that way. We execute out of RAM. The interfaces here on the bottom, we're going to have a USB 2 host used to plug in DVB dongles, a USB 3 device, which is a 5 gigabit per second full duplex device port. That'll be used to transport IQ data to a host PC. We're also going to have gigabit Ethernet, and we're going to have a switch on board, which allows us to connect directly to a local network as well as a local single board computer at the same time. Up here on the right, we're going to have an expansion header similar to the Raspberry Pi. It's actually compatible with Raspberry Pi hat boards, and we have an additional connector with some high-speed differential I/O on it, which will enable the Leaf module, which is our Raspberry Pi hat name. The Leaf module will be a little more flexible than the Raspberry Pi hat because we'll have some high-speed I/O as well as the lower-speed serial I/O. This is a layout of the data engine module. You can see the connectors in the upper left for the standard Raspberry Pi, the Leaf connector, the expansion connector, and the clock module on the lower left. And I'll show you here kind of assembly and everything put together. The RF modules are on the back side, and you can see in blue here, and they extend up beyond the data engine on the back side. On the top side, we have the clock module in the lower right and the Raspberry Pi hat or Leaf board in the upper left. So it ends up becoming a 3-board stack with the RF modules on the bottom, the data engine in the middle, and the Leaf and the clock module on the top. So when can you get one? This is the scheduled dates, scheduled well-planned dates. The receiver module is all done and ready for production. We're just waiting on the placement of the data engine to make sure everything fits together so that we don't have any surprises with mechanical interference or anything like that. So scheduled for December 2020. The clock module's in process right now, and the first one out is going to be using the ZF9T. John's already talked about that. We're estimating February of 21 for that. The data engine, January of 2021 for the data engine. And the magnetometer, Raspberry Pi hat, looks to be October next month, October of 2020. And Dave Witten is going to talk to you a little bit more about that. Thank you for your time, and check out tangerinesdr.com for any future updates. Okay, it looks like we got John and Tom and myself here to answer any questions.
And Scotty, I fear that as a moderator, you may have to read the questions from Q&A and distribute them and answer them unless Nathaniel's willing to do that.
Oh, well, Nathaniel and I can jump in and help.
Yeah,
well, at least I'm not chewing gum, so I can read at the same time.
Oh, let's see, where to begin? Well, why don't we start with we'll start with some easy questions, Bill, or easy questions, Scotty. Bill Engelke asks, can I use Leo Bodner GPSDO before the TAPR one is ready?
And I guess I should answer that. Probably not, because the clock module is going to provide, well, actually, yeah, probably not. We need 4 outputs of 122.88 megahertz. And the Bodner can probably provide that frequency, but you'd need to have the fan out to be able to drive 4 differential lines. So you'd need a hardware widget at a minimum to be able to do it.
And why, I think this is Scotty, why did you design the RF connectors 90 degrees off from the I/O connectors? Doesn't that complicate packaging for cases?
Yes, it does, but it eliminates the impossible packaging for the electronics, because if you rotate the RF boards 90 degrees, then it puts the FPGA underneath the Leaf board, and that's not really a doable thing. So the FPGA is going to be in the lower left corner of that diagram I showed you, which is open because it has to, first of all, it has to be open for the height, and then we're most likely going to end up with a heat sink glued onto the top of it because it's a nice heat generator. So yeah, it does complicate it a little bit. However, we did restrain it to only 2 sides instead of 3 or 4 sides. So that might help make it possible anyway. Hope that answers the question.
And Graham asks, where can you get a user-friendly F9T receiver?
I don't really know. The last time I checked, no one was making, no third party was making an evaluation board for the F9T. So you're kind of stuck. I shouldn't really mention this, but as a side project, I've been doing a carrier board, basically evaluation module that you can put both or either an F9P or an F9T on and get it all the IO. And that board is finished and working. And I'm happy to make open source design, anybody who wants to copy it. It does require a toaster oven for assembly because there are a bunch of pins, ground pads on the bottom of the F9 module that you cannot hand solder. But I can certainly provide the files for that if anybody wants to try to build one.
And Richard Stanley says to John, did you try the uBlocks dev board for the F9P? How's the SMA connector compared to the one on SparkFun?
No, I didn't, because I only had one board. Yeah, the U.FL connector is kind of a pain to deal with. However, SparkFun now has a version of that board with an SMA on it. So you can, same price, you can request it with either type of connector. So they've made that a little bit easier. That came out after I bought mine.
And then Scotty, do you anticipate the Tangerine stack requiring anything besides passive cooling?
Unfortunately, the answer is most likely yes. We may be able to design the case with some conductive pads on it to conduct the heat away. That the big heat generators are going to be the A to Ds on the receiver boards and the FPGA itself. And I think the idea is by keeping it in the stack, we put a heatsink on the FPGA, and the A to Ds are actually mounted on the back, on the receiver boards are on the back, and their components are on the back side. So basically the heat generating components are both on the outsides of the tree board stack. If we put small glue-on heat sinks on those, we may be able to use a very small lateral fan to blow air through the stack of 3 boards. It takes very little air to cool the FPGA. I'm not sure. They think the ADCs are probably about the same heat load as the FPGA. So the short answer is probably not. You may be able to operate it that way on your bench as a test for testing, but it's likely to either require a fan or some kind of clever case mechanism to conduct the heat away.
Sounds good. Let's see. And so back to John, for timing, is the only advantage of the F9T over the F9P the lower price?
It does offer 2 time pulse outputs that can be independently programmed. So that could be useful for some other applications. And it also has 2 ability to clock external inputs, which it has 2 of those as well. Unfortunately, in my testing, I discovered there seems to be a problem with using that external input for what we would want to do. But the main reason is it's cheaper. Having the extra time pulse signal could be useful later, but it's not something that we're currently making use of.
And Scotty, Rich Stanley asks, can you share the link if public yet for the code for the Altera FPGA? And then he says, pretty sure it's Altera.
Yes, it's Altera, which is now Intel. So it's because Intel bought Altera. So it's an Intel Max 10 M50 FPGA. And currently I don't have a public link yet. I'm still finalizing the schematic design for the data engine. And at the same time, I'm designing the initial framework for the FPGA because as you FPGA designers know, that it's the Quartus design tool that tells you whether you have made any errors in your pin connections. So before you commit your board design to actual copper, you had better build an FPGA image with all the pin connections and make sure that they all work. So that is in process right now. When we get a FPGA design that actually does something useful, like maybe even test code, self-test code, we'll be putting those links up because this is all going to be open source. So it'll all be available once we get something useful.
That sounds really good, Scotty. Thank you. Let's see. Are there any extra questions? Any more questions out there? John, I have a question. I know that the other John, NAOBJ, was wondering if we could do anything cheaper than the Leo Bodner GPSDO for the low cost station, but you said that you're using the dual frequency, which is more expensive. But if we went to a single frequency chip for the low cost station, do you think that could help that out?
It's an interesting question. It would require a board redesign because the footprint for the dual frequency module is different than the single frequency. And it would probably not offer quite as much performance unless we went to a more expensive crystal oscillator. But conceivably it could be done, but it would be a different hardware module than this one.
Would it be, when you say it would be worse performance, would it be performance on par with using a Leo Bodner? Or would it be at least, would it be good enough? Do you think it would be good enough performance to meet the requirements of a low cost personal space weather station?
It probably could, but there are a number of differences. So first, I don't think the frequency that John is going to require is a VHF clock frequency. I'm assuming it's a 10 megahertz input or something like that. Mm-hmm. So we're set up now to make the VHF signal. You could replace that with a lower frequency oscillator. And then it just comes into an issue of the cost of the oscillator versus the performance. But you know, everything's a balancing act in how you take cost versus performance versus complexity of the loop design.
Yeah.
But
maybe we can talk about that with John NAOBJ offline or later. Because we're coming up to the next presentation now.
Yeah, and I'd like to talk to Tom also about receiver performance, maybe during the break.
Okay. Well, I think we better switch over now. So I think we have our next presentation, which is from Jonathan Rizzo, who is looking at designing a VLF board for the Tangerine, a leaf board.
Hi, my name is Jonathan Rizzo, KC3EEY. I'm a VLF natural radio enthusiast and senior electrical engineering student at the University of Scranton. I'm currently designing a VLF module for the Tangerine SDR for automated reception of natural radio emissions and amateur transmissions in the ULF and VLF bands. For more detailed background on VLF natural radio and the motivation behind this module, I invite you to view my TAPR DCC 2019 presentation, Ground-Based Observation of Whistler Waves, on the Ham Radio 2.0 YouTube channel. For an example of a Raspberry Pi-based VLF automated reception system, I also invite you to view my HamSCI 2020 presentation using a PVC pipe antenna and a Raspberry Pi to detect VLF natural radio on the Ham Radio 2.0 YouTube channel. The random nature of VLF natural radio occurrences and how sporadic they can be, especially chorus emissions, it really isn't practical for the listener with a portable VLF receiver to listen for them unless substantial time and effort is put forth to catch them. Natural radio emissions often occur at inconvenient times, like in the early morning or during bad local weather conditions. I used my portable VLF receiver quite often and didn't hear a single whistler. This doesn't mean these events don't occur, you just have to be at the right time and the right place on Earth. Another issue is power line interference. 60 Hz hum and its harmonics are radiated from power line conductors all the time, often changing in harmonic content as electrical loads like motors and switch mode power supplies dump their harmonic byproducts back onto the power lines. Power line emissions can radiate for miles and still wash out even the strongest natural radio emissions. A great solution to the limitations and pitfalls of live listening is an automated VLF reception system. E-field receivers are sensitive to the electric component of the wave, and B-field receivers are sensitive to the magnetic component. Both offer different advantages to the VLF enthusiast and researcher, and automated systems often contain both, but either one can be used in a single receiver system. These receivers are installed outside, most of the time in a sealed enclosure and mounted on a mast along with their antenna, and are powered by a battery. Sealed lead acid is best, or isolated DC from the feed line. Current draw is usually very little, so a sealed lead acid battery of a few amp hours can last for months. Isolated DC to DC converters can be used as well, but care must be taken so that their switching frequency is high enough that it does not cause interference in the VLF band. VLF audio and sometimes DC power is transported on the feed line running from the VLF receivers to the data acquisition system. Unavoidable ground loops due to the voltage difference between earth ground and data acquisition ground can cause mains hum injection into the receiver front ends via their ground. So audio isolation transformers and isolated DC to DC converters are required. Automated VLF reception systems include the receivers and associated antennas, as well as the data acquisition system that provides the automation. The receivers can either be E-field or B-field receivers, and these systems utilize one E-field and two B-field receivers for triple axis reception that allows for varying and distance calculations of incoming signals. E-field receivers consist of a high impedance front end, either a JFET or op-amp circuit with some added gain, used as an impedance converter. The gate resistor of the JFET sets the input impedance, usually 10 megohms or higher. The antenna is connected directly to the gate of the JFET or input to the op-amp, usually with an inline choke. The output of the front end is much lower impedance and is often filtered, then applied to an audio gain stage for headphone monitoring or a feedline driver to drive a long length of cable back to the data acquisition system. The antenna is a simple electric field probe connected directly to the input stage, and coax cable cannot be used due to an impedance mismatch. The reason why such an electrically small antenna can be used is because of the high impedance of the input stage. If one were to use 5 kHz as the middle of the VLF natural radio band, the wavelength would be 60,000 meters. The impedance conversion is much more practical than even a quarter wavelength antenna. Here is a block diagram of a basic E-field receiver showing the probe antenna, input stage, filtering stage, and output stage, either consisting of a headphone or feedline driver. An earth ground or counterpoise is also required on the input stage, but it doesn't have to be a good ground. The counterpoise created by grounding an E-field receiver to your body is often very effective, especially in portable receivers that you hold in your hand. Another thing to keep in mind is that when connecting to a data acquisition system plugged into mains power, isolation transformers on both ends of the audio feed line are required to eliminate a ground loop, then inject 60 Hz hum into the input stage via ground. Another alternative is an amplitude modulated audio optical link via fiber optic cable for complete galvanic isolation. Power can be provided either via battery at the receiver site or from a feed line via DC to DC converters. However, isolated DC to DC converters must be used on both ends, and their operating frequency needs to be high enough that it doesn't cause interference in the VLF band. B-field or H-field receivers consist of a loop antenna coupled to the front end via an audio isolation transformer to match impedance between the low impedance of the loop and the high impedance of the input of the op-amp circuit. After the front end, filtering is implemented and passed to an audio gain stage for headphone monitoring or a feedline driver to drive a long length of cable back to the data acquisition system. To determine the bearing and direction of incoming VLF signals, 2 orthogonal B-field loops are required for north-south and east-west bearings. VLF enthusiasts often employ orthogonal loops for stereo listening of VLF signals. The magnetic component of observed natural radio emissions often has different signal and propagation characteristics and can provide additional information than the electric component can. Whistlers and tweaks are often stronger in the B field than in the E field and provide additional signal and propagation information. B field receivers require a good ground or counterpoise connection on the input stage and feed line isolation on both ends. Here is a block diagram of a basic B field receiver showing the loop antenna, input stage, filtering stage, and output stage, either consisting of a headphone or feed line driver. An earth ground or counterpoise is required on the input stage for good receiver sensitivity. It is recommended to use shielded loops in an automated reception system because noise sources often come and go, especially with dynamic power line interference from harmonic generation originating from electric motors and switch mode power supplies. These harmonics are injected back onto the power lines and can radiate for miles. Audio isolation transformers on both ends of the audio feed line are also required, and the receiver is powered in the same way as the E-field receiver. Here is an example of an installed E-field receiver on the left. The receiver electronics are enclosed in the PVC pipe, and the feed line and ground come out the bottom, while the antenna element is inside and is in most of the length of the pipe. On the right is a B-field receiver with loop antenna. The receiver electronics are housed inside the gray enclosure, and the feed line and ground come out the bottom. The loop connects from the top. The data acquisition system captures the VLF audio and records it digitally, sometimes adding a timestamp reference to GPS time for correlation purposes. After recording and timestamping, the data is processed using digital signal processing techniques for filtering, event detection, event storage, and visualization. The simplest data acquisition system is a digital audio recorder. For the serious enthusiast, a computer with a good sound card, a GPS pulse per second signal, and appropriate software like Spectrum Labs or VLF-RX tools can be used to capture, record, filter, do event detection, and audio streaming for live listening. Professional researchers often use commercial data acquisition systems like one from National Instruments or others. They can also create custom data acquisition solutions, like the awesome VLF receiver designed by researchers at Stanford University. VLF-RX Tools is an open-source VLF receiver toolkit for signal capture, analysis, and storage of VLF signals and events. It's written by Paul Nicholson, a VLF enthusiast very active in the VLF community. VLF audio and a GPS pulse per second signal is fed into the sound card of the computer. VLF-RX Tools captures the VLF audio and timestamps each sample. Offset correction is applied to the timestamp so they align to GPS time. The signal is then applied to a tracking filter that tracks mains hum and removes it and its harmonics. The filtered signal is then fed into a whistler and chorus event detector that logs each event. Finding location can be accomplished with spheric time of group arrival. Bearing and distance of incoming VLF signals can be determined with triple axis reception. Sudden ionospheric disturbances can be detected with phase measurements from VLF transmitters. The source code can be compiled on VSTs and Linux, and live listening can be done via streaming to an IceCast server. This is a block diagram of the signal flow between the utility programs of VLF-RX tools, utilizing circular buffers and named pipes for transport. Audio and the pulse per second signal come in through VT card, where each sample is timestamped. Offset correction is applied through VT time. The 60 Hz hum and harmonics is removed with the tracking filter, a VT filter. The signal is then combined into a 3-channel stream with VTCAT and sent off to the event detector VT event and the time of group arrival utility for time of group arrival calculations. It is also sent to VT resample that downsamples the stream, and VT Vorbis that sends it to an IceCast server for live listening. VLF audio module for the Tangerine SDR will replace the sound card and use the GPS DO for timestamping. This will produce a stream with combined channels like VTCat does and present them over a TCP socket via the data engine's Ethernet port. Any server on a local network or the internet running VLF-RX tools can accept this multi-channel stream and perform the various tasks such as event detection, sudden ionospheric disturbance detection, time of group arrival measurements, and data exchange, streaming, and signal archival, all without the need for a high-quality sound card and a computer. For the VLF audio module came from a post on the VLF Natural Radio Groups.io group with a discussion of the Behringer UMC 404HD professional USB audio interface for professional audio and music recording applications. It has 4 analog inputs and can sample at up to 192 kilohertz, and was discussed as a high-quality capture interface for VLF and GPS pulse per second signals. Paul Nicholson decided to try it out on his automated VLF reception system that previously employed an M-Audio 192 PCI high-quality sound card. He found it performed better or the same in much of the testing that he did, and decided to use it in production instead. It utilizes a Cirrus Logic 4272 24-bit 192 kilohertz stereo audio codec for analog to digital conversion with 114 dB of dynamic range. It also utilizes the AD8694, NJM2122, and RC4850 op amps for analog filtering, gain, and buffer stages. Here's the front panel. The USB port is in the back. For the VLF audio module, the CS4272 is not a good choice. Only 2 analog input channels are available. At least 3 are required for the VLF audio module, and ideally 4 for a backup receiver. It's also a codec, so that means there are analog outputs as well, which are not required and won't be utilized. So an alternative had to be found with at least 3 analog input channels and no analog outputs. Since it simplifies hardware design, a single IC solution can be used with the same performance. I chose the Cirrus Logic CS5364. It offers 4 analog inputs and no analog outputs, with a dynamic range of 114 dB. The master clock is obtained from one of the programmable clock channels on the GPS DO. Audio samples are transported via the I2S or TDM port to the data engine FPGA. I2S only supports 2 channels, and TDM can support 4. The FPGA will set the number of active channels, sampling rate, sample length, and master clock frequency based on the user configuration settings. The VLF audio module interfaces to the data engine as a leaf board. The I2S or TDM port is connected to a high-speed serial bus on the M.2 connector and I2C control via the Raspberry Pi I/O header. It may have an EEPROM for leaf board ID. For operation, the user connects the VLF audio feeds via audio isolation transformer to the appropriate screw terminals. The FPGA configures the active channels from 1 to 4, the sampling rate, sample length, and master clock configuration via I2C based on user configuration settings. It also configures the GPS-DO programmable DDS channel to generate the master clock frequency required for the configuration. Samples are transported via I2S or TDM to the FPGA and are time-stamped reference to GPS time the same way VT card timestamps a sample. Because their master clock is derived from the GPSDO and the low latency of the FPGA, the timestamps do not need offset correction. The channels are combined into a stream in the same way VTCAT combines channels, and is presented to the Ethernet port via a TCP socket. The channels are combined in the same way as VTCAT combines them, and the timestamps are applied in the same way as VTCART applies them. So the stream is compatible with VLF-RX tools, and the Tangerine SDR and VLF audio module can provide a high-quality VLF capture and timestamp interface in a compact network SDR. These tables are taken from the datasheet. For 192 kHz in either I2S or TDM modes, quad speed mode must be used. Depending on how the master clock divider is chosen, one must select the appropriate master clock frequency, and the serial clock and word clock are generated by the CS5364. For TDM mode, only the serial clock is generated. VLF automated reception systems are an invaluable resource for science. According to an anecdote from Paul Nicholson, written on the VLF Natural Radio Yahoo group, Dr. Robert Schofield, a physicist involved in the LIGO experiment that confirmed the existence of gravitational waves as predicted by Einstein, was tasked with verifying that terrestrial sources of noise, such as spherics, did not generate false detections in the LIGO data. Dr. Schofield contacted Paul and requested timestamped VLF data, but he did not have recorded data in his server's cache for that time period. So Paul contacted Mike Smith, a VLF enthusiast that supplies a VLF stream to Paul's servers. Mike uses a high-quality sound card sampling at 192 kHz to capture a wider bandwidth than the downsampled streamed version of the data Paul had on his servers. And he had data for the time period that Dr. Schofield needed. Data was provided to Dr. Schofield. So, the VLF reception system and network from Paul and Mike played a small part in one of the biggest discoveries of physics in recent years. This is why these VLF reception systems are so important. A VLF receiver built with old answering machine parts and a Tangerine SDR has the potential to do amazing things. I'd like to thank the following: the National Science Foundation for their financial support via the listed grants, Amateur Radio Digital Communications, and the University of Scranton for their financial support, Tom McDermott, N5EG, and Scotty Cowling, WA2DFI, for their technical support, Dr. Nathaniel Frizzell, W2NAF, for his endless support, motivation, and inspiration, and Paul Nicholson for his amazing support and assistance he has given me, his amazing software VLF-RX tools, and his contributions to myself, my projects, and the VLF community at large.
Thank you very much, Jonathan. That was great.
Thank you.
Let's see, do we have any questions here? Well, I think one person's asking, what about using military surplus VLF receivers? Why are we doing this?
Well, I was actually looking for a couple of those receivers because I wanted to know how they were designed and how they actually work. From my understanding, they contain a lot more stages, and they don't necessarily output an audio feed that is the whole bandwidth of the VLF band. So I would really like to get one and look at them and see if it is possible to actually use them. But for the time being, for this system, so far I've had good luck with homebrew receivers that I built.
Thanks. I think one thing is that since we're trying to build a fairly complete personal space weather station, it's really good to have these different modules where, you know, if you want to use it for doing VLF, you can do so. If you want to use it for doing HF, you can do so. So I think this is a really nice board that will help to round out the system as a whole.
So I have a question, my own question for Jonathan. The Cirrus part that you picked, the 5364, can you give us a little more info on that? Is that a quad channel part, or are you going to use multiple ones, or well, what does the performance look like?
Well, so the 5364 is quad channel, and its dynamic range is 114 dB, and it is specifically an A to D converter, so it doesn't have any outputs, and that's why that I chose that part, because I didn't want to have extra A to D converters, even though that I could have. I figured this would simplify design, and it would give pretty good performance. That's why that I chose this one.
Jonathan, do you know if there's an easy way to calibrate an LF-VLF H-field antenna system to actual field strength?
Yes. When I was doing my senior project, I built up a VLF receiver designed by Paul that has, so what he uses is an AC line filter choke as a transformer to inject a calibration signal to the input of the receiver. And he uses a calibrated, he uses a calibration signal that's synced to GPS. Unfortunately, he hasn't released a lot of documentation yet, but he primarily uses it for phase calibration. There's some more information in his documentation for VLFRX tools, and I invite you to check that out. And it is possible for field strength and amplitude calibration as well. But for the signal analysis functions that Paul does, it's in VLFRX tools. It doesn't seem to be very important.
Thank you.
Mm-hmm.
Dave New asks, is there any noticeable reception of passive key fob systems operating on either the 125 kilohertz or 18.2 kilohertz? He says those are B-field systems, so in theory they shouldn't propagate very far.
Well, I believe that because those signals are usually so weak, you would have to be pretty close to the antenna to actually pick it up. That's the good thing about those sorts of things, is that if their transmitters are fairly low powered, then it's really not going to cause that much interference. I would imagine that would show up as pulses on the incoming stream. A big source of interference is it's an automated meter reading standard. It's abbreviated TWACS, TWACS, and that superimposes pulses onto the 60 hertz sine wave, and the high frequency components of those pulses generate a lot of noise, and they
present problems to these sorts of systems. So that's unavoidable interference because those are radiated on the power lines. But as long as far away, there shouldn't be that much of a problem.
And you know, John, N8UR, and Scotty were talking, you know, wondering more about your clock requirements and what you need from the clock module and how we would get. So what frequency do you need, and how are they going to provide it? So maybe Scotty and John can jump in here for a minute.
Yeah, so we just need to know what frequency you're going to need, and generally it's preferable to get the frequency from a clock generator or a synthesizer rather than through an FPGA because of jitter issues. But
yeah,
go ahead.
Well, so the plan was for the GPSTO, since you mentioned that it had 4 programmable clock outputs. One of those would be used for the master clock of the ADD converter, and based on the channel configuration used, it would set the frequency. And from the looks of it, it looks like the maximum frequency is around 50 megahertz, but it really depends on how you configure the ADD converter. That's why that I included that table in the presentation.
Right, and it looks like the range is 30 to 50 megahertz, so we just have to make sure the synthesizer can generate that. I think it can, John, right?
If we build with the synthesizer module, yeah, we can generate any of those frequencies without any problems. It's just the current design for the CKM doesn't have the synthesizer. It would have to be
right,
the synthesizer version, but with that, it'd be easy to generate those.
Well,
right.
We could generate it in the FPGA if you're willing to tolerate the increased jitter performance that you're going to get from it. I don't know how critical that is for you at this frequency range.
Well, that would be, when I'm actually testing this module, that would be something to investigate. I was also thinking about using, I remember reading or hearing somewhere that there were going to be lower cost clock modules based on some sort of a TXCO or other sorts of frequency sources. So I was thinking about using those also as an option if you don't want to do sudden ionospheric disturbance detection, where you don't really need that accurate or you don't really need a fairly jitter-free clock. So that's also an option too, either from the FPGA or
another option would be for you to synthesize a clock on board from a standard frequency that we give you. Say we were to pick 25 or 50 megahertz and say you always get that, and then you could go from there. Would that be an option?
Yeah.
So anyway, we need to talk offline about this, and I think Steve is ready to chime in here on the break time.
Thank you so much, Jonathan. It's been great having you.
Thank you.
Thank you, Jonathan. Very nice presentation.
Thanks. Yeah, very, very nice. So yeah, I think we're going to turn it back over to Steve now. So we'll say 73 to Jonathan, KC3EEY again. And I do want to point out Jonathan is a senior at the University of Scranton, but he's also an engineering technician at on semiconductor. And so he's been doing all of this work himself, just driven by his passion for VLF studies. So I think it's a great job.
Thank you. Thank you.
You're welcome. So I'll say 73 to Jonathan and back over to Steve, N7HDR.
I think everyone, especially ham radio operators, especially those of us that are technical experimenters, are passionate about it. So you're in good company there, Jonathan, so welcome. We also need the younger blood to replace some of us graybeards here as well. Okay, it's break time. I'll put up the break slide and we'll be back in a little less than 30 minutes. Go ahead and take this time to stretch and relax and grab something to eat. And as always, the chat room is open and you'll probably hear some conversations going on. So don't be surprised on that, but we will see you at the top of the hour.
So Steve, how do you think what do you think about the presentations so far?
The presentations are excellent, and when putting this all together and gathering all of the papers and those that would like to present their papers. So we received 14 papers for the proceedings. For those that are registered for the conference, you will be getting an email where you can go and download the PDF. It's over 230 pages. You'll also notice on the break slide I have here where you can order the printed proceedings. Thank you, ARRL, for compiling the proceedings and putting them in book format as they do every year for the DCC. And they're putting it at a very well, they're basically putting it at cost, $9 plus shipping. So this price will carry on about a week or 2 weeks after the DCC. So if you're interested in getting a printed proceedings, order it now and get it at the at cost price. And as to the talks, 14 papers submitted, 13 of those papers are being presented here today and tomorrow, in addition to other invited speakers and those who have requested to speak. So actually, I haven't even counted how many talks we have, but I had to extend today an extra 2 hours to be able to fit them all in. We had more talks than we did slots for them.
That's really good. I think we have another question for Jonathan here, if he's still on the line.
Yes.
Yeah, it says, do you have a recommendation for a loop receiving antenna for sub 500 kilohertz? I built them in the past, but that was decades ago. What's the state of the art?
Well, I did not get to the experimentation phase for my loops yet. But what I do recommend, there are a lot of technical papers on a website called vlf.it, vlf.it. It is a great resource for VLF, and many people have done the experimentation and modeling for loops specifically for VLF receivers. And they have excellent papers there and excellent resources, and I would definitely recommend it. I've spent a lot of time on there myself. So for ideas and some inspiration for loops, I would recommend that. For the B-field receiver design that I'm going to try, there is a paper from a Vietnamese group, a Vietnamese university. They have designed a loop antenna and a receiver. That the picture of the loop antenna, that's actually what I posted. I would also recommend that you look at that paper. It is freely available on that site as well.
Thanks a lot, Jonathan.
Mm-hmm.
Yeah. Roy Gerdig and Gregory Raven, they said thanks for the VLF.IT reference. And also thanks for the interesting site. So that's really good.
Yeah, it's a great site.
So Jonathan, that loop is an unshielded loop, correct? Because it looks like it's just wires.
Right. That loop that was in my presentation was unshielded. Although I would recommend shielding for a system. They didn't have a lot of interference when they originally wrote this paper, and I've also heard stories of people building these loops with and without shielding, and it really didn't help them. And there were also some people where the shielding did help. So it kind of depends on your location and your noise sources, whether you really need it or not.
Okay, because I'm not a loop expert, so I'm not sure what advantage shielding gives you, but I just noticed the interesting construction of that loop. Looks like something very easy to do.
Well, the shielding is meant to shield the electric field from being picked up by that loop, and only the B field. So so in a practical loop, the majority of the E field energy is shielded, and most of what you get is the B field.
Okay, very good. Thanks.
Mm-hmm.
Anyway,
so yeah, Jonathan, what are your next steps in terms of working on this?
So my next steps, what I was going to do, I was going to work on the basic schematic and the power layout, and also the input stages. So what I wanted to do was I wanted to get get a power design, mainly an LDO based design for the analog power, and trying to model some filtering if I need to. But the main thing is power, and also doing some SPICE simulations on the input stages. I was going to start with the filter values that they have in the data sheet and play with those until I get something that I think is the best.
That sounds really good, Jonathan.
Mm-hmm.
I got to get my mute right. It looks like Tom is not still here. Tom McDermott, are you still here? Anyway, I suggest asking Tom's help if you're interested, because he's an expert receiver design guy and does some modeling too. So he might be able to help you, or together you might be able to come up with some pretty awesome simulations and designs, or a design. So just suggestion.
All right. When I'm ready, my intention was to ping him and you with a design for the power circuits.
Yeah, because we're going to need to work together to come up with the pinout of the leaf board, which is not finalized yet.
Right.
So that you're going to need definitely. We want to make sure you get all the support on that connector that you need.
Yeah, that once you finalize that, I'll take a look at it. The main thing is that as long as there's a path for, or as long as there's a pin for a clock coming from the GPSDO for the GPSDO design with the programmable clock output, then that's really one major hurdle. And then
the only problem, The only problem is that not all clock modules will have that particular pin out. So even though we assign the pin, and I prefer not to require that you buy. Let me maybe phrase this as a question. Do you perceive that you're going to need to have a GPSDO on any VLF receiver that you set up?
Well, you don't really need one, but to make meaningful measurements, it's kind of fairly necessary. I would imagine for the non-serious enthusiast, either an onboard clock, or instead of the GPSDO, use a program, or use a lower cost frequency source. Because weren't you, wasn't the original design gonna intend for other frequency sources than the GPS one?
Well, there's other frequency sources besides the clock module, because the vision is we're going to have multiple clock modules, and there may be even a clock module that doesn't have a GPS on it, in which case that, depending whether it had a clock synthesizer on it, it might or might not be able to give you the frequency that you need. So one of the alternatives would be for you to just put an oscillator on your board and feed that clock to the FPGA, synchronous with your data. And then you're kind of the master in transferring the data. And then you could pick any frequency you want, really.
Would we want, though, I think we would want everything to be synchronized to a master clock for the whole system, though.
Well, it will be,
right?
But this would be the data channel would be not necessarily synchronized to the master clock, and we'd resynchronize that coming in, because he's only running at about 50 megahertz. So as long as it's digital data, we can do that. And do you see, other than synchronization between the channels, we're not going to need to synchronize with anything external, are we?
Well, the thing is, the reason why that this module is so reliant on the GPSDO is because the program called VT time that I mentioned. So VT card is the program that reads the samples from the audio driver, and it assigns a timestamp to each of those samples based on the system clock. Well, and by system clock I mean the sound card clock. And VT time does offset adjustment on those timestamps based on a GPS pulse per second signal that is read from the unused channel. So if you have VLF audio coming in the left channel, the right channel, the pulse per second signal comes in, and Paul uses some DSP techniques to find when a second mark actually occurs. He uses three methods, but if we have a clock that isn't from the GPSDO, then in that case, what we're going to have to do is we're going to have to use some DSP techniques in the way VT time does to provide correction for the timestamps. That's the only thing.
If you're gonna require like say a 56 megahertz clock, I looked in your table. It looked like all those frequencies were very explicit and down to 2 digits. So like 49.50 megahertz or 52 point. It's a specific frequency that you have to run at because the data is synchronous with the I2S channel or the TDM channel.
Yeah.
And that is not going to be synchronous with the GPS, because that clock is, I mean, if it's 52 megahertz, how could we synchronize it to the GPS? I mean, we can get a timestamp of the data coming in from the GPS by looking at the 1 ppm and the correction to that. So what we get is we get a very accurate timestamp at the ppm clock time, because we measure the 1 ppm clock time very accurately, and then we get information as to how to adjust that to become real time, right? So
right.
That mark comes in, that mark comes in, that mark comes in. Well, how far off of real time is it? Well, during that 1 second, we can figure that out, how far it's off. So, but I'm just trying to figure out how we're going to timestamp those, because you're not going to timestamp them. You're going to receive them with the A to D, the quad
Yes.
A to D, and you're going to send them over the TDM channel. And then the FPGA is going to timestamp them, or we're going to send them to the single board computer, and the RX software is going to timestamp them. How is
no.
it?
Oh, so what's going to happen is the FPGA is going to do the time stamping.
Okay.
And oh yeah, that brings up an interesting point, because so the reason why that those clock values are so specific is because they are for the different modes of the A to D converter, depending on what you choose, whether you choose 1 channel or 4 channels, it's a different clock rate. So that's why that.
Is there a fixed relationship between the data coming in and the time it was actually acquired? Because if that's fixed, we could adjust the timestamp.
Well, that's exactly what the VT time program is doing. It's adjusting those timestamps. So that would, I assume, since we were using a programmable clock from the GPS, that we wouldn't really have to do that. But I did not think about synchronizing that with the FPGA. So
yeah, because that transport layer between the A to Ds and the FPGA, that's not going to be synchronous. That's going to be, I mean, if you use those specific clocks, but it's likely to be a fixed latency or fixed offset between when the actual sample was taken. And if that's the case, and the FPGA knows what frequency you're at, what mode you're in, and it can apply an offset, then we can timestamp it correctly, at least to the best of our ability. I don't know what the software does. I mean, how does it, you feed it an offset or a correction so it knows what to do?
Yeah, what it does is so it'll actually sample the pulse per second signal on the other channel, and it'll find through 3, you could choose 3 different methods. It'll find when that pulse per second actually occurs in relation to the sound card clock, and also the time set on the computer, and it generates an offset value that adjusts the timestamp on the sample.
Okay, but how does it know how to do that? Is it, I mean, do you tell it that as a parameter when you fire up the code, or does it actually go, it looks at the 1 pulse per second, but how does it know, how does it see what the sample clock is? I mean, is that another hardware input that it sees?
No, it gets its information we'll see what it does so the VT card program sets the sampling rate of the sound card.
Okay.
And it goes based on the sampling rate of the sound card. I'll have to double check the details. It's in Paul's documentation.
Okay, but when it gets the sample, it's got to be some kind of latency between the time the sample is, which edge of the sound card. Now, I don't know, maybe these edges are so slow that it can calculate this in one clock tick. So because I mean, it would seem like it's going to have to somehow line up the sample clock of the A to D and the pulse per second time, right, to get an offset.
Right. It I believe so. So what it does is VT time knows what the time is set on the system, which is disciplined by NTPD.
Okay.
And it also knows when the pulse per second signal comes in reference to the system time.
Okay.
And what it does is it calculates the difference between so it sees the system time I'm not exactly it was a while since I looked at the source code.
Yeah. Yeah, really. Probably complex.
This is so how Paul does this is pretty complex. Because I asked him, well, why didn't you use say like a pulse per second signal coming into the serial port or a other port? And he said that there's too much system latency between when the time or when the system actually detects it. So he wasn't able to get good performance that way. So he did it his own way through the sound card, which was which he's able to get 50 nanosecond accuracy on these timestamps.
Okay, so he's getting it from the sound card. He's getting the acquisition time of when the sample was taken. So that's how he does it then, is he's getting that and comparing that to, well, he can't compare it to system time. That's probably not accurate enough. But he gets a pulse per second some way, right? Or he gets it from the sound card.
So he gets the pulse per second signal from one of the audio channels.
Okay.
And the actual and you can choose between 3 different detection methods based on your pulse per second signal properties. So for the Trimble receiver that I'm using, I use a method where it finds the phase center of the pulse, and it's at that point where it actually sees the pulse per second signal that pulse happening. So
okay. Well, I can see how he does it, because if he feeds it in through an audio channel, then the same A to D is going to convert the pulse per second as is going to convert your actual sample, right? So then they're going to have similar time delays. So he can basically null it out by assuming that if the delay is the same for all the channels in the sound card, then you're going to get the 1 pulse per second coming in coherent with the sample. And then if you know the offset of the pulse per second, then you got the time of the sample. And then he can sample it. But if we do it through the FPGA, we're going to have to do it differently, I think, because the FPGA is probably going to have to timestamp it.
Right. Yeah. Yeah. Actually, yeah. That's pretty much exactly how he does it. I would have to double check the source code, but I believe that's how that he does it.
So then we'll need to change in the software to when we do it through the Tangerine, right? Because I'm thinking you're going to run the software on the single board computer, right?
Right. Yeah.
And Scotty, you got a 1 minute warning.
I see that, Steve. Thanks. I think we're done here, but
there's one question that is on the chat here to Jonathan. Do you have a budget estimate for the VLF module?
$50 to $75.
Okay, great. Thanks.
Very good.
All right.
Anyway, Jonathan.
So next up, Dave Whitten.
Yes, we're ready for him in just about 60 seconds. So good afternoon, Dave.
And there's Dave.
Hello, I'm here. But I imagine you have a copy of the presentation.
I do. Would you care to introduce your own talk?
Well, the talk is about the ongoing calibration and characterization of the magnetometer component of these projects. And that's pretty much, there's a lot of folks been helping out with that. Hello, this is a presentation about the magnetometer characterization for the space weather projects that we have going on. I'm Dave Whitten, KD0EAG. This work was also conducted by Yeoman Kim, KD2 MCR of the New Jersey Institute of Technology, including assistance from Gil Jeffer and Sun Young No, among others, and especially Julius Maddy, K2K GJ. And we're very appreciative of the granting agencies that have helped us get this these projects going. This, like most projects, involves, well, first I should say something about why we feel we need a magnetometer as part of these projects. And I believe the best explanation is that, as most hams are very aware, the terrestrial electromagnetic environment is very subject to the vagaries of our ionospheric environment, and the ionospheric environment is heavily influenced by a variety of off-planet sources of influence, but most notably the sun, solar storms, solar ejections, all manner of things, and sunspots. All these things are well known to cause great changes in the electromagnetic environment on Earth. The magnetosphere is particularly influenced by this environment. In any case, as part of these projects, we wanted to use a magnetometer that was inexpensive enough to be deployed widely, but sensitive enough to provide useful scientific data, particularly when taken in as a collection of a lot of physically dispersed sensor sites. The components of, the important characteristics that we were looking at are the sensitivity, of course, of the sensor itself, the noise, the degree to which it's susceptible to corruption from non-ionospheric noise, the accuracy or and the degree to which the measurements made correlate with those at established instruments, and also can it be packaged in a way that can be deployed repeatably at a lot of different places by a lot of different people. Another component of this effort has been creating software for testing. There was very little initial discussion of what software to use. There's not a lot of software that comes with these sensors when you first receive them. And so there was very little initial discussion about how to go about this. You can't test much unless you have some software, not with these sorts of things. And there's a tendency when you're discussing projects that have a lot of hardware to assume that the software just kind of happens. On the contrary, the software takes a lot of time and debugging in all aspects of these projects in order to make anything that anyone can actually use. The other thing about the software for these kind of undertakings is that it never seems to be entirely finished. There's always another feature that could be worked in. Now, here I have a mock-up of the one of the early designs for the magnetometer support boards that can be used both locally to the single board computer component of the weather station and remotely when populated with a magnetometer module here as the actual sensor that we're using to collect data. These also have both the magnetometer sensor and a temperature sensor at each end also. And so we can do some calibration and sanity checking. The magnetometer module is called the PNI RM3100 module, and it's a 3-axis magneto-inductive measurement module. It's low cost. It's about $20, and hopefully that will allow us to do widespread deployment. They're very small. They're about 1 inch square and a little over 8 millimeters high. And so they're very small compared to most other sensor types that are used for these purposes. And it has substantially higher sensitivity than the types of magnetometers that many of us are familiar with these days in our cell phones and navigational devices. The manufacturer claims 13 nanotesla with the default settings. I want to emphasize that one of the purposes of this undertaking was to determine what non-default settings would benefit us the most, and that remains an ongoing an ongoing investigation, but we've substantially improved the observable performance by adjusting that. Here we have some pictures of folks that work with Hyum and Kim at NJIT, deploying one of the earliest experiments we did, putting out one of these magnetometer units at Jenny Jump Observatory in New Jersey at the end of June. The objective here was that we wanted to compare the data we could collect with that of the NJIT science magnetometer that's at Jenny Jump. Both data sets were averaged over, in a kind of a 10-second moving average. At least the data we're collecting from our units is currently being collected at 1-second intervals. It's not, the upshot of this first test was that we were not completely satisfied with the correlation between this device and the Jenny Jump device for reasons that haven't completely been cleared up at this point. We're still working on that, but we think we're getting to that. One of the design features of these this architecture was that we wanted to separate the actual sensor as far as possible and in as low noise a manner as possible from the single board computer and other items that make up the ground station. To this end, we decided to use I2C based communication, and which might seem a little odd because I2C provides usually about a half meter of separation between components. It's designed for use inside of a chassis. And it uses single-ended signaling that provides very little noise immunity in the outside world. The personal space weather station and similar projects require significant separation between the sensors and the support electronics to be useful. We decided to work with a chip from NXP Semiconductors called the PCA 9615 that converts I2C single-ended signaling to differential signaling and allows you to use a voltage that's independent of that you're communicating with your host for the remote communication. We did this over essentially Cat5 or Cat6 cabling, using RJ45 connectors. Differential signaling allows, as usual, a substantial increase between the remote sensor and the data collection apparatus. And reliable operation at well over 30 meters was demonstrated in the testing, quite possibly a good bit more than that. The design of the I2C, differential I2C bus allows attachment of additional sensors as well at either the local or the remote end of the bus within the limits of available power. We found that changing the remote regulator to a very low dropout unit and using 3 volts to power the sensors rather than 3.3 seems to have made a major improvement when coupled with in-ground temperature stabilization. The downside of this is this NXP PCA 9615 chip is a real pain to solder. Let me tell you. We became quite concerned about the temperature sensitivity of the sensor. The manufacturer states that the sensor coils alone have a maximum temperature coefficient of 2 nanotesla per degree Celsius, and that they're roughly free of temperature sensitivity because of their design. We did not find that to be true within the requirements of this project. Measurements made by Julius Matty on the complete RM3100 board, as well as information provided by Dave McGaw in some quick tests that he did, indicate that a 7 to 10 nanotesla per degree Celsius temperature coefficient is probably more realistic for the complete assembly. So therefore, temperature is an important parameter. We are currently assuming that measured temperature stability is better than 1 degree Celsius over 24 hours. But this finding really motivates us to explore in-ground deployment as a mitigating, to mitigate this. So here you have some photos of an initial go at burying these sensors to see what would happen. Essentially, we're using Cat5, or shielded Cat5, and here you have the magnetometer support board and an actual magnetometer module. This is the remote end of the whole arrangement. Again, hopefully at least 100 feet or so from any other electronics. Some standard PVC pipe, perhaps some closed cell insulation, and a waterproof RJ45 jack. Here you get a better view of the actual magnetometer module itself, but you can see how this sensor is assembled and placed within the burial containment. And here you can see pretty much what it looks when placed in the ground for actual use. Now, ongoing work includes continued development of software, especially to support the new set of boards that will be that are hopefully being produced very shortly, that are much closer to the intended end use, the ultimate magnetometer boards that will be used. Probably port everything to Python from C, just for convenience for some uses. And hopefully this might be used for the final integration of into the data collection system that Bill Engelke and others are working on. If that proves sensible, at least we hope to provide concrete example software that illustrates how to manipulate the various parameters that can be tweaked on these devices. Also, for the whole system as a whole, We want to do further evaluation under realistic conditions. We want to test at more established quiet sites and do more comparisons with calibrated sensors of established quality. And we have significant hopes of being able to do that through the fall here with a little luck. Our conclusions are that for the critical parameters we decided were most important, that the RM3100 can provide perhaps 10 nanoteslas of sensitivity if carefully deployed. The measures are susceptible to corrupting influences, such as electric deer fences, but with thoughtful site selection and positioning in sensible places, it should be capable of producing some useful data. Accuracy, initial tests show good correlation with one standard magnetometer installation, the Fredericksburg, Maryland site on Intermagnet, the website Intermagnet. Some divergence from the Jenny Jump, New Jersey site remains unexplained, but we're working on that and we expect to have that chased out eventually. Improvised Helmholtz coil measurements suggest that the RM3100 field data is good to at least 5%. Tests with traceable standards are anticipated soon. Current indications are that significant protection from temperature shifts and other hazards are provided by below ground installation, which we are continuing to experiment with. I apologize, I only have one reference here because the slide would not accept any more. Got very aggravated with it, don't know why. But this is a link to the user manual for the RM3100. I do want to say that there are substantial other materials relating to the project so far on the site we're using for this conference, but I can't give you the link right at the moment. We can probably give you that to you afterwards. Thank you.
Thank you very much, David. Scotty, do you have any questions?
Yeah, I had a question from the list here, unless you're going to handle it, but
Oh, you can go. Okay.
The question was, are you using Ethernet cabling for connections to carry the non-Ethernet differential I2C signals and power?
I'm sorry, are we using Ethernet? I missed part of that.
The question was, are we using Ethernet cable, but using it to carry I2C and power rather than Ethernet?
Yes, that's exactly correct. This is definitely not compatible with your local network.
You want to go ahead, Nathaniel?
Sure. And then the second question is, what is the expected measurement range? And how much better are the standard magnetometers, say from the USGS and NGIT in performance, compared to these low-cost magnetometers?
I would have to defer that. Actually, Hillman is out there as a, I don't think he's anyone gave him a presenter link, but
he's logged in.
Oh,
are you there, Hillman?
Yes, I'm here. So could you please the question, repeat the question again?
So for these magnetometers, what is the expected measurement range? That's part A. And then part B is, how much better are the standard magnetometers, such as the ones run by the U.S. Geological Survey and NGIT in performance, than these low-cost magnetometers?
So expected measurement range is basically the Earth magnetic field, which goes between about 60. The space physicists usually use nanotesla instead of any other units available out there. So between 60,000 nanotesla and minus 60,000 nanotesla, that is our desirable range, which this particular magnetometer can achieve. I think the dynamic range of this magnetometer can include the Earth magnetic field range. So by adjusting the proper digitization level of this output, we should be able to cover the Earth magnetic field variation range, which we want as space physicists. And second question about comparison between this low-cost magnetometer and the much more full-blown magnetometer run by, say, USGS in terms of performance level. At this moment, hard to say, but the target, basically the target is different. USGS, they are very interested in absolute measurement of the Earth magnetic field. They want to know how the absolute magnetic field of the Earth changed over time, whereas as a space physicist or space weather related research, we want to know variation rather than absolute value. So as long as we can detect those type of variation, we'll be happy. And then variation compared to the magnetometer that USGS magnetometer can do, we're not trying to measure any like really, really tiny, precise level of variation. We want to know, for example, geomagnetic storm, substorm, that can be detected easily by even this type of low-cost magnetometer. In terms of number, we are shooting for tens of nanotesla level sort of accuracy or resolution. But I believe this particular magnetometer can achieve up to a couple of nanotesla range. And we have compared this magnetometer with a local USGS run magnetometer in a very crude way. And we found out that it was very comparable. What level of to what level? That's something that we should find out. But from our preliminary observations so far, it was pretty comparable. But again, I like to stress that the target is very different. We're not looking for such an absolute precise measurement of the Earth magnetic field.
Okay, and Hillman, that leads us to another question that is, what do we expect to learn from the magnetometer measurements? Does the DC magnetic field significantly influence HF propagation?
So I guess that's not really the question that I can handle. Maybe Nathaniel can handle that, but what do you expect to learn from the magnetometer measurement itself? Well, basically the Earth has a magnetic field around, and magnetic field always is susceptible to any type of influence from the space, say solar wind and solar activity. So any type of variation or disturbance, perturbation can be related to what is really going on in the solar terrestrial environment. So there are a lot of things we can learn from magnetic field variation in terms of solar terrestrial environment, but how does it affect application? That would be the question to Nathaniel.
Yeah, so I think there's a few things going on here. I think in terms of the background DC magnetic field that's not changing very fast in time, I think that can affect HF propagation in a number of ways. Really, I think one of the strongest effects of it is how the magnetosphere is organized, or the configuration of the magnetic field. So because the background magnetic field, that's what's going to control whether you get O mode propagation through the ionosphere or X mode propagation through the ionosphere. So just that background magnetic field can control that sort of thing. Also, the background magnetic field can help organize the different parts of the ionosphere, because you have up at the high latitudes, you have the auroral zone, and that's because you have the field lines, the magnetic field lines going more into the Earth, and there, whereas at mid latitudes, the magnetic field lines are tilted a little bit less, and so you'll just see different propagation effects just from the geometry of those field lines. So I'd say maybe that's not exactly related to the background strength of the magnetic field, but it certainly is related to that background field, just its more static configuration. Then in terms of the variability that you see, one of the reasons we see the variability in the magnetic field on Earth is because of current systems that are traveling through the ionosphere. So if you have a current system that might be caused by auroral activity or by geomagnetic activity, that will be picked up by the magnetometer on the ground. And that is that variability can cause effects in radio propagation.
And another question we had here was, and this is probably for Dave, and maybe I can help answer it. Did we consider BLE or other wireless modes to connect the magnetometer up rather than using wires?
Well, I think we kind of dismissed most of those options early because we wanted we wanted the quietest possible option that we could think of, lowest number of data transitions and RF emanations and things, using shielded cable to get significantly far away seemed like a major win. I don't know. What would you say about that, Scotty?
Yeah, I think you hit it exactly right. And we'd still have to run power out to it anyway, so you're still talking about a wire. So, and I just noticed that Jules is on here, and
yeah. I meant to point. Yeah, he might have something interesting to say.
I allowed him to talk. I know George is getting antsy because we're out of time, but Jules was very instrumental in doing a lot of the testing. So I'd like to defer to him for a second if we can. Jules, are you here?
Sure. Can you hear me now?
Yes.
Is the volume good enough?
It's a little loud, but we can deal with it.
Okay, I'll move it back. How about here?
Good.
All right. Just wanted to comment relative to the change that we might need to be picking up in the magnetometer. A few days ago, probably due to a solar wind shift, the magnetometer data at Fredericksburg registered about a 70 nanotesla shift over a matter of 3 or 4 hours in the X component of the field. Now that would easily be picked up by this magnetometer. Typically, diurnal variations are in the order of 10 to 20 nanoteslas, maybe 30. And this mag, in the test that I've been doing recently with the ground buried unit, has been following those quite nicely to within about 5 nanoteslas.
Great.
Okay. Very good. And we thank both Dave for his presentation and his work, and Jules for their work too. So I think we're out of time for questions. If you want to hang around for the break, we can do more then. So I guess we'll turn it back over to George.
We're going to bring up Eric
Westgard, INY90,
Westgard,
Director of Medical Communications for the Medtronic Twin Cities Marathon, as well as the Red, White, and Boom Half Marathon and the Lopet City Lakes Winter Festival. So today's topic, we're going to have really 3 subtopics: build a mobile mesh tower fleet, and then a little update on the Twin Cities Marathon and what we do there, a little bit about our mesh network, and then a little bit about our tower fleet and how we happen to have a use case for a mobile tower fleet. So the Medtronic Twin Cities Marathon is one of the larger outdoor sporting events in Minnesota. We use about 110 amateur radio operators every year to volunteer. And we're out on the water stops, we're out of the aid stations, keeping an eye on the runners, reporting in via radio injured, down runners, or any kind of situations that are happening out on the course. And the event is very happy to have live situational awareness. Those go to any of 3 voice nets. There's actually 4, but 3 that are related to what's happening out on the course. Those incidents, that information is entered into our various databases. And then we query those in a couple places. One is in the Family Medical Information Tent, where we're talking to families and helping families find missing or injured or kind of misplaced runners, and then vice versa, runners looking for their families. As well as in the medical tent up at the Race Operations Center. And then obviously out at the net control stations, we're trying to figure out what's happening. And we get a lot of queries and a lot of requests from senior race officials. Hey, what's happening out at mile 16? And is there some kind of medical situation at mile 4? What's happening with certain runners? And we're able to provide that information, again, primarily focused on location. When it gets down to, okay, someone is injured, they're on the way to the hospital, then we'll normally hand the telephone to someone where they can talk over a secure line for information that's related to HIPAA information and specific medical treatment, et cetera. And the data, there's a lot of data here. We have 14, 15 laptops going. We're doing live updates. We've got the dashboards. Really far exceeded years ago the ability to run it over packet. Won't run over something like WinLink, just there's enough bandwidth. We were using a D-Star DD mode for many years, and now we've switched to a open link state routing protocol mesh on 5 gigahertz. 2.4 gigahertz is too congested at the finish line for any kind of usable data flow. So the doctors, really, the practice of medicine has gotten very much online. There's this notion of physician order entry, and they're used to sort of entering data in a computer. So the doctors actually went out and built an app called RaceSafe, and it runs on iPads and iPhones and Android devices, and they can actually put in a bib number and literally enter treatment and medical information. In a lot of cases, this needs to be real time. Things like, do we think someone's having a heart attack? Do we think someone's got heat stroke? And what does a core temperature of 107 mean versus a core temperature of 103? And sometimes the people out taking care of the runners can make those decisions. Sometimes they need to get higher authority involved and got to get a consultation. And if you've got a student EMT doing something versus an experienced sports medicine physician, that all flows up to the center screen, which is a dashboard. And the race medical director can be looking at this dashboard and be available to give real-time feedback on, yeah, I think that's the right thing to do. Put some ice towels on them, throw them in the ice bath, call a rig, do a transport, things like that that are very interactive and very data driven. And then we're allowed to use the RaceSafe software. In fact, we were put in charge of training everybody on how to use it. It's cloud-based, and then we also have a backup system that we use. And we've been working with the RaceSafe folks on trying to get some updates and making it more friendly to our volunteers. So the software we wrote is called TrivNetDB. It was ported years ago from the old Aries data, but it's basically keeps track, first name, last name, bib number, which also could be a phone number, and any sort of status information. We're not keeping track of medical data, but just where are they or what's happening. Hey, they got on a bus, they entered the med tent, they left the med tent, etc. And when the race officials, the senior ones, come running in and saying, hey, what's going on at such and such, or we can give them status, we can say, yep, they entered the med tent, they left the med tent. And then, we have a pretty good idea, they got on a SAG bus, etc. We have a pretty good idea of where people who are having situations are. And this is really important, this notion of situational awareness. And we're getting pretty good at helping families find their runners. Like, hey, my mom was supposed to finish an hour ago. Where is she? Is she in the medical tent? Is she dying someplace? We go, no, your mom got on a bus an hour ago, and the bus drop off is 2 blocks, and she's scheduled to get off the bus in 12 minutes. Though that's the kind of information we can provide. And the race is very, very happy with that. The families are happy with that. And it gives us a good feeling of accomplishment. We're out really helping people to reunify with their families. And you can see the use case of this in a disaster. So we really move a lot of data around, and we've got requests. We got a formal request a couple years ago for live video. The start line is about 9 miles from the finish line. The start line is over in downtown Minneapolis. The finish line is in downtown St. Paul. And they, the race officials are mostly at the finish line and wanted to see what was happening at the start line in the corrals and the pens and the start area, et cetera. So we got to work. We've been playing around with mesh since really 2011 and got the idea to build a city-to-city dish backbone link. And we needed approval from our local senior medical officials who are also affiliated with the hospitals. And they asked the question, if we give you this access, is it going to only be used by ham radio operators, or can we use it? And I looked them in the eye and said, well, we'll let this mesh network be available for first responders to use. And they said, fine, here's the person's number, go make it happen. So now, in truth, we'd made the decision 5 years ago or 10 years ago to use Part 15, but that turned out to be the right decision. Now, this has led to what I call the revolt of the COMLs. Our local COML community, especially the ones affiliated with some of the counties, got really irate and said, hey, look, this is a private closed network and it's not ham radio, and what do you think you're doing? And they got a little cranky, and we'll tell you how that sorted itself out. So in the January of 2020, I got a call. I'd given a talk on a medical panel down in Orlando with some other large marathons, and the individual from the City of Lakes Lopet Festival, who was right in Minneapolis, was there, was looking for some help, and we didn't really know what the help was. We met with them, and it turns out, we offered, three choices. We had medical command center, we had missing persons and family reunification. He said his #1 requirement, and this was the medical director as well, is getting care to runners who are down on their 42-kilometer course. So the course is, it's through the woods, it's in golf courses, it's, it can be far away from roads, and we needed to find out who was down, what was happening, and are we getting, evacuation, are we getting, EMTs to the scene, et cetera. So I rounded up some hams, and unfortunately the race operations center was in the back of a ski chalet. It's really quite cute, and as you can see, there's a little bit of a hill in the background here. For us, Minneapolis, that's a good sized hill. I was worried about repeater coverage with the hills around, so I looked for a tower trailer. Our one was stuck in the back of a storage barn full of RVs and boats, and the other was literally frozen in 200 yards from the nearest road. I asked a local government agency who had one, and they said, no, you're not a government official, you're not a government agency, and essentially go away. Well, we went out online and did a search for tower trailer, and the search engine kind of turned that into light tower. And a light tower is a device used by construction companies, job sites, for providing light. Normally has a 30-foot crank-up tower, a 6-kilowatt, 2-cylinder diesel engine, and will provide usable lighting in the area of 4 to 5 acres. Now, we found one in a cornfield for $700 at this time of year, and it was missing its lights, and the engine was broken, but the price was right, $700 bucks. So N0NIS, I told him about this, and he took pity on me. I don't have a tow vehicle. They weigh about 3,000 pounds, agreed to go fetch it. And we brought it home, and we kind of had this idea, this sort of 1.0 vision, where we'd put some deep cycle batteries, we'd fix the engine, put some dual band or tri-band antennas up there, some mesh antennas, and we'd have ourselves a mobile asset. And we started working on it. By the way, the biggest source of these in terms of online purchasing is a website called ironplanet.com, and there's usually hundreds of these on sale, and that are at an auction. You can also kind of get these at retail from equipment dealers, and the prices vary all over the place depending on the laws of supply and demand. And right now the prices are quite low. So we had this idea, okay, we're going to fix the engine. Well, I had this idea, I'm not blaming Doug. So I said, what can be wrong? And the initial symptom was, we had some wiring problems, and it didn't have any fuel to the injectors. And I said, well, we can, deal with that. We just need an injection pump. So a couple $100 later, one of those came, and then we've had problems with the throttle and the governor, and that was missing a spring, and how it can be missing a 3-inch long spring inside the engine is mysterious. And then the injectors didn't look good, so we replaced those, and then took the cylinder head cover off and noticed one of the valves was stuck, and so did a valve job. And in the final analysis, took the cylinders apart and discovered that the cylinders were worn beyond tolerance. There was no compression. So the answer is, was there engine trouble? Yes, there was, and we spent a lot of time on engine work. Well, if you got one trailer that you kind of like, and why not get a second one? Really was no use case, but we thought, why not? Found another broken one. This one was quite a bit larger, had a Lister Petter diesel in it, which is also used in military applications. This one was water cooled, and the symptom was didn't start, no fuel pressure. I said, well, we know all about injectors now. We'll get ourselves some injectors, and we'll play around with that. So I started working on that and came home. The governor assembly, and this one was also broken. It was held on by a tie wrap. We had, various problems with tires and bearings and rusty lift cables and broken jacks and glow plugs. And I think actually this one may have had cylinder wear as well. So we spent a lot of time on engines, but also, putting on antennas and thinking about DC power systems. So we had our debutante party really for these at Field Day 2020. So we got a call, and we were going to kind of sort of have Field Day. Many of the people didn't show up. The normal providers of towers didn't show up. And I said, well, can I come to the Field Day? And they said, well, I'm going to bring in a couple of towers. They go, good, you're in charge of towers. So we brought two. And the first one got a coat of black paint, and it actually got a code name, Orange is the New Black, which we're not allowed to use because of trademark, but you get the idea. It used to be orange and now it's black. And it has a 6-meter beam at the top, TV rotator, and some mesh. And then the yellow one, which never really did get a code name, drew the short straw and had to carry the full-size tri-band beam. And we also ran a G5R feed between them. We parked them about 120 feet apart. And we ended up with about 5 dipoles on each one, various things. And then we decided, even though the diesels were not working, either one, that the 1,500-pound diesel made a some good ballast for holding up tri-banders. I think the impression was good. These set up in about 20 minutes, and they really worked fine. And we even bought a little propane generator for the black one, and it provided power to a field day until one of those nice motorhomes showed up with a built-in diesel or a nice, quiet, high-powered generator. So the word got out on the trailers, and we started buying more of them. And then we found a couple at an auction that literally had the engines removed and had radio antennas on them, solar panels. We couldn't figure out what that was up, but these were very, very cheap, a couple $100. So 3 more were purchased, and also came up with the idea that these should travel in convoy. And then, by the way, if you're storing these in your driveway, they will fit in a garage. If you're storing these in your driveway, normally you can't store construction equipment in a residential driveway, but if anyone, the neighbors ask, is it a barbecue smoker? The answer is yes. And then I think you can store barbecues in your driveway. So the current status of the tower fleet right now, we have 8 right now here in Minnesota, and the first one is on the left. And you can see we've added a bunch of antennas, and we've got a little bit of a solar panel in there. So we've got our 5 gig mesh antenna, the Part 15 mesh, and then we've got we finally got the ComLs, calm down, and they spit out a couple of radio channels and a bandwidth, which is all you need to set up the ARRL system. And so we said fine, and Peter, who's my software engineer / network engineer, had a couple of the Ubiquiti rocket radios in stock. So we programmed for the ARRL, and we just bolted them on the trailers, put them both on there. We showed up at the event, cranked them up both up to 30 feet. The ComL saw the ARRL signal and were happy. So the problem was solved, and the revolt was calmed down. And the thing with these is, if you don't agree with the local network standard, at least follow it. And in this case, we just put power to the radios. We put antennas on them. We tie wrapped them to the tower, and you don't have to make them interoperate. You can put an air gap between them, and they just get power, and power is fine. And you can't transmit malware over power, so we're good. Pan, tilt, zoom cameras, these are good. Our friends at the Hennepin County Sheriff's Office have been having a ball with these in terms of being able to tilt and zoom. I kept a couple of lights on the green one. The green one is called the Jolly Green Generator. This one we got at a very good price. Note the bent axle, I think that was why. And the 6 kilowatt generator is running. And the first use case for these was a tree down next door to my house, and it was handy to have the idea of lights and power for electric plug-in chainsaws. So we're keeping a couple of lights on these. In fact, I'm putting lights back on the original one. And then the idea is to find a sturdy pipe mount at the top to put beams or large antennas, like a 16-foot long GP9. If you do the math, 30 feet plus 16 feet is pretty good for the tip of your antenna. And then 2 big gig mesh, etc. We've even got some snazzy decals and little decals for the tactical / code names. And again, the use case for these is, one of them is video / mesh aggregation. This was an example that we did. The Hennepin County Sheriff's Office did with 2 of their command trucks and our mesh antennas. Well, actually, and then 3 portable mesh cameras. We were doing the Klondike Dog Derby on a 15,000-acre urban lake outside of the mesh backbone area, so we had to bring our own backbone essentially. And the idea is, if you can see in the top right, there's a little dog sled team, and actually right after this picture was taken, one of the dog sleds broke down. There was some kind of problem with a harness or whatever, and the race organizers were asking, "Hey, what's going on? And we were able to zoom in with the camera and spot that they were having a problem with a harness with one of the dogs. But the idea is the mesh can provide the video to a command truck. The command truck can aggregate the video, or in this case, pump it out over YouTube, which is then available to people with mobile devices, tablets, EOCs, etc. So this is one of the use cases, and you can if you have enough trailers, you can have one big event. You can have a couple of little events, and they can be anywhere in the state. So the idea of having a tower fleet, again, we've got 8 right now, and I came up with some proposed, I'm calling these silly rules because I'm trying not to be too serious. And the idea, for example, is the trailer should have a cute tactical name or color. Get your kids to paint them. The model here is the van from Scooby-Doo, right? The idea is we're not from Homeland Security. We're not trying to pretend we're from the government. This is really a spontaneous volunteer rescue operation, more like things like the Cajun Navy or Telecom Sans Frontiers, that we're just out helping people. And then the idea is you want to test them with the local mesh standards. And if you don't have mesh standards, establish them. If you don't like the mesh standards, if you think they should be changed, the idea is just put up antennas and tie wrap them on, give them some power, and you don't have to, mess around with people's networks. Just provide support. And a mesh antenna at 30 feet is a worthwhile thing just to bring them out there. And then we're trying to have a pretty good response time. Essentially, these are plugged in on worm standby and can roll pretty fast in terms of being able to get to a scene without saying, oh my gosh, it's going to take 6 hours to find where I put the antennas and where I put the coax. I like the idea of them traveling in convoy for a little bit of a visual effect. And then the idea is that we want them to be cheap and abundant. We want them to be inexpensive. And a lot of the guys that said, hey, I've got one, it's got a generator, I'm going to power my house. If there's a power outage, we'll say, well, what if there's an emergency 16 miles away? So a lot of us are talking about getting more than one, and you can have one at the house and you can loan a couple out. And we even found some epic call sign decals for these. So kind of the moral of the story here, I think a little bit is we want to take a new look at public service for amateur radio in 2020. And the idea is waiting around for government radio systems to fail, really at the end of the day, boring, right? If you do the math, reliability math, and I'm kind of an expert on this, if you have 2 or 3 99% reliable systems that are reasonably parallel, they're not all using the same infrastructure, they're all not using the public internet, or they're not all using the single Ethernet provider, but if they're reasonably separate, the odds of all 3 failing other than being leveled by a hurricane are pretty small. So I think this backup communications, when the cell phones fail model, I think is becoming sort of old hat / uninteresting. So the idea is hams are embedded in agencies and providing really more of a direct service. So family unification, weather spotting, duties as assigned, IT support, food distribution, whatever. We're adding value. We're helping people directly, essentially. And then we've got assets. And I think, one of our most cherished assets have been the Go kits. Well, Go kits aren't welcome anymore. You ask the Boston Marathon, hey, can I bring a black backpack full of, random radio equipment, my FT817 and my NBIS antenna? That would be a no. The NFL doesn't want to see your backpacks. So we really have to rethink that in terms of shared assets, mesh nodes, infrastructure, fixed infrastructure that's already there. And then I'm arguing probably pushing up a rope here, that a ham license is a valid credential, right? It's in a database. You can look it up. It matches your driver's license. You know, a ham license can't be issued in real time. If you decide to go out and start a riot and say, oops, I'm going to go get a ham license so they won't bother me, you know, that all takes time getting your ham radio license plate. And I'm really reject the idea that unwanted volunteers are a problem. At my events, I only want unwanted volunteers. And this really leads us to an engagement and a maturity model. Those of you who are in IT, you know, we've heard about maturity models, and I would argue something like a integrated volunteer emergency management is really the highest level we can be. We're part of the organization. We're tied in. I know I talked to my agency, the Marathon, just last week. They're having a rough time because so many events are canceled, and they're all about, you know, hugs and high fives and, you know, people out getting fit and running. And their first question to me was, hey, do you know any bike medics? Because they're starting some very, very small events. So I could say, well, you know, that's not ham radio, but I happen to know the bike medics, and I gave them the list, and they're really happy. So the idea is, are you part of the solution, or are you kind of, you know, fighting with the old model here? And things like, you know, backup communications and, you know, providing a backup POC. Yeah, those are important, but those are not, you know, mathematically probable things that we're going to have to do. And then really the notion of an agile model. Are you understanding your served agency? Are you using your skilled volunteers to model what you need to do? Are you executing flawlessly? And then are you measuring results, and you're improving and trying to be better and better every year? Well, thanks for the time, and hopefully we'll have a few questions.
Okay, thank you, Eric. Are you there, George?
I am here, and so is Eric, I believe.
Okay, yeah, and I see I have one question here. Dave Seidel at ARRL Legal Counsel is looking for documentation of the ARRDN network providing emergency comms for the 9-centimeter band. I don't think you mentioned that. I think that's 3 gigahertz. During recent hurricanes and forest fires, this is a last-ditch effort to save that band. If you can provide any input, that might be helpful to them. So I don't know if you have any comment on that band, or
we could use 3 gig. We just have not. We have severe spectrum congestion at 2.4 in the Part 15 band. It's actually useless during big events due to all just the background noise floor gets really high. But we haven't used 3 gig.
Okay, and I see you answered the first question about what kind of radios are you using? ARRDN?
Ubiquity.
Ubiquity?
Yeah, we really like Ubiquity radios. They've been just lovely.
But you did say you used pre-ARRDN homemade OLSR mesh networks. Is that? Can you expand upon that?
Yeah, one of our served agencies actually complained there was apparently some infighting in one of the groups, and Peter just, you know, loaded up OpenWrt and loaded up OLSR, and we sort of built our own mesh. Essentially, it looks just like ARRDN, but it's homemade, and it's actually compatible, but it's our own version. And we picked Part 15 because that was what our served agency wanted. So it's ham radio administered Part 15. But we've kind of switched over to ARRDN, and our local ComLs are suggesting we use channel -2 and channel, I think it was 180 for that. So we're going to be kind of switching over to ARRDN for all intents and purposes here in Minnesota.
Okay, and there's another question is, could you explain what is the relationship with the existing mesh network and what you mean by, quote, putting up a mesh antenna with power, and what problem of interfacing that solves?
Yeah, the whole issue, you know, and this is a great debate if you have, you know, 12 hours, is the whole, you know, Part 97 and crypto debate, right? And so our position was, we're on Part 15, we support crypto, we support, you know, if the doctors want to run, you know, HIPAA, that's fine. And then we're going to just basically air gap the ARDN. And the ARDN is we give it power, you power it up, and if it's on a separate, you know, separate Ethernet switch, right? We're providing service to the ARDN people, but we're not interoperating with it. So that's the idea. So we essentially have 2 networks. And actually, from a redundancy standpoint, having 2 networks is more reliable than having just one. And if one of them gets hacked, ours is not on the internet, as an example.
Okay, and another question. Do you think extensible mass trailers are superior to dedicated comm vans?
Oh yeah, in about 3,000 different ways. The ours trailers cost $200 to $500. Insurance is $16 every 6 months, and so they're so much cheaper. The comm vans are great if you have 4 or 5 guys you want to pack in there and have workstations, but we you know, that's kind of unpopular these days. So
okay, and oh, sorry.
Yeah, so they're an order of magnitude cheaper, and you know, how many comm trucks have 30 to 40 foot antennas on them?
Yeah. Another question from YouTube is he said that he likes he'd like you to comment on the cute names and colors for the towers, and kind of suggesting let's not be the wacky or hams. Don't know if you have a comment on that or not.
Well, okay. In full disclosure, Peter, my network guy, insists that IP addresses would be more sensible names for the trailers. So that's, but the cuteness, we're trying to be, I'm from Minneapolis, I'm trying to say we are not impersonating Homeland Security here. So these are, the idea is when they see it, and you know, if your kid painted it, you know, clearly these aren't government assets. We're here to help people, and we're not. I'm trying to be a little fun here, if that makes sense.
Yeah, yeah, and you got several kudos on YouTube. They really liked your presentation.
Oh, thank you.
So how are we doing for time, George? I think we're about up, unless there's any other questions.
You were at 30 seconds.
Oh, the question on what traffic goes over Arden. So Arden is, and I don't know what traffic's going to go over Arden. That's up to the ComLs. But my team says the medical stuff and anything, you know, that's for example, one of our agencies is using it for hostage negotiations. That clearly goes over the Part 15, and we can run all the crypto we want.
And one comment here is that he's volunteered for a number of events over the years, and he appreciates the ones organized by grown-ups. So.
Thank you very much.
All right, thank you. Back over to you, George.
Welcome, I'm Rob Froney, KL7NA.
Hi, I'm Caleb Freilich, and I'm a senior electrical engineering and mathematics major at Walla Walla University.
I'm Conrad McClure, a senior engineering student at Walla Walla University with an electrical concentration, and also the president of the Walla Walla University IEEE student branch.
Hi, my name is Joshua Silver. I'm one of the engineering students who had the privilege to design a software-defined radio for my electronics class at Walla Walla University.
Hi, I'm Jordan, and I'm also a fourth-year electrical engineering student at Walla Walla University.
Last spring quarter, my Engineering Electronics 2 students at Walla Walla University were all online. Classes were virtual. They were all at home. This class always includes a big design project. So last spring quarter, my students in teams of 2 designed and built, literally homebrew, software-defined receivers of the QSD variety. Today we're fortunate to have 4 of my students here to describe, give a trailer essentially of their paper, which includes a simple theory of how a QSD receiver works, a comparison of 4 different QSD receivers, and a host of tips and tricks and lessons learned when they designed their QSD receivers that should be of interest to anyone doing anything similar in the future. With direct down conversion, DDC software-defined receivers becoming so popular these days, you might think that the QSD variety is old-fashioned, you know, kind of like the soft rock. But it's enjoying a surge in popularity thanks to Guido, PE1NNZ, and his QSD transceiver design. If you haven't seen his design, you really need to check it out. It's open source, it's on GitHub. It features 123 dB blocking dynamic range, 50 dB opposite sideband rejection, a final amplifier that's Class E, very efficient. This thing runs on single sideband and the other modes. And the whole thing is done in an Atmega 328p running at 20 megahertz. Recently on groups.io, a posting said of one of the SMD versions, quotes, makes a KX2 look positively elephantine. The work my students did on their receivers is directly applicable to transceivers like Guido's, and I'm hoping this group will benefit from my students' hard work.
We're going to dip into the theory first so that we get some terms and basic understanding set for what the paper goes over. We want to make sure that we all have a basic understanding of mixers and quadrature signals. Once we understand that, we'll be able to figure out what I consider to be the hardest line of the title of our paper, using quadrature sampling downconversion, which just sounds like a bunch of techno mumbo jumbo if I've ever heard it. In our paper, we use an analogy for talking about mixers and quadrature signals in a way that most people should be able to relate to. If you've ever seen a video where the propeller of a plane starts up, you may have noticed that it appears to spin in one direction, stops for a moment, and starts spinning in the other direction. This phenomenon, and the reason it happens, works well as an analogy for what we're doing. So in our example, let's take a single blade of a propeller as it spins. We're going to do two things with it. We're going to set up a camera to take pictures of the propeller at a rate that we set, and then we're also going to plot a graph of the vertical position of the tip of the propeller as it spins. In this example, we'll spin the propeller at half a rotation per second and take 3 pictures per second. The line on the graph plots the vertical position, and the small images along it show what the camera saw. So let's look at the resulting images. If we flip through our images at the rate we took them, similar to a flip book, the propeller would appear to spin. From these images, it takes 2 seconds to complete one rotation, so we would conclude the propeller was spinning at clockwise at half a rotation per second, which it was. There are 3 interesting cases to consider regarding the rate of the camera. If we took pictures at the same rate the propeller was spinning, the propeller would appear stationary when we flip back through it, reaching the same position at the moment we take the picture each time. If we took them slightly slower, the propeller would get all the way around and then a little bit further before we take the picture. When we flip through, as we can see in the small images here, it would appear to turn clockwise slower than the real rate. Here, 0.2 rotations per second. And then similarly, if we took pictures slightly faster, the propeller wouldn't quite get all the way around. And flipping through afterwards, we'd see the propeller moving slowly in the opposite direction, as we can see in the little images here. Here, counterclockwise, opposite to the real thing, at 0.2 rotations per second. So that's where we get the phenomena from a video of a propeller. The propeller starts spinning slower than the camera, reaches the camera rate, and then exceeds it. And so we'll go through those 3 stages and we'll see that slow down and stop and reverse. So that brings us to mixers, because a similar thing is happening. Put it simply, an ideal mixer takes 2 sinusoidal inputs and will output a signal that contains frequencies of the sum of the input frequencies and the difference of the input frequencies. The latter of the 2, the smaller one, is the one we're interested in listening to. And this new, slower frequency is known as the intermittent frequency. This change from a fast real rate to a slow apparent rate is where our paper gets the down conversion in the title. We're converting a fast radio frequency down to a slow intermittent frequency that our sound card can process. To connect with our analogy, the propeller rate is equivalent to a radio frequency, and the camera is a local oscillator, which sets our sampling rate. And from sampling the radio frequency at that rate, we'll come up with an apparent intermittent frequency. That is the difference of the radio and the local oscillator, RF minus LO. So there's 2 issues we're going to run into that we have to overcome: images and harmonics. So for images, an important note regarding them is that if a radio frequency is lower than LO, remember RF minus LO, The resultant frequency will be negative. A negative frequency here can be considered to be identical to the positive counterpart. At least on its own, we can't tell the difference. So if we pick up two frequencies that are the same distance frequency-wise from our local oscillator, both will appear at the same intermittent frequency after the mixing. So we need to be able to reject the undesired image frequency so that we don't hear two stations at once. With our propeller, we can see this if we take images at 1.2 times per second and then have two propellers, one spinning 0.2 slower, one spinning 0.2 faster. After our image taking, we can see that the vertical apparent trace looks exactly the same, and the only way we can tell the difference is because of our camera, where we can see the top one is turning at a negative counterclockwise rate, and the bottom turning at a positive clockwise rate. From this, we can conclude that if we want to be able to tell the image and desired frequency apart, we need to track the horizontal position as well as the vertical. That way we'll see that same kind of rotation. So here we get into quadrature signals, which are simply two signals that are out of phase from each other by a quarter of a cycle. If we track both the horizontal and vertical positions, we'll see something like these here, where despite the rotation direction, the vertical position remains the same here, but the horizontal position below is mirrored. Because of this, the stationary vertical graphs are called the in-phase component, and then the bottom two are the quadrature components, because they are a quarter of a cycle out of phase with the in-phase one. So if we put those two on the same graph, that can be seen easily. On the left, we can tell whether it's a positive or negative frequency based on the order of whether the horizontal and vertical traces reach, which one of them reach their peak first. With the propellers shown, reaching the upmost and rightmost positions in that order will mean it's clockwise, and the reverse will mean it's counterclockwise. Putting those all on the same graph, all three iterations, on the right here, we can see that a quadrature signal will lag the in-phase for a positive frequency and will lead the in-phase for a negative frequency. Knowing this, the software-defined radio can determine whether it's looking at a positive or negative frequency, the desired or image frequency, and choose whether to play or reject that audio. Okay, now the other big issue is harmonics. There are an infinite number of harmonics that will create the same traces as the one we're intending to listen to, as can be seen here with one example where 5 and 9 rotations per second, when capturing at 4, will get that exact same apparent trace, and quadrature signals aren't going to help with that. This is actually the part where I'm going to tease you, because the reasons for this and how we must address it are left in the paper. That way my teammates will still have time to talk here. If this section went a bit fast, I certainly recommend giving the paper a read, as we've broken things down a bit slower and in more detail here. So now I'll turn it over to Caleb, who's going to go over the designs we discussed in the paper.
Let's look at the highlights of 4 different QSD receiver designs, 2 by student teams and 2 by our professor, Dr. Rob Ferroni. We'll run through the designs quickly, highlight their main feature, and then take a few minutes to compare design differences. The main feature of Design 1 by Caleb and Conrad was the instrumentation amplifiers that took the difference of the quadrature signals from the Talo mixer. Jordan and Josh's design used a differential amplifier and had switchable bandpass filters for a wider overall range of frequencies. Our professor, Dr. Rob Ferroni, designed circuits 3 and 4, the distinguishing factor of Design 3 being the use of a doubly balanced sampling mixer. The highlight of Design 4 is the ability to do digital signal processing right on the receiver board. This design follows Guido Tendol's QSD transceiver design. However, Design 4 is only a receiver and has provision for porting the code to a Blue Pill STM32 board. Let's compare these key design differences. First, the bandpass and low-pass filters. What separates different bandpass filter designs? Quantity and type of filter. Design 2 uses a switchable Bessel bandpass filter with 4 bands, which improves performance by better eliminating spurious signals and reducing the overall noise, whereas Design 1 has a fixed bandpass filter. The pure minimalist, however, would avoid using a bandpass filter at all, as in Design 4, which is easier to make, maintain, and fit on a small board. While a bandpass filter is optional, the low-pass filter is essential. It guards against aliasing and sets the bandwidth of the received signal. The designer can choose the number of poles to use. In designs 3 and 4, just a single pole of filtering is seen on the op-amps after the mixer. However, an extra pole of attenuation is obtained from the sampling capacitors, functioning as an RC low-pass filter with the resistance before the capacitor. Design 1 and 2 used a separate second-order low-pass filter in addition to the pole of attenuation obtained by the sampling capacitors to improve the modularity of the design, achieve slightly better control of the filtering, and split the gain across multiple stages. Generating a local oscillator signal can be accomplished with a Johnson counter. By using two D flip-flops and a clock input, the gray code sequence 00, 10, 11, and 01 can be obtained. This approach was utilized in the first 3 designs. However, in design 4, the capabilities of the SI5351 were exploited, and using the EtherCAT Arduino library, the same sequence was generating using just 2 clock outputs. It's slightly more programming, but it saves money and precious board space. Many different mixing topologies can also be used, but our designs utilize just 2, the sampling mixer and the Talo detector. The Talo mixer is very similar to the sampling mixer, but samples at 4 times the local oscillator frequency and only produces the difference frequency between the RF and LO signals. Our research, here cited in a quote by Michael Sower, shows the Talo mixer to be one of the most effective mixers available. Our designs helped to validate this, as the image rejection was nearly twice as many decibels in designs 1, 2, and 4 as it was in design 3, which utilized a sampling mixer. The difference in amplifiers really all comes down to input impedance. The input impedance has a great impact on the whole circuit. For instance, a large input impedance allows the sampling capacitors to hold the charge longer and makes the amplifier resemble a voltage amplifier rather than a transresistance amplifier. The high impedance input of the instrumentation amplifiers of design 1 is due to the internal structure of the amp and offers several key benefits. 1. It isolates and decouples the circuit into modular blocks, allowing for easier understanding, diagnosing, and testing. 2. It removes the antenna impedance from the gain equation so that only one resistor sets the gain. Now, granted, instrumentation amplifiers are very pricey and fewer options are available. A differential amplifier like that used in design 2 is cheaper, and in our testing, we found the performance of the 2 amps to be fairly comparable. Design 4 doesn't take the true difference of the quadrature signals, but instead amplifies a linear combination of the 2 inputs. Thus, the gain across the non-inverting path is not the same as the gain across the inverting path. R18 and R19 are included in some designs to make the system more symmetrical. However, they have no effect on the operation of the amplifier, other than adding a little noise, so they are replaced with wire. Here's a table of the critical performance data for each of our designs as compared to the soft-rocked RX-TX receiver.
To prevent any heartbreak during the design and build process of your SDR receiver, we wanted to share with you a few tips and tricks we found very valuable. Tip number 1. Simulate your circuit first, then build after. This will save you tons of time and troubleshooting in the long run. The portions of the circuitry we highly recommend simulating are the mixer and amplifiers. We all used LT-Spice for our simulations, and a sample of what your receiver may look like being simulated in LT-Spice is shown here. This is my simulation, and I wanted to point out a few things to look out for when you do your own. First, looking at the outputs of the amplifiers. We are ultimately looking for 2 sine waves that are 90 degrees out of phase, because that's what gives us our image rejection. Another thing to note may be the clarity and gain of the signal. If I click on the output of my second set of op amps that I'm using as a low pass filter, you can easily see the difference between the signal before and after that low pass filter. As mentioned earlier, there are many different topologies to choose from, but you have to be careful with your simulations based on the topology you choose. It may not only affect the final output, but also the output from the mixer. The output of the mixer should typically take this form, provided that no load is attached to the output. But if we attach our amplifiers, we get an output that looks like this. So it may seem like an incorrect and surprising result at first, but if we do circuit analysis on the differential op amps, we discover that this response should actually be expected for this particular circuit.
To streamline our design, my partner Jordan Watkins and I decided to use surface-mounted components. To do this, we used a budget toaster oven to manually simulate a temperature profile to reflow solder paste and adhere our components to our circuit board. This allowed us to use cheaper components, create a smaller circuit board, and use components that have more ideal characteristics than through-hole counterparts. We were able to simulate the temperature profile by using a laser thermometer and the temperature dial on the toaster oven. By looking at the graph, you can see that we set the temperature to 325 degrees Fahrenheit for a minimum of 2 minutes to properly wet the solder paste. Then we can ramp up the temperature to be above 425 degrees Fahrenheit for up to 25 seconds in order to reflow the components. After reflowing the components, we can then open the toaster oven to quickly cool our device back down to ambient temperatures. This method proved to be very effective and repeatable in testing. It's important to mitigate ground loops in our designs, as ground loops can cloud the signals we are trying to listen to with noise. A ground loop is formed when there are two ground connections between a component and the ground plane. There are a few methods that we can do to mitigate this. Firstly, it's common practice to fill in all available circuit board space with a ground layer that serves as one reference ground. Another method to reduce ground loops is to add jumper cables that can isolate ground to one path by manually breaking the loops being generated. And finally, in design 2 and 3, we used a 1-to-1 transformer that was able to reduce our input noise by an additional 20 decibels. Using a combination of these methods in our designs yielded very positive results. When designing the board's layout, it's important to keep a few things in mind. It's a good idea to include a prototyping area on your first revision, as it's not uncommon for your circuit board to not work right out of the box. As previously mentioned, it's important to create a ground plane. In addition to this, it can be helpful to solder sockets onto many parts to easily change or replace components. It's important to separate digital from analog components, as the digital signals can generate noise on the analog signals we're trying to listen to. Lastly, test points. Being able to test and probe specific components on dedicated pins on one area of the board can make troubleshooting your design significantly easier. It's been the most useful addition of our entire design, and I would never design another board without them.
To sum it up, designing and building SDR receivers is fun, and what better way to advocate for electronic education and advanced radio technology than with something that is fun? We hope that the work we've done helps engage a larger audience in designing and building quadratured sampling down conversion SDR receivers.
Well, very good. That was excellent. We got some comments. This was the best explanation of quadrature detection I've ever seen. I wish I'd seen this years ago. And one question I had on that last slide, I saw some flying leads next to your inductors. What could you expound upon that? Was that some rework, or was that actual inductance you added, or what was that?
Yeah, I think that was, I had wired my bandpass filters incorrectly, so I had to rewire them.
Okay, very good. So now you're an expert in soldering jumper wires on.
That
right?
that never happens. Never.
Yeah. So very good. So you got firsthand experience in fixing something that you did wrong. That's good, because like Steve says, it never happens, sarcastically. So we all know that it does happen. So you have to be experienced in fixing that. And do you want to comment on test points, adding test points? You have a comment on that? If you did you use them? Were they great? Were they a pain in the neck? Did you wish you didn't have them? What, all the above?
I used them all the time when I was doing the testing. Yeah, I had, so Dr. Fernie recommended we had 2 ground points, and then I soldered a wire across it. So then when we used our oscilloscope, we just clamped that onto the wire there, and then you can use the probe part in the test points, which made it super convenient to use.
Super easy. people that complain the most about test points are the CAD people who have to put them on the board, right?
Who did the CAD work?
Yeah, did you all of you lay your own boards out, or
was it each of you individually doing your own board, or did you guys collectively work on the one design?
So we had, between us, at least the students, we had 2 different groups of 2 students. So it was me and Caleb, Jordan and Josh. We did all lay out our own boards, but we actually only fabricated one from each team.
so what tools did you use for layout?
We used KiCad. Yeah.
Very good. And you use one of the quick turn prototype houses to get your boards built? Yeah, Caleb, you're muted, so.
Yeah, we used JLC PCB in China, and for me at least, they returned my boards in less than a week. It was really incredible.
And they're in China?
That was quick.
Yeah, yeah. It was incredible.
Yeah, most of them will FedEx them, or if you want to pay extra, on that. Yeah, it's a great world to be living in today. When I was your age, it was using ferric chloride on some boards in my kitchen, and I made the mistake of I needed a bigger dish, and instead of getting a glass dish, I was like, oh, I'll just make this out of tin foil. And the ferric chloride attacked the tin foil, and I had ferric chloride everywhere.
Did you ever get the one design where you put the aquarium bubblers in the bottom to make the ferric chloride?
Oh yeah, all those tricks make it warm, vibrate it, bubble it.
Yeah, but you know what it also does is it gets ferric chloride everywhere.
Well, I'm really happy to see the students learn what they did, and not have to do chemistry.
My best trick on etching was to use marbles so that the precipitate that was etched off fell well away from the board, which kept the etching process active.
Yeah, but see, now we're in the 21st century, so we have experts to do these boards from China, who is a half a world away, and you get your board back in a week. So I see that Jordan had to put wires on her board. So were all the boards? How many of them had to have wires put on them to make them work? And did everybody get a chance to experience the magic of rework?
Yes, absolutely. We actually, my board ended up going from just a single board to a board that was going to a breadboard that was just like pulling out of jumpers from various points where we completely forgot. We completely missed a part of a chip that needed a good current source, and so you wired on that completely off the board on its own little breadboard.
So you had a 2-board set then? Kind of. Yes. You had a 2-board set. You wired them together.
Yeah. Exactly.
Now, how did you guys test your boards? Did you hook up an antenna to them? Listen to a radio station?
Yeah. So that Michael Bublé clip at the very beginning, which I realize now we didn't even address in the actual presentation of why that was there. That was a signal that I picked up from my board from Florida. So it was all the way diagonally across the US. And yeah, I actually just took a long strand of wire and threw it on my roof and thought of myself as a radio expert.
Well, and kudos to you again. I mean, again, for a lot of us, our first experience that was with a crystal radio.
Mm-hmm.
And here you guys made a very modern software-defined radio on that. I see Josh Silver joined us. So Josh, you got some comments about your experience?
It was, I mean, in general, sorry, I haven't seen the comments.
Well, the comments are generally very, very good. I mean, you guys are getting all kinds of kudos, especially for your presentation. There's a lot of folks really excited with, how that you show and cue. And I compliment you all for it's clear to us you guys went through a lot of effort to make that video. That is not something you just throw together.
And were all your boards 2-layer, or were some of them 4-layer, or what?
I believe that all of them were 2-layer. because I believe that was the cheapest method to go about it from ordering from all the way from China.
Okay. Well, very good. So I guess another question, maybe at the beginning, and maybe you talked about this, but did you all kind of start? I know, I think it was Josh who had the first set of presentation, and you said, "Well, we're going to learn these things." No, or it was Conrad. That was you. And so you kind of all got together and worked on that together, and then you split apart and went your separate ways to make your own receiver designs. Is that how it worked? So then really you each picked your own parts and you each made your own schematics then after that.
Yeah, pretty much.
So how did you find the experience of picking parts and reviewing data sheets? Was that daunting?
Oh, that was the best part. Oh, I wish I could do that every day.
Sarcasm. So we got a question from Michael DK5HH. He's in Germany. What is the upper frequency of your devices?
For ours, it tops out. Ours was kind of set by our bandpass filters, namely. I'm not sure on how high we could actually go.
I think it was to like 50 megahertz.
Okay, thank you.
Yeah, it's going to be whatever your limit to your aliasing frequency, right?
Yeah.
Unless, of course, you want to receive an image. And then you got to throw your extra filters in there for that. Okay.
Yeah,
so
someone who said that they designed their board with rub-on transfers. Now that's even older than.
Yeah, let's not get into a contest of that. These four students get a lot of kudos here. So I know you guys said in the video, but while we wrap up here, so what year students are you, starting with George?
Yeah, so I'm heading into my 4th year and hopefully graduating this year. We'll see.
All right. Have you got job prospects yet?
No, not yet.
Okay. Get that resume out there, and your resume, that board, those wires on it.
You have 102 potential employers in the attendees tab.
Yeah. So Conrad, your status?
Also starting 4th year on Monday and hoping to graduate.
Okay, cool. Caleb?
Yeah, also a senior and hoping to graduate, but then heading on to grad school, hopefully.
And your graduate degree in?
I'm a senior electrical engineering and mathematics double major.
Well, that's one and the same.
It's pretty, yeah, you got it right. It's pretty much the same thing.
And Josh?
Yep, I'm also a 4th year electrical engineering major, hoping to graduate this year as well. Haven't done too much for job prospects, but hopefully I'll be getting out some resumes this quarter.
Okay, well, congratulations to you all. I want you to know you did an outstanding job. I mean, for students, what you guys did is above and beyond what most students do.
And
so
congratulations.
Look at the comments.
Everybody loved your presentation. It was very good.
And Rob, did you want to put in a final word?
Oh, I'm just really proud of these guys. It was a lot of fun for me, and kind of a strange quarter we had where everybody was online, but it's kind of that way again, not totally, but my classes are all online again this time, but no labs this time. So yeah, it was fun.
Good luck to you all. Take very good care, and we hope to see you in the future.
Congratulations. Good work.
Thank you.
Okay, so we're going to segue into another break time. And as always, I mean, of course, everyone can hang out and chat and ask questions and stuff, or take a moment to stretch. We're going to be back here at 2100 Zulu, and we got 3 more talks, and that'll round out today's set of talks. So we hope you're really enjoying the talk so far. Keep those comments in the chat box coming, and we will see you in about a half an hour. I'll put up the break slide.
And if you're an attendee and you'd like to speak in the chat room, just raise your hand and we'll turn your audio on. So I got to say, Rob and Conrad and Caleb, Josh and Jordan, yeah, I'm jealous because I sure wish when I was in school, I had a course like yours to take. Instead, I got mostly math courses that I didn't like and an awesome Fortran course, which was the best we could do in computing.
Well,
but of course, that got your hands on the computer, you know?
Well, you got my hands on the punch cards that you fed into the computer.
Yeah. The right to submit a card deck to the acolytes at the Temple of Computing.
That's right. And submit to their will.
Is this where we mentioned punching sequence cards against their inevitable shuffling of the decks?
We don't even want to go down that road.
Okay, so Gregory Raven's got a question here. He says, there was a reference to some receiver design based on Arduino at the beginning of the presentation. Can someone post a link to that?
Yeah, I'll post a link.
Okay, thank you, Rob.
So, and I bet it's in the PDFs that'll be available immediately after the DCC is over, or shortly after this weekend as well.
Yes.
So Rob, just curious, how long was this project in fermentation in your mind, and how did you get students to sign up for it?
Well, you know, they kind of have to take this class because it's required for their major, you know, so I didn't have to worry about that. But, you know, engineers have to learn how to actually do a complete design. And so, you know, the whole class, pretty much the whole purpose was to do a complete design. And yeah, it was fun. It was a bit of a logistical nightmare because I had to ship all these parts out to people, you know, and I'd miss something. And sometimes I actually end up making 3 shipments to people before they had all their parts. It was a little bit of a thing. I discovered I'm not very good at logistics.
Well, I'll bet your students are going to be the first in line to get offers from employers, because I know that with the skills that they developed over just this project, that'll be in demand, I'm sure.
Yeah, I'm really proud of these guys. They did extremely well. I was really impressed.
Is we actually, I'm an advisor for a local Explorer post here, and we do projects like this with our explorers, not as formal as yours was and as academic related. But one of our explorers told me when he got into college and he got a work-study job, he said almost all of the skills that he used at his job were ones that he learned in the Explorer post and not the ones he learned in school. So I'm really glad to see that you know, students learning this stuff now firsthand and in the university, so when they graduate they'll have experience already.
Yeah, and it's a lot of fun too.
Yeah.
And then Rob, does that class run every year?
Yeah, runs every year. So you know, the reason there were 4 receiver designs, I mean the 2 from me, was because after reading Guido's you know, GitHub page, which I will try and put a link to here. Let's see if this works. Yeah, I just stuck a link in the chat. After reading about you know, several clever things that he did that we didn't think about, I had to you know, build another new design for next year. You know, so and besides that, the nice thing is now I also have you know, Jordan and Josh and Caleb and Conrad's video to show my students, and you know, the paper that we wrote also, you know, all their efforts on that will go to help my next year's class do an even better job. At least that's my hope.
Well, I was wondering if you're going to change it up, but I guess really they still have to go through the same efforts.
Yeah, well, one problem we had this time was that a number of people had different computers. And it turned out that getting Quisk to work on Macs was not as easy as it was to work on Windows or on Linux, and I run Linux, and a lot of my students run Windows, but there were several with Macs, and I have to say Jordan is really to be commended, because she is the only one with a Mac who actually got Quisk to work, but she did, and I'm really indebted to Jim, the author of Quisk, for fixing a few things for us, and just kind of helping out with little things like that. So it was not just my class, but the Ham community was helping out. So it was great.
Well, and thanks for really sharing the experience, especially as much of the schooling now has gone online, and that gives us kind of a snapshot of what it's for the college folks. One of the things I did last year was mentor a robotics team, and just as we were going to be going into regionals, everything got shut down, and all the work that we had done had just come to a screeching halt.
Yeah, sad.
So, Rob, I think there was a question we just got a little bit ago that asked if you're, are you contemplating selling kits? Or maybe that's beyond that. That skips part of the part that you want the students to actually do, which is design and lay it out.
Yeah, there's not time for the business aspects of things, and honestly, there's still tweaks to be made to make these guys a little better. Like for example, Caleb mentioned that my first receiver only had 15 dB of image rejection, before you actually, tweak it in Quisk, and I'm still trying to figure out why that's the case. I fiddled with a number of different things that I thought might be it, but none of them tended to make him any better. So, yeah, it's it's a learning process. But the other thing about kits is I discovered that logistics is not my area, so I'm steering clear of that. There are other people who have those talents, but not me.
Yeah, and I've heard a comment saying that kit building without design is just solder practice. So it's really, you learn a lot more, especially from having to debug, like trying to find your opposite sideband problem. You'll learn so much more from that than just soldering something that already works together.
Yeah, that's right.
So Rob, you ought to find the, what is it, systems analysis people and get them signed on.
Yeah, I should get some more collaboration with some other class or something, but yeah.
Well, and that's what really I'm trying to find the word. That's what really surprised me when I was doing the robotics, and it's the first robotics at the high school level, is these kids join basically the robotics club, or it's an extracurricular class, and get class credit for it. But it's not all about turning a screwdriver, for example. They have the business people, they have to make YouTube videos. There's others that they have to make an engineering book, and there's fundraising, and every bit of this all gets graded. So kids can join up with a robotics team depending upon what their interest is.
So there's a question for the four students. If you each want to answer in turn, it's a question as to how you built your board. Because I noticed it had some SMT parts on it. The question was, did you use a solder paste stencil, or did you hand solder your board, the parts on your board?
So that one varied depending on which group it was. Caleb and I did mostly through hole, but some surface mount, and we all did it just with a soldering iron. I believe Jordan and Josh actually, I believe they got a stencil.
Yeah, we did. We got a stencil. Yeah, and then like Josh was explaining, we used a toaster oven. I got my toaster oven from Walmart for like $18, $19. So that was nice. And I made sure to label it, not to use it for toast anymore.
So you got the solder stencil and you squeegeed the paste onto the board
And
I did.
Placed the chips and then baked it.
Yep.
Wow.
Did you guys look at the solder paste under a microscope, a stereo microscope by chance?
Oh, look at it under a microscope?
Yeah, look at solder paste under a microscope.
Like all the little beads?
Yep. Little bitty round beads of solder suspended in flux.
So
no, I've seen that before. It's really cool.
So Jordan, when you baked your board, how did it come out? Was it easy? Did you have any problems getting the heat set right or anything like that?
I didn't. I looked online. Some people said like above 415 Fahrenheit was pretty good. So I just set it there and I stared at it until this solder paste was liquid, and then I tried to pull it out. I burnt some of it, but it was still functional, so I just called it good.
Okay. So you didn't have a thermostat on yours or anything, just the standard thermostat that came with the toaster oven?
Right. I just tried to eyeball it. Josh did his more technically, and his came out nicer.
So did he use a thermostat, or did he just keep an eye on it closer?
He kept a thermostat and monitored the temperature.
Oh, okay.
Yeah.
Cooking class.
Well, I still remember the one guy, and I think he was in Germany, that bought one of our HPSDR boards, and he used the toaster oven method to build it. He bought the bare board, and he sent us a picture back of this board that was charred and burnt all the way through in several places, like he had put it in, he like used a blowtorch on it. And he came back and said, well, your FR4 is defective. And we sent it back to the manufacturer, and they said that basically you would have to get up to about 350 degrees C in order to do that to the FR4. And of course, solder melts at, is about 200 and 210, somewhere in there. So that's why I always like to hear stories about toaster ovens, how they worked and what your experience was with them.
Yeah, it was a good experience for me. It was definitely a lot faster than hand soldering, because I actually had another board I did for another one of Dr. Froni's classes. I had everything soldered on there, and then I had to desolder all my 0805 SMD components, and I was like, whoa, I'm never doing that again.
So how did you do that with the oven, or did you use a hairdryer, or what did you?
Oh, I had 2 soldering irons, and I got my brother to get a pair of tweezers and pull them off as I heated both sides of it.
So why did you have to take all of them off?
I fried lots of traces, and I think I fried my MOSFET. It just wasn't working, so I just decided to move it to a different board.
Oh, so you moved to another board, okay.
Mm-hmm.
Those are called fuses.
Yeah, well, I learned about that. I was like, dang, I should have incorporated that into my design.
Well, imagine we had a board that we built once that had a combination of capacitors and inductors. Inductors in series for filters and capacitors for bypasses. And the contract manufacturer put an inductor on in place of a capacitor in one place on the board. One place. And of course, they look all the same. So how do you figure out which one is the inductor and is shorting out your power supply without doing what you did and take all of them off? It was horrible. It turns out that the inductor was a slightly different color than the capacitors. And so we figured it out that way without having to do what you did and go through the pain of taking all of them off.
That's good.
Well, again, congratulations on successful boards. One way or the other, wires or not, still success.
Thanks.
Hey, Scotty.
I'm trying to read for more questions, but I'm not seeing any. Go ahead, George.
Hey, yes. So I got an email to my Gmail account on account of my account sent out all the invites and everything for this event. And it was asking about a link to the PDF of the proceedings. And there's, I believe, a link on the TAPR website to be able to go to Lulu to purchase one.
It's on the screen right now.
Right, and if you're an attendee or a panelist, the confirmation email that got sent out to everyone yesterday and that you got if you joined later has the link for the PDF downloadable now from our Google Drive. And so if you go get that email, you can get that link and you can get your PDF right now.
That's good to know.
Hey, we tried to be sneaky, but provide the answer. It's Zoom doesn't let us provide lots of information in those things, so I had to sneak it in as like a title under the DCC flyer image.
Let's see, Dave W. got his today. I ordered my proceedings when you first published the link, Steve, and I still haven't got mine. And Tom's got his and Dave got his, so I'm jealous now.
I ordered mine as soon as we got the link, and I just got the notice that it was shipped. And
you
I
guys
know
are too far
Tom
west.
Holmes got his in the mail, but I guess we're too much further from the printer.
I thought the printer was in the west, so we would be closer. But I guess I'm wrong.
They're sending it on very slow. They probably mailed it, what at the media rate? I noticed it was saying FedEx, so they're using some sort of collective method. So Roy,
comment on the YouTube site that says, "We kids had easy bake ovens. Kids today have reflow ovens."
Yeah, that's true.
Yeah.
If all kids could learn how to use a reflow oven. Okay, Roy Gertig, you have a question there. Can we get a copy of the student's presentation, especially with the airplane simulation? So the answer is well, one of two things. George just mentioned that the link where you can go and download the PDF of all of the proceedings, including the students, is embedded in the invite, the latest invite that George sent out for the Zoom presentation. The other is we'll resend to all the registered attendees an email following up with the link.
Well, afterwards, the link will be publicly available. And if he wants their well, in any event, if he wants their video of their presentation, YouTube is streaming, recording it right now. So as soon as we're done and they process it, that video will be available, and we'll be quickly publishing all the MP4 videos from all the presentations afterwards. And then as Jason finishes his editing, we'll have the slice and dice by presentation videos with Q&A.
So I'd like
and that'll be on the TAPR channel on YouTube.
Or we haven't, I guess we haven't worked out whether the stuff Jason edits will, if we can get him to upload it to there, that'd be great. If it's on Ham Radio 2.0 and we link to it, that's great too, because it's still on YouTube.
So Rob, whose idea was it to use the propeller analogy? Was that yours?
Well, yeah, I mean, I've seen that people before talk about aliasing, you know, with the propeller. Conrad was the guy who drew all those pictures, you know, he's, you know, the whiz when it comes to the graphics.
That was genius. That was absolute genius. So congratulations, Conrad. That was awesome.
Yeah. I agree. Yeah, as soon as he did it, you know, I was like, sent him a note and said, "How did you do that animation? That was so cool."
It's like some of the people said online here that it's the best explanation that they've ever seen. So excellent.
Yeah, I was amazed. He did it all, you know, he had some figures from the paper, but he turned them into the animation with just PowerPoint.
So having the paper and the video will make it all complete.
Yeah, right. And, you know, I'll probably stick the paper on my website sometime too. You know, it's nice to hear it'll be on YouTube. It was, I like the way you guys did this time, where you had the presenters make their presentations ahead of time. I think that really made things a lot better.
Oh, thank you, Rob. Thanks for the feedback. And we were certainly, so far we're getting a lot of compliments for how well the conference is going. So thanks everyone. And we do solicit everyone's suggestions. And we all know we really enjoy being in person. And there's really no substitute for that, but we're trying to make it the next best option.
So Harry K9 DXA had his hand up, and I allowed him to talk and unmuted him. So if he has a question,
good.
he can, yeah.
I just put a chat item on there that the toaster oven deal was covered in a QST article a few years ago, and they had some also some items in there about ideal temperatures. There were a couple of different temperatures that the author noted would be good to follow in your control design in order not to overheat or underheat the board while it's in the oven. That's all I wanted to say.
Oh, yeah, I recall that. Wasn't there also some suggested minimalist temperature controllers?
Yeah, they had one controller designed and put in the article, so you could build your own little system just from the article.
Thank you, Harry. Okay, we got about 5 more minutes, so we'll just coast, and we will get Scott Howard queued up here in a few minutes. I guess we should put like music, or, you know, since you're on the beach there, Scotty, can you kind of like turn your mic on to the waves there?
Yeah, that's probably a safer alternative to music. We'd probably owe somebody royalties, and we don't want that.
I get my big fan for the hurricane weather. Yeah, you know, what's weird is I don't even know where this picture came from. I just went into backgrounds and it was there. So I thought, wow, that's a cool picture. I'll use that one. So maybe an upgraded zoom and it came with it. I have no idea. But I like it because it's where I wish I was right now. And you can sort of be there and not be there.
Or are you responding to Bill Dombush's comments?
Yeah, and I was going to say to Bill, I've already typed it in there. So Bill, I got to get up here close. It's small print. Dornbrush. I hope you consider doing both in-person and streaming future conferences. It's very hard for me to justify attending in person, but this has been great. Well, thank you for the comment, Bill. So one of the thoughts is, you know, we agree. We've kind of talked about that. And one of the things, of course, is to be able to stream the live presentations that are going on during the conference. So that's one option. The other is to invite outside speakers to remotely give talks. I mean, technology is getting better and better. We've done in the past with varying success. So there's a lot.
The one I remember was from W6HHC, I think, and it worked very well. I mean, it was just like being there, only there was no speaker talking to you. It was just the screens and the audio.
So we did Microwave Update when Tom N8ZM hosted it in Dayton, and we had 1 or 2 presentations come in over the internet. Last year, we also at the DCC had our banquet speaker, Bill, speak, W8ELK, speak by Skype.
Yeah, after being locked up for 6 months here, I was looking forward to a road trip to Charlotte, but it was not to be.
Yeah. So N9NL had said, why not include remote speakers at live conference? We have in the past. So the question's going to be, are we going to include more in the future? And we've got some wonderful audio-visual people, and Jason Johnson and George, who's playing our host right now, and in the past has been Gary. So the limiting factor has been more the technology out of our control. And now that we purchased a Zoom account, this has been a big help here, and this has really taught us a lot where we didn't have this before. So the tools that we're having at our disposal now is making it a little more easier. So we're going to seriously think about it. Okay, well, we're counting down, and so let's go ahead and get started here. And Scott Howard, you want to unmute and unvideo and say hello?
Sure. Hey, everyone. This is Scott Howard.
Hi, Scott. And tell us a little bit about what your talk's going to be.
Sure. So this is actually similar to the last one in that when my lab shut down last spring on campus, we had some students that were working in some medical imaging research that needed to keep on doing some work while they were spread out across the world, essentially. And so we kind of pivoted from some of the medical imaging stuff into using compressed sensing as a way of transmitting images over radio. So I'm the ham, so I'm like, okay, so let's figure out, what can we do with this? And what we came up with was a way that you can send images where if you lose packets, it doesn't matter, you still get the full image. And any packets lost just end up decreasing the quality of the image rather than causing sections of the image to be blank, which is good for like low power applications or for very low, high bit error rate applications that you might want to use it for.
Okay, and thank you for that. And for everyone's benefit, it is going to run about 25 minutes, so we're only going to have a very short for questions at the end. So go ahead and roll it.
Hello, everyone. My name is Scott Howard, KD9PDP, and I'm here to tell you about packet compressed sensing imaging as a new image transfer method that was developed where you can send packets containing image information through unconnected and noisy or lossy links and still be able to receive the entire image, even with very high bit error rates and packet loss. This project was developed starting last semester when the University of Notre Dame, where I teach, was shut down. And so we had to find projects for students to do remotely from all over the world. And a team of students came together and started working on this and developing this technology. which is supporting a high altitude balloon project in Notre Dame, and also a new CubeSat, the Irish sat, that is starting up as well. And so this is all kind of a big effort. It's kind of starting up together. We're excited to kind of share with you, and hopefully something people can find useful and use. So, what is PCSI, Packet Compressed Sensing Imaging? Well, on the right is a picture of the GUI, and I'll have a demo of it later of it operating. But the highest level, it's the image transmission mode for digital packets for unconnected networks, similar to how APRS uses unconnected networks and UI frames and AX25. And so what we do is that we're sending these packets out, and those who are receiving the transmission, even if individual receivers only receive a subset of information or a subset of the transmission, or if they miss random packets in between, they still can see the entire image. Every packet contains information in the full image, and each subsequent packet simply fills in more of the blanks. It makes a better quality image. So if you miss any in between, it doesn't, not the end of the world. You can still get the full image. In fact, on the right here in this image, you can see that in this demo, we had about 54% of the packets were received, or 45% of the packets never were even received. And we transmitted an image with the quality down here. This is what the received image actually looks like, which is pretty high quality for losing half the packets that were transmitted for you. Okay, so this is useful for any band or any mode. It's not really specific to VHF or UHF. In fact, there's some good HF reasons why you might be interested in sending kind of short packets and short windows with this information. Right now, software works with any KISS TNC hardware, software modems for transmission. We actually had one of the first demos. Someone was using a Raspberry Pi running Linux as the SDR dongle as the server, and then they had a PC that connected over a TCP connection to it, and then ran the client of our software on the TCP using the Raspberry Pi as a server. And then we had another Windows computer somewhere else, transmitting it through the GUI also. So yeah, you can come up with a whole network, that can use this in a way. Also, this is something that's trivial for transmitters to use. This is an important part for what our goals. We want to make sure that it's something that can be done with extremely low power, low memory ways of transmitting. And pretty much requires almost no computational power with the transmitter. All the hard work is done by the receiver. And that's one of the key designs of this. Okay, so the image transmission challenge we have. We're looking at, think about weak signal to noise ratios. You have fading, you have signal loss, possibly. You can have the low computing power we mentioned, or maybe you have a good window for transmitting for a little bit, and then you have a bad window. And you just want to get as much information out as you can in those little windows where you can get a good contact, and then kind of reconstruct the image with what you got. So right now you have analog and digital techniques, and you kind of walk quickly through, what happens in slow scan television in these environments, and talk a little bit about slow scan digital video. So slow scan television, the analog, it's been around for a very long time, and ISS famously has feeds that come down from it that are images transmitted SSTV. But if you do get noise or or any type of interference in your signal, it causes many different errors. And this is an example image that came over the from the ISS. You can see there's many different effects in here, from ghosting images and misaligned color lines and just outright static that makes your image distorted or lost the data. And so this is something that is kind of well known with analog signals. If you lose signal to noise ratio, this error is going to occur. And so one way of addressing that was the development of the SSDV, slow scan digital video, and which is kind of really clever ways of overcoming a lot of these issues. And there you take your image, you take up the camera, and you convert, basically encode it into a specific type of JPEG format, which does a good amount of compression for you, so your files are going to be smaller, and then you just send the packets in chunks of these minimum coded units of JPEGs, little squares of chunks of your image out. You also put some forward error correction codes on it, so that any errors that are detected on the receiving side can be, maybe even some small errors here and there can be actually corrected, so you don't have to throw away a whole packet because a couple of bits got flipped. And so as a net whole, you can do some really powerful things on here. And on this right side, there's an image. This is actually of a CubeSat on lunar orbit with an amateur radio on it. And this was taken, or at least I found this last June or like 2 months ago. This is an image of Earth from the moon. And this image was transmitted with 2 watts over UHF using SSTV, which is really, incredible feat. And so it's a really cool thing to do. Over here is from the SSTV's website from the UK High Altitude Society. And you can see the image here, and in the right corner you see these little blocks. Well, these blocks correspond to areas where the signal dropped out. And so if the signal dropped out using SSTV, you just lose sections of the image, it's just blank. On top of that, doing this JPEG encoding and then this, FEC codes can take a lot of memory. It can be kind of, tricky to do, if you're trying to teach a course to first-year engineering students using Arduinos. Trying to get them to squeeze some JPEG encoding into Arduino is going to be a little bit difficult. And so, we're kind of looking at both from point of view of how do you do this on like a low power computing, just for teaching purposes, but also because we're interested in houses of balloons and CubeSats, and we want to also think about maybe extreme environments. If you're in the trying to get signals out where it might be low power transmitters and weak signals. So what do we have? So this is a overview of what PCSI looks like. We'll talk about a little bit what it looks like first, and then I'll do a demo. So if you had an image right here, like on this left, and I wanted to transmit it, I can break this up into, the bits for each of the pixels and transmit them. And using a, normal 256 byte payload that you get on a packet, you need about 914 packets of information to be transmitted out in order for you to send this whole image. So it'll take 914 packets, maybe 2 seconds per packet or so. And I'll tell you about how long it would take for this. Okay, with using PCSI, if I just received only 10 packets of this image, 99% loss essentially, I still get image, like I get a picture of the whole image. Terrible quality, but it's there. I get another 20 more packets, and now it starts to take shape a little bit. After only 100 packets, so like, still 90% pixel loss or so, I'm beginning to see the image. I'm actually seeing what it should look like. And then finally, after 300 packets, this image is pretty faithful to the original image that was sent, and kind of shows this power of this technique and how it can be used. That those 300 packets could have occurred at any moment, the beginning, the end, randomly in between, in different window chunks. It doesn't matter. It will just take it all and reconstruct the image. All right, and so now for this demo, we'll walk through. So there's a website right here on github.io. You can go, and there's going to be videos of how to install it and how to use it. And I'll just go through a quick demo to see show you how this works. All right, so when you go to this github.io page, you can either just download the straight up Python files and run them on Windows, Mac, Linux if you're interested. We also have Mac and Linux binaries that you can download and just run. So here I just downloaded this. This is the Windows distribution, PCI SCI Win64. Okay, and then I open up this folder right here. And when I open the folder, there's a lot of files. But inside of here, this is PCSI GUI file. That's our main file. That's the file that we're going to run, and that's our application. Okay, so I'll double click it, and one instance will pop up. Aloha, and I'm going to demonstrate transmitting from one radio to another. And so I'm actually going to have so one instance is control one radio, and then the other instance is controlling the other radio. You actually can do receiving and transmitting on the same radio. You can have whole internets with multiple people broadcasting at the same time. We'll show what happens. All the possible images will show up here, and you just kind of select which one you want to listen to and watch at the time. And even though you're not looking at an image, you're still acquiring all the data from everybody else's. And so you can actually have like a whole net of images just kind of being shared with each other simultaneously, which is kind of cool. And you can have the same radio that's transmitting also be the receiver for this network. Okay, so once you have this open, I'm going to connect to my 2 radios I have. One radio is this Kenwood THD72, and it has a built-in TNC, so that's why it's nice for this demo. But like I said, you can use like software modems like Direwolf and just hook up your sound card into your radio. And actually, the video on the GitHub IO does that. I also have a little ham shield here, just an Arduino connected to a small radio. This is going to be our receiver, and we'll also use the other Kenwood as our transmitter. Okay, so for the transmitter, you always need your call sign, otherwise it won't transmit. I have this on port 8, and so I'm going to connect, and then I'm going to load my image. I already had this image saved. This is the image. This is not one of our images. This is one we found on the internet that is a high altitude balloon. Okay, and then yes, everything is good to go, and I will hit start. Great. So right now, my radio is transmitting. Little red light here. You'll have a console window that also shows up, and just as for debugging and showing all the binary data is coming out. I just want to distract us from that for now. And actually, you see, I've been transmitting. It's already set 5% of the image. I never set the receiver. Oh no, I missed the beginning of the transmission. What will I do? So I will now connect to my receiving side. Okay, and now I'm going to start my receiving. And there it is. Okay, so after one of the packets came in, it showed up on this list here as I received a station. The PCSI is just the name of my ImageNet, and this is my call sign that for me, and this is the 0th image. So sure, I click on it. Select image preview. And what I see here is a bunch of the random pixels that have been sent. We'll talk about how this works later, but there's random pixels here. And if I want to reconstruct the image, I click process PCSI, and then this will just run continuously and run some algorithms that we'll discuss in a little bit that will reconstruct the original image. And there it is. Okay, so far, we've only received 5 or 6% of the pixels, and this is what our image looks like. Okay, and so as this progresses, you'll get more and more. So far, we've transmitted 20% of the image. I missed the first 15% of the transmission, but as we sit around and watch this, this will actually slowly improve. Okay, and so I guess we'll do what we do on the cooking shows, and we'll come back and view this later. Maybe I'll go through another couple slides here before going forward. But yeah, you can see, you're actually starting to see some of the color coming in. And so we see that this is beginning to work. Yeah, just improving every reception. Okay, so back to the slides, and then shortly I will return to the okay. So here is our demonstration we just did. So we talked a little bit quickly about how this works. And of course, we'll try to find some analogy you can compare to what we look at. Well, we kind of think about how our eyes work. Our eyes have 120 million pixels of black and white, 6 million pixels of color in it. We got basically 24-bit color, 10-bit grayscale. This is essentially what we got going on. And we can perceive around 100 frames per second. So those 90 hertz phones are kind of really attractive. So what's the bandwidth we need? Okay, you can just do the math right here, and it says you're going to need 294 gigabits per second bandwidth in order to transmit every single pixel to your optic nerve down to your brain. However, the optic nerve can only carry less than 10 megabits per second, and so we're going 30,000 times slower than we need to go, and it still works. Well, how does this work? How can our eye work? Well, the way our eye works is through a combination of things, but your eye doesn't actually need to transfer all the information it's constantly receiving. It just needs to send enough information that your brain can kind of reconstruct what should have been there. And your brain has some amount of processing goes on to have recognize shapes and recognize fill in the blanks and kind of make it happen. And so it's saying, okay, can we do something similar for transmitting imaging data? And so these images right here, they're from Richard Taylor's blog on PyRunner. I had a link to it 2 slides ago. Definitely suggest you check it out if you want to learn about the kind of math and the physics of compressed sensing. Our paper we have for this conference has a little bit more detail, but we'll just give a quick high-level discussion of what happens. So compressed sensing says, if I only have these little bit of pixels here and there, can I reconstruct this? Our brain looks at this, we can kind of see that there's Escher's waterfall here, but on the right, yeah, I can see how one came from the other. Our brains can do that. Let's get the computer to do that. Okay, so again, why this matters is that if we had static on an analog or digital image, you typically these sections of our image. With compressed sensing, what we're going to do instead is transmit just the random pixels here, and then use some algorithms to rebuild everything. So do we even need to send all the information? Is this even a valid thing to do? Like, aren't we leaving information out? Yeah, that's a good question. And so it turns out that no, we actually don't need to transmit all the data. And this is the whole magic behind how compressed sensing works. The idea here is that if your image is sparse, you don't actually need to send every pixel. And so by sparse, I mean that a lot of your image is zeros. So you can say, okay, well, that makes sense. If most of my image is zeros, I don't really need to send lots of zeros to find a way of only sending information that matters. Well, if I look at this image on the left here, this image does not have a lot of zeros in it. By zeros I mean pure black. It has a lot of grayscales and some whites and stuff. There's some text in here, maybe some blacker in the shadows, but not really pure. Not much black. However, you can do some mathematical transforms that rather than representing this image as an image, I can represent this in a thing called the discrete cosine transform spectrum. So it's just a mathematical equation that transfers this into this, and information-wise, they are identical. I can perfectly reconstruct this entire image on the left from all the stuff on the right. They are just a different representation. Well, this image on the right has lots of zeros, lots of obvious zeros. Therefore, if I think about the image in that space, in that domain, I could transmit it and have all this sparse information, and then reconstruct it in that domain, and then convert it back to the original image domain, and get the original image back, even though I didn't send all the data, because most of the data was zero anyway. So that's what we're doing, and that's how it works. And so on the right here kind of shows what we're happening when we're imaging. All these red pixels are black and white pixels that were sent, and they're kind of randomly distributed all over. And then we have those kind of bluish colors are the color pixels. And then here's our transmitted pixels that actually got reconstructed in the right. So this is what was actually sent. Our algorithm reconstructs it down here. Speaking of which, let's go check up on our program that's been transmitting in the background. Oh, so there we go. We received 53.8% of the pixels. And this is what our image looks like. So it's still, now it's beginning to look like a real quality image. And it's still running. Yep, it says it's still running. Yep, so 54.4. Okay, and so we'll check on it again later as it continues to transmit. Okay, so how do we do this? How do we send random pixels each packet? As a receiver, if you're just sending me random pixels, how can I rebuild my image from a bunch of random pixels? Well, it turns out, that you can randomly select the same pixels every single time if you choose a pseudo-random number generator. So pseudo-random number generator is just like if you do a random number generator on a computer program, it actually isn't random. It's an algorithm that will get you the exact same random numbers every time. It's just, they look random to us, but there's a computer program that just tells us what these are. So if I just know I'm using a certain computer program to generate random numbers, and my transmitter comes up with a random list of numbers, I can come up with the exact same random list of numbers on my receiving side, and then I just transmit. So all my transmitter needs to do is tell the receiver what was the first random number that was chosen, or what was the pixel ID about where the first index is, and then the receiver can know what every single possible pixel value is. If I just send a list of values, 255, 123, 69, 14, 186. My receiver then can know which pixels those correspond to, because the random number generator will be the exact same whether it's in space or on Earth. Right? And so that's the magic between how you can know where the pixels go. Another trick we use is chroma compression. It's popular with JPEG as a way of exploiting the fact that the human eye has way more black and white detectors than it does color detectors. So the resolution is much higher for humans to resolve black and white than we can resolve color. And so why send high resolution color and also high resolution black and white if our eyes really care about black and white more than color? Okay, and so this idea of not sending, transmitting so much color information is called chroma compression. JPEG uses it a factor of 4, so it sends maybe 1/4 or 1/2 of the number of color pixels as it does send black and white pixels. We use a similar technique that JPEG uses. We represent our color image in the YCVRCR for luma and chroma red and chroma blue color scale. On the right here, you can see color image, the black and white one, which is just the luma, and then here's the chroma with the blue and the chroma with the red. You represent the image in this way, and then you send every pixel eventually for the black and white image, but you only send a fraction of the images randomly from the blue and the red. And we've actually seen that you can do a chroma compression about 20:1, meaning we only send 5% of the color pixels, and we can reconstruct the full image. The image that you're looking at right now that I'm showing you that's being transmitted on the radio has a chroma compression of 20:1. I'm only sending 5% of the color pixels in total, and letting the computer make the best guess of what everything should be in between, and our eyes really can't tell the difference. Okay, there's just some notes about packet framing, and the paper has more details about this, because this question comes up a lot, like, oh, do you have to use AX25 or can you use this other thing? Really, packet framing is independent of PSCSI. PSCSI is simply the method of getting a stream of random pixels and then reconstructing the image. So you can use any packet framing you want. Right now we're using AX25 because the KISS hardware and software is easily accessible. Everyone can have a software modem downloaded on the computer that can work over KISS. So let's use that. It's also compatible with APR's hardware and software. And so if you have the hardware, you can use it, and software, you can use it. But it's probably a good idea to not use the APR's channels because it will, this is kind of this kind of technique could monopolize the bandwidth for that. Okay. Also, you can do digipeating if you have X25. That's an optional thing. And also, we had some discussion on our GitHub about using SSDV style framing, which is much more compact style framing for much less overhead, better for higher bit environments. This might be a good one for the HF if you have some issues. And we have a kind of a comparative study and showing what the throughput versus bit error rate is in the paper if you want to see some more of those details. Okay, and so if you want to transmit, basically all you have to do is use a pseudo-random number generator, select which pixels you're going to transmit, then select what chroma compression you want, so which color and which black and white pixels you're going to do, convert it to the YCVTR, and then create the payload. And the spec is in the paper. Transmit the payload. Basically, each payload that is transmitted has all the information you need to reconstruct the entire image. So that's how it's designed. Put in the frame, which is kind of convenient if you have a TNC that can do all the framing and CRC and bit stuffing for you. And to receive it, you receive a packet, extract out the header information, so you get things like the bit depth and the image size and all those color values and everything. And then you can use one of any compressed sensing algorithm to kind of reconstruct what it should have looked like originally. We give some demo ones, example ones in the paper, and so those are sufficient ones. This is we have links to the actual papers we use, and basically we are reconstructing the original spectrum, or making a best guess of what the original spectrum would have been if it was sparse, and then reconstructing our image from that. Okay, yes, and so that's how this technique works. Let's go check up on our imaging one more time before heading off. Okay, so we received 80% of the pixels so far. And here's our image. So you can think about this as 20% packet loss, and this is the image quality. There's no compared to the original quality up here. There's no areas of pixel loss or data loss or corruption or anything. It's still coming in, so we'll continuously improve every packet we get. But this is generally how this would work. All right. So in conclusion. Some stuff we're thinking about doing in the future. We're developing an Arduino transmission client for kind of our low power areas. So it's kind of a challenge for students to learn about. We're trying to think about setting up servers for centralized upload so that people from all over the country can receive high-altitude image partial packets, put it to the server, which then can combine them all and just do one analysis for it and put out like one clean image of all the packets. Also, think about ways of trying to introduce this into APRS as frequency objects, so that you can see if an ImageNet is active and can join in, or you know where to tune what frequency in order to see the images that are being transmitted. And also, we're looking at developing cell phone apps. Making this device work on a cell phone. We're working with Rob Riggs over at MobileLink to figure out ways that we could develop apps with their hardware. And so we have a cool little partnership starting up over there. So you have your phone connected to Bluetooth, which is a TNC connected to your just handheld radio. Snap a photo on my phone, and then I can transmit over my radio over low power, remote, mountainous, bad, whatever conditions we got, and you have a whole network of people doing this, kind of in remote low power environments, if they're interested. All right, so that kind of brings me to the end of the talk, and encourage everybody to try it. If you have bugs you find, if you love people finding bugs, and so we can fix them and make this better. You have to post them on GitHub. Again, here's a link for downloading it. And yeah, I welcome any questions. Yeah, well, hope you enjoy using this. Yeah, thanks everyone.
Wonderful, thank you. And Scott, go ahead and let's turn your video on.
Okay, yeah, I'm here. It just says I can't because the host has stopped it. Oh, there we go. Thank you. Here I am.
Gotcha. Okay. And so we got some questions coming in. So Mark says, interesting presentation with an exclamation mark. Are you familiar with the shortwave radiogram project by Kim, KD9XB?
No, I'm not.
Okay, that was a yes/no question.
You have a link to that or information for that? You can put it in the chat and I can go look into that.
Yeah, so Mark, you might put a link to that in the chat and then Scott can follow up on that.
Ground mode propagation, I'm guessing, but I'm curious about it.
And we got another question from Bob V. How does PCSI image recovery do with time correlated loss compared to uniform random loss?
Yeah, so if you think about what we just did in this demo, that was time correlated loss. That was all the packets that were lost at the beginning. You know, I didn't start receiving the packets until maybe 15% into the transmission. And so it works. The reason why is that each individual packet contains random pixels. So it doesn't matter if I lose packets that are in a sequence with each other, or if I lose packets that are randomly oriented, because each individual packet itself is random. And so there's kind of no way to avoid the randomness. It's kind of the way it's designed.
Okay. We've got another question here from N9NL. Does the sampling really have to be pseudo-random, just be deterministic, but distributed throughout the image?
Yeah, so this is one of the tricks about PC or just compressed sensing in general, is that the sampling that you choose has to be very different than the reconstruction system that you use. And so we're using a cosine transform reconstruction. So we have to make sure that we just avoid using like a periodic structure for sampling. And so if you choose randomness, you're guaranteed to not basically accidentally choose things that look like cosines. So that's the way that we choose it. So there are other things you do besides random, but random's kind of the laziest.
Okay, great. And by the way, Mark did post the URL in the chat, so when here in a moment you can check that out.
Steve, I have a couple questions.
Bill,
I have a couple
Bill
questions.
Engel
Also.
Bill Engel asks, "Can I get this and use for HF-SSTV? What is the bandwidth required to transmit?"
Yeah, it's a packet system, and so it's different than SSTV, which is more of an analog and uses bandwidth. So this would be it's a digital system, so you'd be 300 baud most likely on HF, and whatever TNC or soft or whatever type of digital communication thing you have. You actually could theoretically put this into any HF messaging thing, even if it's only 40 characters. Your image will take forever to get there, but so it could work on whatever you would do.
Okay, well, excellent, Scott. I'm afraid that's the time we have for questions. It looks like we got them all.
Hey, Steve, there's a couple from the YouTube channel, but we can do those on break, I guess, afterwards.
Yeah, so could you hang around during, well, there is no break. We're actually finishing. Scotty, go ahead and ask the YouTube.
Sure.
Okay, there was a couple questions. One was he asked if you got the cones and rods mixed up in the bandwidth calculation.
Oh, possibly. It was a kind of a back of the envelope quick thing on the fly I was doing with some students.
Okay.
Yeah, so it should be 20. Yeah, I'll double check that.
Okay, and the other one was he noticed that the transmitter has transmitted more packets than the image has, and he's wondering about the algorithm.
Yeah. So that was we kind of chose that on purpose. That I transmitted maybe 15% more from the transmitter than the receiver received. So the algorithm, what it's doing, so in the paper I have a little bit more detail about it. It's basically getting the pixels that were received, and then it's making a guess of an image. And then it's trying to see what's the difference between what it guessed and what it actually was received, and minimizing the error between those two. And so this way you can get the most likely guess. And it also has the extra constraint that whatever it guesses is also going to be a sparse image. And so by putting the constraint on and trying to make these two match, it fills in all those gaps, even though we lost 20% of our packets from just not turning on a receiver fast enough.
Okay, and the last question is that you can't do it on an Arduino. The processing happens on a PC. So then, is there Arduino acting only as an AX.25 modem?
Exactly. So the transmitter just needs to be an AX25 modem, basically. It just needs to be able to pick values out of an image, the RGB value, and then basically just convert them to YCBCR, which is a very simple conversion, and then send it over AX25.
Okay, great. That's all the questions we had on YouTube. Thank you.
And let's take one absolute. We got one comment. All right, one absolute last question then. How do you sync in the middle? Are you sending the RN and then using it to generate the next RN?
Exactly. So what we are sending is, if we send the RN, that's a very large number and we're very bit constrained. So instead what we send is called a packet ID. And each packet ID is like the index of the random number generator. And so we kind of generate the list of numbers ahead of time, and it just tells us which index we're looking at to kind of save bits. But yeah, exactly. We send that random number generator seed essentially every time, so we know where it is.
You know what we ought to do, Scott, one of these times is play Stump Scott Howard. You really are right on the ball and got all these answers. Thank you very much. It's excellent.
Thank you.
Okay, we're gonna mute your video, and we got Alex Swartz. Alex, you want to say hi?
Hello, nice to meet you. Thanks for putting on the show.
Okay.
Can you hear me?
Yes, we can hear you, Alex. And let's see here. And there's your video.
Okay, that's my video. Okay.
Hi, I'm the Alex Schwartz, VE7DXW, and I'm the principal investigator of the RF seismograph project. We're trying to detect earthquakes just using a shortwave receiver. And here you're in the headquarters in Lynn Valley in North Vancouver, British Columbia. And this is my closet. And this is basically my workshop. We have the main receiver up there, which is a TS590. It scans every 7 seconds to a new band and then records the noise level. And the noise level is recorded via the RF seismograph program, which runs on top of the Raspberry Pi, which is the white box. And down here we have the main computer with our new software called RF Earthquakes versus Propagation display software. And what basically does, it takes the measurements, the data come from the seismograph, gets plotted here, and it gets correlated with the timing of the strength of the quakes that the USGS puts out on their website. And we record all the quakes. The quakes here are the green and the white spikes. The green are very small quakes, and the white spikes are the bigger quakes. And if they get really big, they will show up as pink. But basically, what we do is we do the measurement of the propagation and correlate it to the earthquakes as recorded by the USGS. Welcome to the presentation, How to Build Worldwide Earthquake Detectors with a Standard Shortwave Radio by Alex Schwartz, VE7DXW. To first understand how we can how earthquakes affect the propagation, we first have to understand how earthquakes create electromagnetic fields. There are several ways electromagnetic fields are created. The first are the piezoelectric effect, which is the main cause of the electricity that flows and the electric magnetic field as a result of that. Secondly, there's microfractures in the rock that release vast amount of electrons, and these electrons move up towards the surface and circulate around the quake area. There is a current flowing. Electromagnetic will start to emerge out of the Earth's crust and move towards the ionosphere. Since the ionosphere contains ions, it attracts the magnetic field, and it creates an effect that allows the ionosphere to concentrate, and starting lenses that start to reflect shortwave radio. And that's the kind of propagation changes that the RF seismograph looks for. So this is a picture of how this basically happens, a very simple situation. So once the current flows at the bottom in the ground, the resulting magnetic field pops into the sky and then starts to changing the ionosphere. And this can happen within a half an hour, or and as soon as the ionosphere started to change, the radio wave propagation that was existing changes, and it changes quite drastically. On the right, on top right, we see an equivalent of the what happens at the sun. The field lines are visible easily because we have bright ions that are lit up, and we can see that with a telescope. And this is exactly the same process that happens on the planet, just happens at a very lower energy level. Boyarchuk and Pulinet's RF quake experiment in 2002. In their 2005 book, Ionospheric Precursors to Earthquake, they describe an experiment where they go into the outback of Australia and record the effect of earthquakes, of local earthquakes, on the shortwave radio frequencies. The measurement was carried out on the following frequencies: 129 to 132 kilohertz, 2.3 megahertz, 4.2 megahertz, and 48.06 megahertz. The issues with that setup is that it's only can be detecting RF outbursts from the quake directly, and they did not measure any skip change due to the creation of earthquake's magnetic field. And so the experiment did not really reflect what the RF seismograph actually can do. Principle of operation of the RF seismograph. The magnetic field of a developing earthquake exits the ground and starts to bend the ionosphere. This is a slow process, taking a couple of minutes, but can be jittery at times. If the quakes are strong, above M5.9 on average, the ionosphere is overloaded and transition waves may occur. This is a very common occurrence, and the ionosphere is thin right now, and in the low solar flux conditions that we currently have. The measurement below shows exactly that behavior where we have several earthquakes coming after 1400 UTC, and you can see the green part of the spectrum, which is the 40-meter band, starting to jump up and down after in 1500 UTC. That we get 2 hours of high noise level, and then our noise level drops again, and then the double quake strikes, and all of a sudden we have 20 meter propagation. And this effect on the quake, on the effect of the quake on propagation can actually be quite seen, but it's not quite as clear as just looking at one picture. You actually have to follow it for several days, maybe even weeks or months, to understand how this all interrelates with each other. The different types of measurement from the ARRL seismograph. The ARRL seismograph performs a semi-passive and passive measurement at the same time. The passive measurement only records the noise level. So if there's no signal present, you only see a flat line or a line that moves up and down with the noise level. As the receiver receives an incoming signal from a faraway station, such as JT65 or FD8 signal, the signal strength is added onto the top of the noise, and the creates a wide line visible on the screen. So now you might wonder, why do the ionosonts not see this behavior? It's probably because they are not fast enough to display the fast changes of earthquakes. The ionosonts only measure every 15 minutes and will usually miss most of the fast changes that are required to see the earthquake. Creating a worldwide propagation network to detect earthquakes. Thanks to the ingenuity of Ham worldwide, we have digital modes that utilize the available HF bands, specific frequencies on each band. Especially WhisperNet is an incredible tool to measure how very small signals can travel around the planet. And we have a really talented group of people that work on this continuously to keep to keep the people busy and the bands occupied, so that the RF seismograph can record the change in the propagation during the effect of an earthquake. We basically built a worldwide machine that utilizes every station that broadcasts throughout the world in one of the ham radio frequencies that we measure, and every change that an earthquake makes will be recorded, because there's always another station somewhere in the world that is currently broadcasting and it can be seen on the RF seismograph, and the changes of the earthquakes will be measured as well. Earthquake size and impact on propagation. Earthquakes are very powerful events. An M4.0, for instance, is equivalent to 1,000 tons of TNT. 1,000 tons of TNT equals 1162 megawatts of power. So if you consider that these quakes only last a few seconds, you're probably talking about a transmitter power over an energy of 1 gigawatts. And the effect of the quakes is always depending on several things. Hi, I'm the Alex Schwartz, VE7DXW. Hi, I'm the Alex Schwartz.
Okay. Oh, something didn't work. What happened?
1160 I have no idea what happened.
So if you consider that
is it streaming again now?
Okay, continue. Thank you.
For energy of 1 gigawatts. And the effect of the quakes is always depending on several things.
I'm sorry, we're having trouble playing
Trouble. I
Alex's
don't understand what.
presentation.
Oh, do you want to just you? Oh, you're still there?
Yes, we're here.
Oh, how are we going to do this?
Well, we'll do it the old-fashioned way. Give me a second, please.
Okay. Well, I guess.
I have your PDF.
Okay. All right.
So,
and then we'll just continue on the next page.
Okay.
Oh, let's just see what page that is. Okay. Okay, page number. What is it? Yeah, earthquake size and impact. What page is that? Page number 8.
8?
8. Page number 8. Yeah.
Okay, just a second. And I'm going to do this. Everyone is showing the PDF, and Alex will ask me to turn the page, and I will do my best to do that. So, give me 1 second to share the screen that has the.
Okay. Darn it.
Yes, I agree. Okay, please talk.
Okay, so here we have the earthquake size and impact on propagation. So what we noticed is that since we have this worldwide propagation tester, basically, we can see actually, interestingly enough, we can see almost M2.0 quakes. And the M2.0 quakes, when they occur, that we can see are the local quakes that occur mostly in the Rockies and in California. And there's also a consideration about how much solar wind we're getting. The more solar wind we have impacting on the ionosphere, the easier it is to see quakes. Like you can see really interesting patterns developing by looking at our seismograph data that we have collected over the last 4 years. And it seems like the 40-meter band is probably the easiest band to recognize that there's earthquake behavior, because they have this behavior. Can you go to the next slide? Okay, super. They have this behavior where when you look at the left and the right side of the graph at 1800 hours, there you see the green line, which is the 40-meter band, chopping up and down over a couple of hours, and that's usually caused by earthquakes that are developing. And we've been tracking this, and we're trying to come up with a sort of a way of detecting, like an alert system. I would say, oh, when we see that kind of wave, we hope we know that there is most likely a quake to follow, and and the measurement that we did here was actually a very quiet day. Like usually we see quakes in the size of M6.0 and higher, and they have a very significant negative impact on propagation. And the other thing that we see on this quake on this slide is that we see that big sort of light blue bar that occurred just before 1800 UTC, and this is actually propagation created by fast-moving solar wind, and this usually didn't last very long, and it seems that when there's an opening, when you have fast moving solar wind and an earthquake together, it seems like the earthquake just creates a sort of a gap in the ionosphere, a gap enough to let the solar wind come in to activate the layer to create 15-meter propagation. And in general, the 15-meter band is different because every time there is a strong solar wind, you will actually see the noise level go up. And that's what you can see after that bar. You can see how the noise level goes up on a 15-meter band. And it's only that the 15-meter band does that. Okay, next slide. Can we do next slide? Okay, so there's actually something interesting that happened on May 1st. And we get a lot of people talking about that earthquakes and propagation have nothing to do with each other. But this data that we collected seems to be suggesting otherwise. But I guess I'm the only one talking about earthquakes and propagation at the moment. So we're looking for other people that start the same kind of research. And we hope that we can eventually collaborate with HamSCI, and they seem like they've been doing a really good job in setting up test stations. And if you set the test stations up at the right interval frequency, then we have the chance to actually see earthquakes. I mean, the problem with the ionosons is that they're not fast enough, so we're kind of not seeing the earthquakes. Like, it looks like they deliberately chose a refresh rate that would cut out the earthquakes because they didn't want all that background noise that didn't seem fruitful to measure all that. Anyway, what happened on May 1st is that there were actually 4 quakes. They all happened in the Pacific, and they kind of happened up in near Japan, and then 3 quakes of them were north of Australia. And the effect of that earthquake, they were timed in a way that the 80-meter and the 40-meter band opened up to Europe, and it made a 2-hour opening that created contacts from the West Coast to Europe in a time of the solar cycle where you would never think that something like that would happen. And May 1st was a lucky day because that was the day of a contest. So there were a lot of people that were appreciating that opening, and they were really surprised to have that kind of conditions at that time of the solar cycle. Can I have the next slide?
And Alex, we need to finish up in order to give you Q&A time.
Alex, your slide is up, but he's muted. Alex, somehow you're muted.
Okay, is it working now?
It is. Did you hear Stephen ask you to try
to
wrap
hurry up?
So, yeah. So you can have your Q&A.
Okay. Okay. Can I finish that slide and then Q&A? Or is there a lot of Q&A?
Oh yeah, absolutely.
Yep.
Okay, well then do the Q&A.
Okay, let's see here.
All right.
So Jay, there's Jay Swartz asking, what coordination have you done with HamSCI?
Yeah, well, we're trying to, well, we've been working together with HamSCI on the solar eclipse part. And when the solar eclipse was over, we were actually, our seismograph was collecting data, and we didn't, it was rather interesting. We saw the high solar activity that we had and collecting all that data. And then at one point, 2 years ago, we discovered that earthquakes actually, there were actually 3 earthquakes near where I live. And all 3 showed up in the noise graph. And then I started to do some research, and then all of a sudden we realized that, you know, this RF seismograph is a real RF seismograph. It's not just a RF weather station. It actually detects earthquakes. And since then, we've been trying to promote it. And so we try to correlate the USGS database with the noise and propagation that we're getting. And I hope that HamSCI can take up some of that research in their future projects.
Okay, thank you. Do you have any numerical correlation value graphs to show that you're actually detecting earthquakes versus just blips in the ionosphere? And have other people tried to replicate your work?
No, we haven't yet. That's why we're trying to, you know, like it's a real alien subject to say that earthquakes actually detect, that earthquake can actually change propagation. It's not something that is very well known or that's very well understood yet. So we're trying to get to work with HamSCI to see if they're interested in correlating some of the noise data that they're going to collect with the earthquake data that the USGS is putting out. And the USGS is amazing what they're doing in terms of earthquakes detection, worldwide earthquake detection.
Okay, and then there's a question of to provide some explanation for your antenna.
Oh, okay. Okay, the antenna is a stock version of it comes from High Gain. It's a 818. It's called 18HT-JR, and it's a vertical antenna that uses outlying wires to create resonance frequencies, kind of similar to a Chi match in a way. But it's a very interesting antenna. It has 5 specific resonant frequencies, and we're using those to measure the earthquakes. The interesting part about that antenna is because it's so tall, it has a very low takeoff angle. So when we're looking at incoming noise or incoming propagation, it's most likely to come from the horizon, and that is where the earthquakes seem to be most visible.
Okay, and the next one is, there are ELF and VLF precursor signals that people have discovered before earthquake events. Are there any precursor signals in the HF bands that occur before HF events?
I would say yes, but this is still highly debated. And we're trying to come up with a sort of correlation between earthquakes event and noise data. What seems to be happening is on the 40-meter band, and that seems to be quite a regular occurrence, is that the 40-meter band goes into sort of what I call transition oscillation, where you get noise jumps, like that you have a certain noise level for 2 hours, and then all of a sudden it just jumps down 10 dB, and then you have that noise level for another 2 hours, and then it jumps back up again, and it repeats itself. And this behavior always seems to dissipate after a strong quake. And we're still trying to kind of correlate that a little bit more. And what we're also seeing is that we have a lot of local quakes that have a significant effect on 80 meter and 20 and 40 meter propagation. And you would think that if an earthquake has an effect on propagation, 80 meters and 40 meters would definitely be the band that would be affected by it, because it's mostly local transmissions within the range of about 500 kilometers. So you would think that would be the effect of that minor local quake, a magnetic field size that it would develop. And since we're within the same distance range, there seems to be a correlation between the propagation and slow and really small earthquakes, especially when there's small earthquakes that happen in a fast, rapid transit.
Okay, we got one final question and then we'll move on to the next talk. And the question is, how long does a band opening last for a short-term earthquake?
Those band openings are usually, we measure this band opening between 5 and 10 minutes, and for the small openings. And it's amazing how well the ham radio operators are using the digital modes. Like it's always on, like there's like a constant noise that we can measure against. So the signals pop out of nowhere, and then there is a spike for 5 or 10 minutes, and then it disappears again. And that always seems to be correlated to a small quake, and mostly on 80 meters and 40 meters. And especially now that we have a low in the solar radiation. Does that answer your question?
I believe it does. And thank you, Alex. We're out of time and really appreciate your efforts.
Oh, can I say one more thing? I just want to say, if you want to check out, we have a real-time RF seismograph image on our website. So if you go to our website, it's there. It's updated every 10 minutes. So if you want to find out how propagation changes, or you want to figure out, what's the best time of the day to operate your rig, you go there and you check it out. And if it works for you, tell everybody else.
Okay, so Alex, you might want to post your link in the chat window, and I think a couple other people are chiming in, but I'm afraid this is all the time we have for you.
Okay, I'll put that in the window.
Okay, so thank you, Alex. Now we're going to move on to our next talk. And Masaki, I hope I pronounce this right. Masaki?
Yes,
okay.
That's right.
Okay, you want to say hello and introduce your talk?
Yeah, but please play back my MP4 files.
Okay, you want to do that first?
Yeah, I'm Yonezawa of Packet Radio Users Group. I have a small presentation for the FX25 compatible TNC and new idea about FX25. Now, please play back my presentation.
Okay, so go ahead.
Packet Radio Users Group. This presentation will describe the features and configuration of the FX.25 compatible TNC currently under development. It will also include proposed enhancements to the FX.25 standard. PRUG, Packet Radio Users Group, is a non-profit, voluntary organization in Japan. It was established in 1985. This section describes the development status of the FX.25 KISS TNC. The FX.25 KISS TNC is in the alpha test phase. It is operating as an APRS node at 430 MHz and has proven to be compatible with AX.25 stations. Currently it uses UI View as an application. Look for JK1MLY on APRS network. It running FX.25 station. There is a plan to add Wi-Fi to interface with the PC. The goal is to increase the flexibility of the TNC's installation location. There is another plan to run applications within the TNC. This is intended to realize independent sensor node. We use a Bell 202 compatible TCM3105 modem chip. This is because of the importance of physical layer compatibility. We plan to implement a software modem in the next version. The ESPWROOM32 Wi-Fi module is the key component. It can handle multiple channels of error correction and software modems due to the high processing power of the CPU. The power supply is also provided by USB when interfaced to the host. The hardware configuration is very simple. The next version will use a software modem and will not require the TCM3105 modem chip. The software is written in C language. FreeRTOS is used. Each function is defined as a task in the OS. This makes the software more readable and easier to modify. The software is available on GitHub. This chapter proposes an extension to the FX.25 standard. Long AX.25 packet can be sent in a single frame of FX.25 without splitting it up. That will be easier to operate and implement the system using error correction communication using the existing environments. This means that not only AX.25 but also various higher level protocols can use the error correction function with relative ease. It is possible the system to be more resistant to further burst errors as the effect of constructing a frame with multiple blocks. Compatibility with the existing AX.25 facilities is maintained. Frame structure of FX.25 drafts. In the FX.25 draft, if the data did not fit in the RS block, the data was split and sent as multiple FX.25 frames. The maximum I field length in AX.25 Vir.1 is 256 bytes. This packet may have more than 300 bytes due to bit stuffing, AX.25 header and FCS. Therefore, this packet cannot be sent in a single FX.25 frame, so the frame is fragmented. FX.25 TNC side needs to have reframing feature for AX.25. And the FX.25 frame is added more bytes of correlation tag, flags, address fields, control fields, FCS pads, etc. This constraint causes a decrease in transmission efficiency. And the lower protocol must know the frame structure of the higher protocol, which adds overhead between protocols and loses protocol independence. One large FX.25 frame by combining multiple blocks. It enables FX.25 to send long messages. You don't need to split the frame. The problems presented in the previous section will be solved. Now consider the use of multiple RS blocks in a single frame. If the RS blocks are arranged in the order of message and parity, the messages are divided by the parity and the code cannot be received by the existing facilities. Therefore, we arrange multiple blocks of messages together and then place the multiple parities behind messages. Since the message part is continuous, we can keep compatibility with the existing facilities. The upper protocol is not limited to AX.25 because the data from the upper layer can be sent without processing that part. Also, here, interleaving can be introduced to increase burst error resistance. Interleave and parity calculation are performed while maintaining the AX.25 packet structure. We propose a format that combines two types of correlation tags for frame with multiple blocks to reduce the number of tags consumed in the future. The correlation tag specified in FX.25 draft standard has the function of specifying frame synchronization, frame length, and coding scheme in one tag. A large number of tags would be required if we allocate a correlation tag in an exhaustive manner with respect to the combination of block length and coding scheme. 64 of FX.25 defined gold code sequence PNCode would be easily exhausted as a result. How to reduce the number of new correlation tag allocations. The assignment method here defines a tag that represents the frame length. Separately, define and combine tags that represent the encoding within the frame. The first tag also provides frame synchronization capabilities. Although the headers look to be larger, the proposed method requires less data in total than the original multi-block structure in FX.25 draft standard. This allocation method enables large-scale expansion to support arbitrary frame lengths, numerous encoding methods, new protocols. Tag number 20 is used as an extension tag. This ensures that the extension tag does not interfere with normal tags. Since the extended tag does not need the frame synchronization function, it is possible to use a bit rotated version of the extended tag pattern already assigned. 63 tags can be assigned in this table space. This extension creates a lot of space for correlation code allocation. We reserved a 16 by 63 tag space using the expansion tag. Almost half the allocation space is still free. Please visit PRUG website for further information like schematics and software. Sorry, most information on the site is in Japanese, but recently Google Translate works well often. We welcome translation volunteers.
And thank you, Mizaki. And questions? And I see that Gregory posted the URL to the GitHub repository.
Thank you. And I have several list of answers for the expecting questions. I think most of you have the same question, so I prepared for that questions. I think most of you interested in the price or delivery date of this TNC. The answer is sorry, currently it is not for sale or trade of you. It is intended to be used by the development member of our groups. And the good news is that schematic and the answer is currently or trade to public on the GitHub. You can download the data and you can use to build your own. And that schematic and pattern data is open to public. Bad news is that the data and you can use to build your own documentation is written in Japanese, so you can you may use Google Translate, but I'm not sure. Sorry. Are there any questions?
There is one question. They're asking, is FX.25 used on HF in Japan?
Not yet. And only several stations using FX25 on VHF and UHF. Sorry. Any question? Not the stations using UHF only. It's only.
Okay. And any other questions in the chat box, please? This is a rare treat for everyone. This is 7 a.m. in the morning for this gentleman.
Yes.
We are getting compliments on your presentation. We have a question. Any comparison in throughput of FX.25 to the older AX.25?
Good question. Under consideration, we should compare it in very many kind of environment. I think it's the propagation environment very clear, no error. AX25 is better throughput. In the noisy environment, FX25 will be better.
Interesting. Okay. Any other questions? And a kind attendee has taught me how to pronounce your name, Masaaki.
Yes, that's right. Thank you.
Thank you very much.
Thank you for being here, Masaaki.
Thank you.
Okay, we're waiting to see if there's any chat questions. I'm looking over on YouTube as well. Okay. Well, I'm afraid it's quite quiet, but there is quite a few compliments on the chat window thanking you and congratulating you on a good presentation. So thank you very much.
Thank you.
Okay, well.
Yes, if you have any questions, send me an email or a chat room.
Excellent. Okay, I hope everyone got that. So email questions, or we can do in the chat. Okay, one comment, nice to know that X.25 technology is moving forward in the modern world.
Oh, thank you.
Any other questions or comments?
Oh, ありがとうございます.
There you go.
Yes. Thank you.
Yeah, it's interesting with Google Translate. Lots of the translation services on social media work quite well, and it's quite fascinating to be able to now read other websites as well.
Yes.
And of course, when we do searches, now we can find additional information. Okay. Well, I think we can go ahead and do a wrap right there, and want to thank you again, Masaaki. And we hope to hear from you again and Prug and their progress. It's really wonderful to hear that Prug is still alive and well.
Yes. I'll come again, DCC.
We'd love to have you. So a lot of the suggestions we've been talking about in a hybrid DCC is to do a lot of the similar things that we're doing here in person, so that allows that type of interaction to happen. So we'll work that into next year's if we're allowed to get back together in groups. That's the big gating factor right now. Okay, well, let's go ahead and wrap it up for the day. We've had over 9 hours of time together. We've had about 2 hours worth of breaks along there. So there's been 7 full hours of presentations and talks and I hope you'll agree that it was quite a excellent day. Thank you for the claps there. And
make it to his pub in 15 minutes. He's buying.
See, that's the hard part here is we would all break for dinner and an adult beverage. So at least
and the discussions would continue on until the wee hours of the night.
Yeah, absolutely. And there'd be a lot of back of the napkin and a lot of new ideas fermenting in that soup, which makes the in-person DCC so special. So if you've not had a chance to be at an in-person DCC, we invite you. We know it's not easy. We know it's not cheap. That's why we travel from city to city in the hopes that we're able to be in your city and close to where you're located so that it's easy to get there. We will start up again tomorrow. First talk is 9 a.m. Eastern Daylight Time for the West Coasties, that's 6 a.m. Pacific Daylight Time. That'll be 1300 Universal Coordinated Time. And we got a lot of great talks set up for tomorrow as well. And there's several other foreign dignitaries. We've got Marco from Italy. We got Michael from Germany, who we heard a little bit today. And we got David Rowe from Australia.
Don't we have somebody from France?
We do. I'm glancing here. Yeah, Anthony. So yeah. The first and second talk, Italy, France, and then Gwen, G3ZIL from the UK. So we got quite an international audience. So we're really fortunate. The virtual DCC is giving us this flexibility, this ability. So we're really excited to hear from all of these presenters. So we definitely need
Michael from Germany.
Yep. Mm-hmm. All right. I guess let's not have some long goodbyes. Let's go ahead and let everybody take a break and get a good night's sleep, and we'll see you tomorrow.